opening the doors. And we are live. Good morning, Clojure.
Hello.
Hello, everyone. Feel free to unmute. Feel free to have a little chit chat before we start. Tell us where you are connecting from. How's the weather there? Especially if it's sunny and warm. That's appreciated.
It's actually much better. It's actually much better weather today than yesterday here in London.
Yeah, that's true.
Yesterday when we woke up, it was like super grimy and dark.
Indeed, improving. Got Berlin. That's
cool.
Normally roughly the same weather we have here in Germany. Well, Berlin is far east, but
yeah, it's pretty close to where I was born. Actually, I'm just on the other side of the border.
What is that, Pavel?
Oh, I was like, my hometown is northwest Poland, so it's really close to German border. So it's like, I don't know, 200 kilometers from Berlin or something.
Overcast in Cape Town, but still quite warm. That's the catch. Like quite warm. That's good.
That's nice.
Yeah, in time zone, we are not far away.
Oh no, I mean that's probably why we have people we have here. The US is fast asleep now, right?
Yes.
5 to 4. Right. Yeah. Well, East Coast is what? 4 o'clock in the morning on the East Coast.
Yeah, it's time for another coffee. Well, I'll wait for the conference start, like the first break.
Well, you're doing the introduction, so
yeah, I'm not going now.
You can't go and get coffee now.
Well, it was I don't know if the people here attended the conference yesterday, but it was, I think, quite a blast of talks, discussions, and it went smoothly, right? Like no big technical problems. Some like people troubled with connections. Yeah, that's always the case. And Zoom is not making it like particularly easy to find settings and stuff. So I don't know if we could do the conference on Google Meet. It's probably a little bit too big. I'm not sure. Oh, oh yes, there's somebody from New York.
I think so.
I'm an early riser. Okay. Or late sleeper.
Hey, morning, guys. No, I set my alarm pretty early.
That's
thank you. If it's for the conference, thank you.
Yeah, no, it was. Yesterday, I also got up early, and it was one of the most phenomenal days. And Stephen Wolfram's talk was...
Yeah.
Okay.
It's like having a hangover, in the morning after that talk.
Yeah.
Yeah, there's a lot to decompress.
Just wanted to thank you guys. Like, the workshops have been fantastic. Like, it's been such a great introduction to like the landscape of Clojure data science, and yesterday was just outright amazing. I don't know how you guys do it.
Thank you. The workshop that should really go to Daniel, who's present in the chat as well. The credit should go to Daniel and the Clojure community. Who's
Yeah.
Daniel is this, yeah. Oh yeah, he's unmuted
Oh,
now.
so many people were involved. So many people
Yes.
were preparing, struggling to prepare workshops, and yeah, so it was really many people involved. And hi, Amma, will you join tomorrow? Maybe.
Yeah, I will
Oh,
definitely.
wonderful. Yeah.
Yeah, like I remember, like the J language is like pretty interesting. I first came across it like I think in 2006, because I was working at Lehman Brothers when they were a thing, and we were using KDB.
Oh yes.
And I was just like looking for an open source alternative.
Yes. That's cool.
So you used to write this language?
Not in J. I was using, well, I guess there's a language called K, and then there was like an evolution of that called Q, and then a database implemented in the K language, and that was called KDB plus. And I think so. Like I was trying to like use Common Lisp before, like since I've been trying to like use Common Lisp, or I was trying to use Common Lisp since like 2001 or something, and never could find the opportunity, and then ran into KDB plus, and it was just so much fun because it was like interactive development, really, but yeah, it was like a really niche environment. But yeah, when he says like APL and Lisp have been big, I was like, yeah, I didn't end up where you ended up, but they were big influences on me as well.
Will you maybe comment about this experience tomorrow if you happen to be at the J Talk? Yeah, I'm not sure if it is very late for you, but
yeah, no, I'll be happy to.
Very early, sorry. Very early.
Yeah.
Oh, yeah. Yeah.
So the J workshop is going to be the first one tomorrow, right?
Yeah, we will begin tomorrow with some, just interactive sessions, playing together with data. And then the first actual talk will be about J by Oliver. It will be short, and then we'll have a brief discussion. And all the day will be mostly that, just people talking briefly and then having discussions mostly. That is what we hope to have, like project maintainers discussing things with each other. And then we have Pavel, Pavel, should we maybe talk about what you're preparing for tomorrow?
Well, I mean, I'm gonna talk about it tomorrow, so I don't want to give it away. No, we did some work on reviving this library that is still called Clojure. It's probably going to change the name. It's the bridge to the Wolfram language. It's the thing that Stephen gave a kind of short demo yesterday. So we can use all the stuff that's in Wolfram language. So I'm going to talk about that a little bit tomorrow. Maybe show a little bit, show a little bit more from Clojure perspective and how it integrates with the editors that we use and some tooling that we have now, that kind of stuff.
And then after Pavel's talk tomorrow, we'll have those group discussions where we will take some time to think together in small groups, and we will pick a few questions and people will be able to kind of suggest other questions so that we can have some thinking about where we are, where we're going. So that is kind of how tomorrow is going to end. And then maybe we'll stay to play more with the REPL.
Indeed.
Hello, sorry about that. I was had a fiddle with my settings.
I can't see you, David.
Oh yeah,
where are you? Oh yes, okay, I can see you now. I think it's because you. Oh yes, the cat. Yeah. So the official start is gonna be 9:45, right?
Yes, we're gonna kick off at 9:45 with the logistics and some information about the day, and then we'll go straight into talks. We're gonna have Christoph Grand start with, and Adam Hellings. Two very interesting talks, by the way. Two very like ambitious projects, both of them.
Indeed, yes.
Right, I'll whack out a tweet to say starting.
Thank you, David.
Please.
Clojure and Slack as well, maybe?
Yeah, no worries.
Brilliant, thank you.
Please. Let's see how the population on YouTube is doing. We got 45 playbacks and counting,
Oh,
and 12 concurrent viewers. So we are starting slow, but this happened last year as well on a Saturday morning. And every conference, even live conferences, is the same. Speaking of live conferences, maybe next year we're going to do live again.
Well,
No?
what's the letter of the Greek alphabet we can reach by then?
Yeah.
Data?
Theta.
I mean, the one thing that if it ever happens, if it ever happens that we go back to live conferences, I think it will be required to do both, to do like hybrid, because people will get used to, like everyone's now used to the fact that this is streaming and everyone from around the world can access. So we would have to like do both, I think. We would have to stream and
Maybe the future of conferences is hybrid.
Yeah.
Like a controlled room with all the live streams, Zoom and whatnot, and a live audience, which is making it double more complicated and risky.
Yes, yeah. But live you get to hang out with people and you get the serendipity and just chance encounters, chance interactions. That's all cool. Difficult to recreate online.
We're being streamed live on YouTube at the moment, by the way.
Yes, yeah.
Where? Did you ask where? I can post the link if you want.
No, we are.
We are.
Yes, we are.
Because yesterday we weren't until.
Oh, did you?
Yeah. I clicked on the live and I can see the live streaming going.
Yes, yeah.
And people like watching it as well.
So it's just you starting today, Renzo, right? And then John should show up.
Yep. If he's not, no problem.
I think he's on Discord now.
Yeah, I wanted to say something about having the next conference half presential and half online.
Mm-hmm.
Some countries have a very strict policy, like in Taiwan.
Mm-hmm.
If I want to leave the country and come back, I will have to quarantine for 2 weeks, and it's too much. So I will still not be able to go in Europe next year.
If this situation is the same as this year, it's probably not going to be live. To be honest, I think it's just too volatile and unpredictable because what you're saying, right? It's like we don't know, and the policy can change really quickly. And so if the situation is the same, it's probably going to be virtual. But if it's better, then maybe it's going to be hybrid. So if you maybe the restrictions that are in place now are going to be lifted, so you can come over, and if you can't, then you can still watch the stream. I mean, that's the best of both worlds, right? But difficult to pull off.
It's still a very big maybe.
Of course, yes. Is David co-host, Daniel, me?
Yes, Daniel disappeared.
Okay. Like David's saying yes.
But fair enough. I mean, we can kick off.
Let's do it.
Cool.
Have a good day, everyone.
All right, so this is the official start. We had some nice chit chat to warm up ahead of the official beginning of the conference. Welcome to this second day of Reclojure. We had a very nice first day, so if you happen that you missed it, you can catch up either on the YouTube stream and like with some time, like in the next following days, we'll get all the talks live as well, like as a separate talks that you can watch independently. So be patient with that. We'll do our due diligence in the next few days. Once again, thanks to our sponsors, Hide and Health Unlocked, Newbank, Freshcode, Juxt, and Gaiwan. We had a few of them talking about their companies, about their values, and the fact that they are hiring yesterday during the sponsor pitches. Feel free to ask any questions to the dedicated channels on Discord if you want to ask anything about these companies. Well, a few logistics information for those of you who specifically weren't here yesterday that already heard this, but there are also like a slightly different things. So stay with us. All the general interaction in main conference is happening on Zoom, where you are now. Well, those of you who are here, and on YouTube instead we only have the streaming without interaction. On Discord we have all the asynchronous interaction. We collect the questions for the Q&A for each panel there. We have different topics for different talks. We have the organizers online that you can contact there if you have any problem joining any of our channels or any other information you might require. Just use the @organizers to reach all of us at the same time. That's probably the best way to notify us, and somebody will be with you. The website contains the main schedule, abstracts, and bios. We're going to do a little bit of work introducing our speakers today, so you don't need to go constantly there, but feel free to see more deep informations onto the schedule on the website. Twitter for any comment or excitement you want to share with the rest of the world. That's very appreciated. Use the hashtag Reclojure or @Reclojure on Twitter, and just go ahead and say if you like it. Even if you don't, let us know as well. Maybe feel free to give us any feedback. We're going to ask for some feedback throughout the day anyway. The format is the same as yesterday. There's going to be 3 presenters rotating throughout the day. Jordan, she's going to join us later on after 2 p.m. UTC. John should be with us for the second block of the day, and I'm starting the conference today. And the blocks are 5, and they all 2 talks followed by a QA panel, and there are short and longer breaks throughout the day. We're going to have some interesting visual art displaying for the breaks, so those are very relaxing, and so stay with us and keep the display running while you're doing maybe something else, grabbing a coffee and so on. The interlude today is going to be about lightning talks, but there's a slide dedicated to that, so I'm going to jump to that later on. And at the end of the day, of course, we have Gerald J. Sussman keynoting. Start thinking about all the relevant questions you might have. Go and grab your book, take it with you. I think he's he would be very happy if we all show his books later on. So if you have it, this one or the SICP, of course, that's valid too. I have my copy, but I left it on purpose to my previous employers to spread the word. Like, it's something that I do when I change job. I leave like all my favorite books on the desk of somebody so they can read it when I leave. Here with the lightning talks. So we are going to use the interlude time, which is like 5 by 5 minutes slots. So five 5-minute slots available for lightning talks. We have 2 pre-booked lightning talks about communities. We have 2 community leaders just chatting about their experience running their communities, so we can like share experiences, feedback, and tips and tricks about like how you grow a healthy Clojure community. We have a couple of lightning talks already proposed on the Lightning Talks channel on Discord. So please go there, put your thumbs up to vote the one that would you prefer to see. If we have more than 3, then we are going to use the voting system and just pick the top 3. If we have only 3, of course, we're going to showcase all of them. So connect for the Lightning Talks. Go on the Clojure website to see when the slot is, because I don't remember exactly the time. And this is a new thing. So there's going to be a 3rd day of the conference. It's a special day. It's also a data science special. It's got a lot of talks, a lot of working groups, and a lot of interesting material. So many interesting topics that is going on for another 12 hours. So this is just a very short summary of what you're going to see tomorrow, or what you can participate in if you want. And of course, it's going to take some of the talks and technologies that we heard during the first 2 days and explore them a little bit deeper. So go ahead, grab your ticket. So at least Daniel, who is mainly organizing the day, knows how many people are joining, and just head over to either the London Clojure meetup. The event for the day is showing up there, or grab a note of this bit.ly link below here. I'll leave it for 1 second or 2, but it's data science special. Well, ask on Discord. Well, how to interact? We want just to remember a little bit how we plan to interact over the conference. So during a talk, you can only use the Zoom chat or the related Discord channel to post questions or comments. Those are very welcome. And during the Q&A, instead, you are very welcome to raise your hand to like make your question live. It's going to make it way more interactive for the speakers as well. So that is our favorite way to promote questions, and raise hands normally have priority over Discord questions. Over the break, just take some fresh air, relax, stretch a little bit, because it's going to be long, over 12 hours of goodies and incredible content for you today. If you want to showcase something or chat with people, like microphone and camera on, there's a couple of Discord, a channel called Showcase and Lounge. In the idea of Showcase is if you have you want to display your screen for a second to somebody who is asking you something, you can display your screen and show something interesting. And on the Lounge, you can just connect and have a chat, a normal general chat. Contact the organizers, Discord at organizers anytime. Code of conduct, we are enforcing the code of conduct today. Very common sense indeed is just be polite, accept everyone's opinion, and in general, be nice with each other. And is mainly what you need to know. We like in our 3 editions of Reclojure, we never had a problem. So we'll just continue like that. Thank you everyone to be relaxed and enjoying the conference. Big thanks to the dream team of organizers this year. Bruno, he helped us a lot in the months ahead of the conference. Daniel, especially for organizing the workshop and the bridge between us and the SciCloj community. David, Felipe for the website, John for presenting today and helped throughout the year, Jordan, Pavel, Peter, Renzo, and Satya. Thank you very much, guys. And our wonderful speakers, their effort is very appreciated and is making this conference what it is, a success. Wonderful keynoters that you will see on YouTube, Stephen Wolfram, and today, Jerry Sussman, and community leaders, of course. Our mighty sponsors that I already thanked at the beginning of the conference, and I will do again throughout the conference. But above all, thank you for coming. Thank you for attending the conference. And now let's enjoy the show. All right, so the first talk of the day, let me just prepare. So we are going to see that we are entering the first block of the day. We're going to have 2 talks and a QA panel. The first 2 talks are very interesting, are 2 ambitious projects that we want to know more about. The first is Christoph Grand. Christoph is an independent software engineer and has been coding and teaching Clojure for more than 10 years. He co-authored Clojure Programming by O'Reilly. He contributed non-trivial parts of the Clojure core code base. He's author of many important libraries like NLive, Xforms, and many more. He's now embarking, along with Baptiste, I hope I pronounced his name correctly. He's now embarking in yet another adventure, like bringing Dart to Clojure. So let's hear about that. Thank you.
Hi, good morning, and welcome to the first talk of this morning at Clojure. First, let me introduce myself. I'm Christoph Grand. I've been a long timer in Clojure. I've been working in Clojure since 2008. I discovered Clojure when it was maybe 3 or 6 months old, and I worked mostly exclusively with Clojure since then. I'm an independent software developer up to 2 years ago, where I joined forces with Baptiste Dupuche. Together we are Tensegritics. Tensegritics is governed by 2 simple rules. The first rule is that I'm always right. The second rule is that if I'm wrong, it's always Baptiste's fault. Here is the story of how I got tricked into writing a Clojure port. It's Baptiste's fault. For a long time, he wanted to write a Lisp implementation, and he was also very interested in trying to reach out to mobile development. At the start of the first lockdown in Europe, so spring 2020, Baptiste got enough time to try to evaluate the options. And among the options, he first evaluated targeting Swift, and after some time, he settled on Dart and Flutter. It was totally not on my radar, not a single blip. I was quite amused by his sensitivity. In the following months, I don't know if it's a pure coincidence or me paying more attention on social media to Dart and Flutter, but I noticed it here and there, and seeing mostly positive reviews, especially about Flutter. And I think that the tipping point was when I heard both David Nolan and read a positive tweet by Patrick Logan about Flutter and Dart. And so maybe there was something true in, or at least valuable in, what Baptiste was trying to achieve. I talked a bit more with him, and at last, he convinced me. As of late September of 2020, I agreed to help him write Clojure Dart. But first, maybe you are like me. You have no idea or very faint idea of what is Dart and Flutter. They are both Google products. Dart is kind of a very typical static language. There are a couple of things which are interesting in Dart. First, it is able to target either JavaScript, its own VM, or native code, be it x64 or ARM. Another interesting part is that it seems to have a conflicted relationship toward dynamism. Maybe it's because its history, how it grew as a language. Last, because initially it targeted JavaScript, its concurrent history is almost the same as JavaScript. You have workers communicating through messages. You don't have shared memory concurrency. Flutter is a cross-platform GUI, and it allows you to target mobile. It also targets web through Canvas, and it now reaches out to desktop even. It's becoming more and more compelling to use Flutter to make desktop application. As I alluded to earlier, Dart dynamism is a bit conflicted. You don't have dynamic loading, but you have really good hot reloading in the Dart VM. It's statically typed more than Java, but it has a pseudotype named dynamic, which changes the way methods are resolved. When you use dynamic, you are close to what you get in Java when you are using reflective calls. There's also a funny runtime type property which can be overridden. When you override it, you can make it without anything, so runtime type can blatantly lie. In the same vein, you can only check whether an object is an instance of a class if the class is a compile time constant, so you can't implement instant question mark. Now, the chronology of the events. In the spring of 2020, Baptiste started to work on Clojure Dart by itself, and as of September, I joined him. We decided to reboot. Our goal was to write a very minimal compiler in Dart for a subset of Clojure. The compiler would evaluate Clojure code and use the auto-reloading mechanism of the Dart VM to patch itself, replacing very simple stuff written in Dart by actual implementation in Clojure and so on. So growing the subset of Clojure until you get a whole language. It was too ambitious. We had a hard time keeping track of what was the current subset, plus subsetting Clojure is not that easy. So 2 months later, we changed our mind and decided to run the compiler inside an existing Clojure implementation, a more typical bootstrap strategy, where you write the compiler in the language itself and you use an existing implementation to compile the compiler and get the actual compiler. In one day, we ported the compiler we had in Dart to Clojure. It was a single pass compiler. 1 month later, we realized that we needed to introduce another phase. So we split the single pass in two and introduced an intermediate representation based on S expressions. This design has served us well because we haven't touched it anymore. We just made some course corrections which are more like tactical changes. The first one was in May of this year, where we realized that if we were going to wait for the compiler to be able to run on the Dart VM, we were going to wait a long time before delivering something valuable to us and the community. So we decided to broaden the capacity of the compiler while in a hosted environment. Up to now, our only goal with the compiler while running in Clojure on the DJI VM was to be able to compile itself. Now we made changes to be able to compile any user application with the compiler hosted on JVM. The second correction that occurred is the realization that as we were going better at emitting Dart code, the more precise the types we were producing, the more types we have to get right. It kind of snowballed, and we had to bite the bullet and really produce good type inference across all the libs using the Dart analyzer and so on. And this is what has mainly kept us busy since the end of the summer. Besides the compiler, we have 80% complete Clojure implementation. Some things are lacking, like sorted collections or multi-methods. Otherwise, we have most of core, some auxiliary namespaces. We have good interrupt with Dart. All Clojure collections are Dart collections, and Dart collection can be passed to Clojure functions. We support generics, which is important because in Dart, generics are not erased like in Java. We also support the name parameters. We have a lot of things. But interrupt was really important to us. It's even the first thing that we prototyped, because one of the pillars of Clojure is its interrupt capacity with the host. Let's cover some specifics about Dart. Well, about Clojure Dart. The first thing is optionals. So in Dart, a method can only have one signature. There are no overloads for a given method. But it can have some optional parameters, either positionals or named. For a long time, we had a special syntax for the named parameters. We use the dot ampersand to tell the compiler where the name parameters were starting. We don't need it anymore because we have the static information needed to know how many fixed parameters are expected. You are just going to write what seems the more natural keywords to denote the name of the parameters, and that's all. Another point of difference between Clojure and Clojure Dart is that in Dart, types are not nullable by default. This is something that changed over the course of the project. It was in the pipeline when we started, but we chose to ignore. Dart 2.12 introduced non-nullable types by default. It means that when you've got a function in Dart that returns string, it's not going to return a nil. And so it means that for a Clojure function, like namespace, which may return a string or may return nil, you can't type int as string in Clojure Dart. You have to type int as string ? We dabbled with the idea of reversing the behavior and have a string by itself denotes string or nil, and string ! denotes strictly a string. But after some experimentation, we realized that it was going to create more confusion and more distance with the host. So we keep the Dart way, which is to put a ? at the end of the type. Still speaking about nil, in Clojure, everything is true except for false and nil. And it's the same in Clojure Dart. However, to make tests more efficient, when we know that we are going to get a bool, we don't test for nil. When something is clearly not a boolean, like it's a string ? we only test for nil. When, as a user, we know that it's not going to be a boolean, we can use the sum metadata. For example, the seek function is going to return either nil or a sequence. And a sequence is whatever implements the sequence protocol. So we can't type what a sequence is in Dart. But we know that it's not going to be a boolean. So we have this sum pseudotype specific to Clojure Dart to be able to tell the compiler it's going to be nil or something which is definitely not a bool. Now, generics are not erased in Dart. In Java, generics only exist at the level of the Java compiler. For the JVM, they don't exist, so you can bypass many things. It's not the case in Dart. First change is that we need a way to encode the information about a parameterized type. And we have this constraint that the Clojure reader expects a typing to be either a symbol or a string. So we could have chosen to encode in a string the parameter's type, but it has drawbacks because you have to parse the string and you lose structured editing once you are in a string. After some head scratching, we came up with the idea of putting the type parameters in metadata on the symbol. By the symbol, I mean the symbol representing the type. So you put meta on the metadata. It's frankly a bit bizarre. But we realized that we could leverage taglets to emit this symbol with metadata. And so we have a taglet role for slash, which allows us to write list ? String to denote an optional list of string. Another thing about the generics is that they impact collections. Because when in Dart or in Flutter, you have something which expects a list of widgets. You can't pass a person vector as the list of widgets because a person vector can hold anything, hopefully. In the Dart collections API, there are cast methods, which are a bit magic because they are parameterized by their return type, but they allow to wrap a collection of a given type into a collection of another type. For example, a list of objects can become a list of string. It's just a wrapper. The list is still a list of objects underneath, and the type of the actual elements will only be checked on demand when they are retrieved from the list, for example. So you are moving a static errors to the dynamic realm. It offers us a way to transform our person vector of object, which is a Dart collection, a Dart list, to a list of widgets. But sadly, once you go this way, the object that you have is the list wrapper from Dart. It's not a person vector anymore. So it goes against an important design constraint of Clojure, which is to avoid wrappers at all costs. Then we realized that we could have type parameters on Clojure collections. These type parameters would be totally ignored. They are there only to placate the Dart type system. And so when you need to cast a persistent vector to be a persistent vector of widget, we are just creating a new route which has the correct type, but it's still a persistent vector, implementing all the Clojure protocols, being still equal to the previous one. And currently we are working on getting the compiler to insert the call to cast itself, so that you don't even have to care about your vector not being of the right type. There will be a dynamic vote to be able to be won when this magic behavior occurs. By default, it will be on. While we are on dynamic votes, in Clojure you've got one on reflection. In Clojure Dart, the equivalent thing, which is one on dynamic, is on by default, because it's more important, in our opinion, in Dart to get the correct types. So when Clojure Dart struggles to determine the type of an expression for interrupt, it's going to complain. Another thing about Dart is how do we require a Dart lib from a namespace. Here, we chose to do it in the same way that ClojureScript does. If the namespace is denoted by a string, then it's going to be a dot lib. Another thing which is important in Dart because it's leveraged by a lot of API is that Dart has built-in support for async and await. So first reaction was, okay, we've got CurrySync. But CurrySync is a word on its own. CurrySync has no good interrupt story. And here we have something built in the language and the standard library. So we need to offer something low level to be able to leverage that asynchronous feature. It's pretty simple. We introduce a new special form, await. So to summarize, we learn that so you don't have to, so that you can reach out to mobile, to desktop, to native applications without having to learn the language, only learn the libraries and in particular to learn Flutter. Now, Baptiste is going to give you a short demo of what it is to code with Clojure Dart.
Hello friends, I am Baptiste, the other half of Convex and the Clojure Dart compiler. I have 4 minutes to show you what it's like to use Clojure Dart for writing iOS and Android applications. So basically I have a scaffold application with only text. If I edit text here, this text is not centered. I have to recompile Clojure Dart file, reload the application, and yeah, we see the text. So now what I want to do is just build a list of dates in French. So to do that, we need to use the list view component, which is a default component from Flutter. List view takes a children property, which is a list of widgets. So def list view, it takes children, and as input we have a persistent vector of strings of dates. So I want to build some Flutter widget. I'm going to use the list tile widget, which is just a tile basically, and it takes a title, which is also a widget. So material list tile, and it takes a title, which is a widget, so I have to use widgets text, and I can give him the input one. So now let's try to compile it. List view, we compile Dart, reload the application. Oh, it doesn't work. And it doesn't work because children waits for a list of widgets, and we gave him a persistent vector of dynamic. So persistent vector implement list, so this part is good, but dynamic is not widget. So on this version of the compiler, we have to cast inputs. It will be done automatically, magically, when the compiler is open sourced. So we just cast this vector of widgets. We reload. Oh, now we have a list of days in French. We can even add some other components. Let's say we want a divider, material divider. And here we go. So basically we are using Clojure data structure to build our widgets. We have a lot more experience now with bigger applications, and it's been a blast. We are very excited to open source Clojure Dart soon. We still have some work to do on type emission and magic casting, like you can see. And I hope you enjoyed this video. Thanks a lot. Bye.
So I guess that by now, your main question is, when can we get our hands on Clojure Dart? There are some things that we want to fix. First, finish the work on type inference. There are still some things to tune. And there's the introduction of the magic cast. And last, there's something about interrupt which is pretty important. It's about how Dart functions and Clojure functions relate. With more experience with Dart now and a better understanding of the language, we are questioning some design choices that we made earlier. So our current estimate is to release Clojure Dart in the first quarter 2022. Finger crossed. Last thing, this work wouldn't have been possible or not at this pace without the support, the faithful support of our sponsors. I say faithful because these are people sponsoring us, believing in us, even if currently all you get is vaporware. There are dozens of individuals who helped us, and two companies, Newbank and Rome Research, both supported and still support our work. So thanks to you all for listening, and thanks to our sponsors again for helping us bring a new Clojure implementation that will increase the reach of Clojure. Thanks.
Thank you, Christophe. That was a very interesting talk, and we are looking forward to the question and answer to ask you a few more questions. Start collecting your thoughts and questions for the Q&A later on. Please post your questions on Discord. And for now, we're going to take a little break and enjoy some visual art. Welcome back from another relaxing break with visual art and some nice music. We're going to have more throughout the day, so feel free to stay on when these are running. I want to introduce to our co-host as well today. John is with us now.
Hello. Hello, everybody. Hope you're having a great conference.
Yeah. It's been great yesterday, and is like everything is lined up to be another great day today as well. So we are having now our next speaker, Adam Helens. This is another interesting talk. Adam and his team is embarked on another interesting adventure, a decentralized and distributed system supporting a language strongly inspired by Clojure. Adam is one of the core developers of Convex, and after his talk, we will be joined by another old-timer in the Clojure community, Michael Anderson, also known as Mikera, of Core Matrix fame. So let's look at the talk, and we'll be back later.
Hi and welcome. My name is Adam Helens. I'm a Clojure consultant as well as a psychologist from the tiny country of Belgium. The topic I'm about to expose today might be a bit polarizing, we could say. I'm sure that most of you have heard about blockchain or crypto in general, but the thing is, there is so much buzz and fuzz going on that it's hard to have a clear understanding of what such decentralized systems really are. So that will be my task for today. Try to provide you with a more balanced, a more realistic understanding of what decentralized systems are and what you can achieve with them. Lucky us, it turns out that Clojure as a framework, as a way of thinking, becomes very useful for that kind of task at hand. The word decentralized is not new at all, but it certainly has become pretty well known in the field of computation for the past few years. But really, it's just the act of trying to avoid concentrating all our things, all our stuff, all our resources into one area, whether it's speaking physically or conceptually. Why, you may ask? Well, let me show you this picture. This is the Evergreen boat that blocked the whole Suez Canal not that long ago. And this whole thing has resulted in billions of dollars of losses because a huge part of the world's logistics was simply halted. Now, sure, the whole canal remains a good idea in spite of that kind of incident, but the thing is, it shows that centralized systems introduce single point of failures, and usually at more than one level. And so as a society, we would benefit from at least trying, to avoid that kind of scenarios, whether we are talking about the distribution of goods or services or politics or economics or education. The common denominator that I see in all that is that we tend to centralize truth and trust. Now, putting those two words in the realm of computation, truth would be data. Effectively, you don't really want your data to be represented by one single source of truth, because when that source of truth starts to misbehave, then there is nothing you can do about it, and your data is essentially brittle and vulnerable. Trust would be more about permissions. We want to have a clear model, a clear idea of what individuals, what entities owns what capabilities over some pieces of data. But it's not enough. You also need security. You need the guarantee that those permissions will be enforced. And once again, you don't want one single entity to be behind that kind of guarantees, because otherwise, as soon as this entity stops behaving in your own best interest, then once again, there is nothing you can do about it. If we had a way to decentralize those three aspects in the field of computing, we would reach something that is commonly known as the Internet of Value. We could say that it's a network that's effectively this public database, public as in anyone can read from it, and it is massively replicated. So we don't have a single source of truth, we have many. And it's a peer-to-peer network where, in theory at least, any peer is just as good as the other one, and it's a permissionless network. You don't want to be asking permission from anyone if you want to join in and take part, because then you could be vulnerable to censorship. And of course, people will try to cheat the system, as always, so you have to have a secure protocol that guarantees that even in the presence of such malicious, malevolent peers, the whole network still performs as intended and securely. If we had that kind of network, then the word value in Internet of Value could have two meanings. First, it's data, right? But this data becomes so reliable that it can be seen as an asset. Asset as in the sense of being useful or even having a monetary value. And this opens the door to so-called digital assets. Now, we don't have to go that far, of course. If you don't care at all about digital assets, I'll be mentioning NFTs later, for instance, non-fungible tokens. If you don't like that kind of stuff, we don't have to go there, but that's how far you can go, essentially. One implementation of such an Internet of Value is the Convex network. It's not the only one, I'm not going to lie. There are quite a bunch of projects trying to achieve this vision, but this one has been designed to be especially energy efficient, because many networks tend to waste resources and energy. And it runs on the JVM, which is really convenient for us Clojurists, because then we can access this stack and use it, any part of it. And what is more important here is that Convex has been designed and really based on what we could call the Clojure philosophy. And this is super important because, you know, it is kind of rocket science. It's a really complex piece of tech, a really complex domain where we mix, networking and distributed systems and databases and cryptography and all that. So if we could borrow ideas that you already know, then it would certainly be a lot easier to understand. What I mean here by the Clojure philosophy is fairly uncontroversial. First, we like to use a fairly small number of data types because we have shown, many times that we can build very complex data models if we are careful about the basic data types, the basic building blocks that we choose to do so. And those data types are even more versatile when we can combine them. Like in maps, for instance, keys can be literally anything. And this strong emphasis on immutability is something that is really important for that kind of system where truth and time have quite precise meanings. So let's start with the very first step, the data itself. Here we can see decentralized data values, or also known as cells for short. Now we can see that they have this strange familiar aura to you because, yes, they have been modeled directly on Clojure data types. So I don't have to explain you what are symbols and vectors and keywords and maps and all that. We do have a couple extra ones, like we have blobs, which are effectively kind of byte arrays. In this network, we have accounts, and those accounts have addresses. We can see here address 42, for instance. But yeah, overall, we are pretty good to go as such. Now, why are they called decentralized? How are they different from just Clojure types? Well, it would boil down to design and implementation. Because we will care a bit later about persistency and the network, we had to embed that into the design of those types. Notably, they have a very dense and very efficient binary encoding. And this binary encoding tends to match quite closely the type that it represents. So if you give me a vector, for instance, an encoding of a vector, I will be able to very quickly deserialize it into an actual vector because the number of steps is quite reduced, and vice versa for serialization. And you know how Clojure types have, these collections have structural sharing? Well, you could borrow that kind of logic for the encoding themselves, where if you have, say, a vector once again with a very large item in it, you don't have to actually embed the encoding of this item into the vector. You could just store a reference. And a reference here would be the hash of the binary encoding of that item. That will become a bit more clear in a minute or so. Imagine this vector of integers from 0 to 100,000. So we have effectively 100,000 elements, yet if we look at its binary encoding, it's only 70 bytes. So what happens here is that obviously we don't have those ints here embedded in the vector. What we stare at are a whole bunch of references to subvectors. And what this gives us are fast incremental updates. So the state of the network could be gigabytes. One day it could even be a terabyte. What happens here is that even though the state could be that big, if I modify it, for instance, and I send its binary encoding to you, you'll get that kind of very compact, very dense definition, and you'll be able to very quickly spot what is different. Most likely just one reference has been changed, for example. And then you can ask me back for it. And we can go back like this, back and forth a few times, and very quickly, even though the whole state might be huge, you will be able to get up to date with me. And this is super important for networking, obviously, but also persistency. Just a quick example here, because we do have some Clojure libraries that you can use for many things like creating those cells. We have this star macro here where we can use Clojure notation to create those convex cells. And many functions, I mean Clojure functions, standard ones, tend to work with those. And for the rest, we have some alternatives that we would expect, like conj, get, and assoc, and all that. Now, it turns out that if we take care about those cells and implement them, then implementing a database, just a plain local database, becomes a lot easier. Let me introduce you to Etch. Etch is a database, I think it's a 1,000 lines of code, really, because it leverages those cells and those binary encodings and everything I was just talking about. It is effectively immutable, it's append only, and it is content addressable. What that means is that here you could picture it as being a huge map, essentially, where when we store values, we store their binary encodings, and keys, well, keys are hashes of those binary encodings. What I have just described is known as a Merkle tree, a kind of tree where keys, are hashes of the values that it point to. Although here it's more of a graph, because remember that those binary encodings might themselves contain references, that is, hashes to other encodings in the database. And that kind of key value store / map is really convenient to use, because what you can do when you want to retrieve, once again, a very large value, you can just retrieve that top binary encoding and you're good to go, right? Then when you need to access one particular item, that might be a reference, then only you can fetch it from disk when you actually need it. And what you don't need can be garbage collected. What this whole scheme allows you to do, no pun intended, scheme. What this whole scheme allows you to do is to handle data that is way bigger than memory, right? Once again, just a quick example here of how we could create such a database, just even for local use. You would point to a file, then you would create any kind of cells that you want, and then you would simply use the write function on your cells, and that's it. They are persisted. And then when you want to retrieve them, you would use the read function and provide the hash of whatever stored cell you want to retrieve. So very convenient, but you would feel a bit naked if you wanted to design a networked database. What is missing is to do some sort of computation, to have some sort of way of executing code for transactions, like in any common networked database. And this is the primary goal behind the Convex virtual machine. It's an execution engine, Turing complete, and deterministic. Later we'll see that it's really important that the transactions that we issue are entirely reproducible. Like any kind of execution engine, we have a set of fundamental operations. We can create some constants, we have branching, we can define some stuff, invoke some functions. But of course, as a developer writing transactions and code, and later I'll be using the word smart contracts, you don't want to write all that into that kind of assembly, if you will. You want to have a higher level language. And what kind of language would be suited for manipulating Clojure-like data types? Let me introduce you to Convex Lisp. Convex Lisp is effectively almost a subset of Clojure, given some additional utilities and a couple of minor differences. And here is just an example. So let me stress the fact here that this is not Clojure, this is an example of Convex Lisp. And you can tell right away that it looks oddly familiar because, yeah, both are just so similar. Now I'll be coming back to this example a bit later. What I'm quite thrilled to say is that Convex Lisp is probably the very first decentralized Lisp in the history of computing. And I say probably because it has been mentioned before when it comes to distributed systems, but this particular flavor of Lisp has an actual on-chain compiler, something that you don't seem to find. So you have lambdas, you have eval, you have macros. If you remove any of that, like a Lisp without eval or a Lisp without macros, it would look a lot less like a Lisp, right? So probably when Lisp was mentioned, it was more about just syntax and S expressions, and this could be effectively the very first actual Lisp when it comes to decentralized systems. You would use that kind of execution engine to alter the state of the network, the state of this public database. But what is it, this state? Once again, you could picture this huge map where we have a whole bunch of stuff, and notably accounts. Let's focus on that because accounts are the medium through which we submit transactions. If we had an account, then you could run this transaction here, def hello reclosure. And if we inspect your account after that, then we can see this kind of map where we have a whole bunch of key values, and notably the environment, being this map where we can recognize our hello symbol pointing to this reclosure keyword. So effectively, accounts are a bit like a namespace that anyone can read, it's public, but you are, by default, the only one who can write anything to it. Accounts are, as I said, very important, and there are actually two flavors of those. There are user accounts, and those are operated by humans, and they are linked to a key pair. If we come back to this description here, we can see that yes, it has a public key, a 32-byte public key. So what happens is that when you create an account, you generate a key pair, you provide the public key to be stored on the network, and then of course you keep the private key for you. And so when you issue a transaction in code, then you sign it using your private key. Anyone like a peer can very easily verify it because your public key is on the network. And if it's the case that indeed you have signed it and submitted it and it has been verified, then your transaction can be executed. Then we have actors. Actors are fully automated. They have no keeper, meaning that no one can issue any kind of transactions on their behalf. But they are still accounts, so they have an environment, they can store some state, some values, and they become really useful when at initialization you define some functions for altering that environment. Because this will lead us quite naturally to smart contracts. Let me give you an example. Here is how we can create a new actor by using the deploy function. And you provide quoted code that is being called and executed when this account has been created and in the context of the new account. What will happen here is that it will define a symbol here, myState, and then a function setState taking a next argument and essentially rebinding myState to X. Just a function for altering the environment, but only if the caller of this function is account42. Believe it or not, as simple as this example might look, those are the building blocks that you find everywhere in any kind of smart contract, no matter how complex. You always have a notion of state and a notion of an interface that is here just plain old function describing how this state is being altered and who can do it. Let me show you an actual example that you have already seen. This bit of code for creating so-called NFTs, non-fungible tokens. They are a type of digital asset. We have an actor here that we import, and then we can call its create token function and provide this map. And this map, believe it or not, is effectively the NFT that we will mint. An NFT could be really any kind of data. In the end, it's just bytes. And if we have a look at what could be the state of this actor, at least a simplified overview, then it would be something like this, probably a map where we have some IDs pointing to those so-called NFTs or data, and we just assign a sense of ownership on top of that. We can see here that account 42 supposedly owns this NFT. But of course, it's not that simple. The whole idea here is that the actor itself allows you to do many, many things, especially when it comes to ownership. And like, for instance, you can decide who can transfer it, who can destroy it, who can modify it, right? So although the data can be quite simple, when you have that kind of guarantees provided by such a decentralized network in that kind of interface, then it can become a digital asset. Now, this was really important in the history of Convex. This library has been written by Mark Engelberg, by the way, who is also the author of Instaparse, and it has shown that you simply don't get that level of sophistications on other networks, because the level of abstractions that you get from Clojure-like constructs is really unmatched in expressiveness. And this is just the tip of the iceberg. I'll go very quickly about the last missing piece here, that is consensus. So what happens when you actually issue a transaction? Well, it gets received by a peer, and this peer sends it to like 10 other peers, and each of them will again send it to a whole bunch of other peers. So your transactions is being gossiped through the network, and very quickly the whole network becomes aware of it. Not only your transaction, but all other transactions being emitted concurrently all the time. And of course, it's a bit messy, all those transactions appearing all the time continuously. So because they are independent, they have no intrinsic order. So peers have to vote on an ordering and agree on one. So they do that kind of continuously until they have agreed on some order up to some point, and then they know that they can execute those transactions at least. And that was what I was referring to earlier when I was talking about being deterministic, is that if you and I have the same state and receive the same instructions and we execute them in the same order, then we have to reach the same result. Makes sense? Now, why would peer do that? Why would they do that kind of work? I mean, if we have a glimpse once again at our account from earlier, we can see this balance. This is a balance in Convex coins. Because when you issue a transaction, you do pay, so to say, some fees in Convex coins. That's native token. In other networks like Bitcoin, those tokens are, kind of numbers that you shuffle around. But here they have an intrinsic value because they are used to reward peers, and that's why the network is kind of self-sustaining. If you want to read more about it, then you can hit the website and find a white paper, and you'll find all you need to know about the convergent proof-of-stake algorithm and many, many other things. So to recap, if you want to build a decentralized application based on everything I've just said, there are two sides to it. First, there is what happens on the network. You have to write those smart contracts in Convex Lisp, deploy them on the network, and if you want to learn more about this, you can once again hit the website and have a look at the developer section. There you find everything you need to know about Convex Lisp. You'll find some examples, like this voting example here, and the kicker, in my opinion, the sandbox, where you can create an account on the network. It's completely free of charge because it's a test network, and you can issue some transactions. And it will provide you this rich, interactive, Reaper-like experience, the best way to learn about all that. And then you have what happens on the client side, we could say. You have to have some way to talk to the network to provide some user experience usually. And we've seen a bit of Clojure today, but we have a whole set of libraries that you can use for creating some cells, as we've seen, and many, many things. And notably, for talking to the network. You can connect to the current test alpha network and issue some transactions, like calling those smart contracts that you have written. All right, reaching the end of this presentation, I'd like to thank Mike Anderson. He's the founder and the director of the Convex Foundation, and he's the one who first imagined this really elegant design and first implemented. So he sure deserves our credit, because we can see in the end that it's quite straightforward to build decentralized application. And when you use the Clojure philosophy to see how it looks like and how it behaves and what you can do, then I hope that it makes a lot more sense to you. The Convex Foundation has been established so that the whole project remains open source. And what we do is that we try to make it self-sustaining, community-driven as much as possible. We try to reward people who actually contribute to it and make this dream come true, so to say. And yeah, sure, come and have some fun. You can help us build everything I was talking about today, improve the database, the execution engine, and all that. You can help us with writing some libraries, Clojure ones, Convex Lisp ones. There's certainly a lot of things to do when it comes to dev tooling. Try to prototype some stuff, either completely decentralized applications, or maybe try to decentralize one aspect, like maybe you have some voting mechanism. You could try to decentralize that one thing in your application. And in the end, it's all about the people, of course. So do join us. We want to spread those ideas. They are novel, both in the Clojure community and in the blockchain decentralized community. So yeah, come and have some fun. Thank you very much. It has been a pleasure. I can get really quite passionate about those topics. So let me leave you with this slide here where you can find us. We have a community Discord. Do come there if you have more questions about the project as a whole. If you're more interested about the Clojure integration, then we have this Convex channel on Clojurians, and of course, have a look at our repos. My name is Adam Hellins. It has been a genuine pleasure. And all I can do now is, I guess, just wish you an excellent conference. Thank you.
Thank you, Adam. That was indeed, Convex is indeed a very interesting system and topic. So here we are with the first panel of the day, of the second day. And this will be with Christophe, Baptiste, Adam, and Michael. So we're going to have both the speaker in the talk and their collaborators or otherwise. So we need to check first that we can connect with all of them. So I'll go with Christophe first. Are you ready? Can you hear us? Can you unmute yourself and see if everything is working?
I'm here.
Fantastic. Thank you, Christophe. So maybe I'll start while others are checking their connection and so on. We have this mystery about an Easter egg that you posted online, and it was posted also today in your background while you were doing the talk. And so I think somebody might have the solution to that. And I don't know if you want to give that away now or ask people to go on your picture and try to see if they can understand what it is. And then maybe we can ask to raise their hands and see if anyone wants to explain what it is. What do you think?
Okay, I'm going to show you rather.
Okay.
I have I'm twice in the Zoom, one with the computer and one with the phone. So
okay,
I'm going to walk to the meeting room.
Okay, which one is? Which one is the second Zoom?
How can I?
Oh yes, I saw it now. All right.
Okay.
I'll make you co-host so you can share from the phone if you want now. Or just enable the phone.
Yeah, what should I do?
Just open the camera.
The camera is open, I believe.
And then I'll spotlight your camera for everyone. So now you're live from the phone. Yes.
Okay. It's cool. So to the meeting room. And here.
Oh, what happened?
Why is there no? Okay. So that's right.
Ah,
That was
okay.
the Easter egg.
So I saw those things, but I wasn't able to understand what they were on the desk, on the shelf. Okay, so good for whoever like managed to understand what was the Easter egg. So now we know it was like the big dart. Let's see, the big dart box with the dart in it, like the dart board in it, and I didn't understand that was it. Pavel, you got
Can
that,
I
right?
ask? Yeah, can I ask you, because I thought there's actually 2 Easter eggs. Maybe that was by accident, and great minds think alike, that kind of thing. But I saw the darts on the table, so I thought that was the one Easter egg. The other thing was that the books that you had on the bookshelf were really familiar, right? And I think all of those books were, well, most of those books, at least on the shelves on the sides, were listed on Rich Hickey's bookshelf, right? Like Rich Hickey posted at some point his, whatever readings that inspired Clojure, and I think all of those books on the side bookshelves were. Was that intentional or by accident, or just like the same books, or what happened there? Christoph, you're muted now. We can't really hear. Okay.
For foundation of databases, it definitely comes from Rich Hickey bookshelf, but the other is an accident.
That is uncanny. Great minds think alike, I guess. That's the answer.
Okay, let's check Baptiste. Baptiste, can you see if you can connect?
Yeah, do you hear me?
Yeah, all good, thank you. So I'll leave it now to John to see if the other guests are available.
Thank you, Renzo. So let's see if Adam is online. I can see he's got his
Hi,
camera.
yes.
Hey, there we go. How are you doing?
I'm quite all right, thanks.
That was an excellent talk. That's an impressive microphone. I thought mine was good, but yours is even better.
Oh, it just looks,
So question to you is there anything curious or interesting you'd like to share about your surroundings, about what's going on at the moment?
In my surroundings, well, it's a bit of a peculiarity, but usually on my desk, I always have a deck of cards, you see.
Nice.
And it's a bit weird, I know, but the thing is, when I was quite a bit younger, I used to do a lot of magic tricks, and so I don't have much time for that these days, but I usually always have a deck of cards so that when I have to do some readings or long session and all that, it keeps my hands kind of busy and it can help me concentrate. So a bit of a fun thing to say, I guess.
Excellent. I suppose it's good for keeping the dexterity in your fingers and stopping RSI and things like that as well. So great stuff.
Mm-hmm.
Do we have Michael as well?
Yes, indeed. Can you hear me?
We can indeed. Yes, loud and clear. Thank you. And yourself, have you got anything you'd like to share briefly? You've got a very nice seat you're sitting on by the looks of things.
Yeah, this is Secret Lab Chair. So I'm supporting. So I live in Singapore. I'm supporting a local company, Secret Labs, that makes excellent gaming chairs. So I can put in a sponsorship plug for them if anyone wants a gaming chair. Secret Labs is the one to go to.
Excellent. Thank you very much. Renzo, do you want to ask the first question?
Yeah, let's go with the first question. We want to know, first of all, if that bookshelf was Christophe or Baptiste's, but I think we saw that live and we know that now is Christophe bookshelf. So another question is that it maybe is not that obvious. I think it was displayed on the slides. What is the meaning of that dot ampersand in Clojure Dart?
Okay, so the dot. You want to go, Baptiste, or
No, keep going.
Okay, so the dot ampersand is mostly on its way out, but in Clojure Dart, in Dart, you can have named parameters to a function. So the trick when we started designing Clojure Dart was to find a way to tell Clojure that from this point on, these are named parameters that you have to pass to this Dart function or method. So the dot ampersand was used as a delimiter to instruct the compiler that it was an interop form with named parameters. But we had to resort to this solution because at the start of the project, we made all variables dynamics. And by making them all dynamics, we got to produce code quickly, but it wasn't efficient, and we had other problems down the road. Now that we have proper type inference on all methods, we know when a method is going to have name parameters, so we don't need them anymore. We are just phasing them out at the moment.
So
Right,
basically,
John.
it's just a syntax to use the name parameters right now.
Okay, thank you for the clarification. John, do you want to take a question for Adam or Michael?
I'm sorry, I can't hear anything.
Yeah.
Oh, sorry, I was on mute. Yeah. So, the question, I guess, for Adam is like, what do you see as the overall vision for Cortex World? What do you expect that will enable and grow into? Like, is it comparable to things like Ethereum and so on? Is that like a very different kind of tangent on what you're trying to do?
Oh, sure, you could very much compare it to Ethereum, but because we have this ability to build complex data models, and it's also much faster, at least in our current benchmarks, you can go much farther, right? I think that this kind of tech has the same kind of effect on blockchain that Clojure had on Java or on the JVM, you could say, right? The JVM by itself as a way of just having a virtual machine, and it's very capable, right? But you want to have something that is more sophisticated and allows you to handle more complex data, and you can go very far. I think that Mike has many examples he'd like to give you, I guess.
Okay, thank you.
Yeah, well, certainly. I mean,
Mike?
I think the vision of Convex is definitely that it can be a building block for people who want to build the sort of next generation of decentralized applications. And I think some of the things that I find particularly important is I was horrified by the energy inefficiency of things like Bitcoin and Ethereum. It's just ecologically unsound. And one of the motivations for me, certainly, in contributing to Convex was building something that was super energy efficient, super fast, and it has a sort of low latency, which makes it usable for things like gaming or consumer mobile applications, web applications, these kind of things, which are currently impractical with a lot of current blockchain technology. So my hope certainly is it becomes a valuable tool as a building block for people who are wanting to build these decentralized applications in the future.
And can you say a little bit more about the energy efficiency? Is that due to Clojure, or is it just kind of like your design or the infrastructure?
I think there's two things. One, the JVM is actually a pretty good execution engine, and we all know from Clojure that the JVM gives a very solid foundation on what to build, a very good performance, and obviously JIT compiler and stuff like that. The garbage collection turns out to be really useful for decentralized apps where you've got these big immutable data structures with structural sharing, and sometimes you have to discard large chunks of it. The GC is very valuable. But I'd say the main reason that it's efficient is that Convex, in the design of Convex, we found a way for the peers, the decentralized peers, to agree on an ordering of transactions without burning energy. Yeah, you don't have to spend a bunch of time or compute or storage in order to reach that consensus on the ordering. And that's kind of the key innovation. Yeah, it's how do you make the ordering of transactions stable, consistent, and consensus without spending any electricity or other computing resources to work that out, or at least minimal. So in a local test network, you can literally pump millions of transactions through Convex per second. It's incredibly efficient with virtually no.
And regarding resources, if I may add, there are a couple other innovations I didn't talk about today because it was kind of more advanced. But for instance, there is a kind of a memory allowance, right? Because on networks like Ethereum, when you store data, you pay fees just once, and that's it. Then the peers have to store it forever, which is kind of unlogical if you think about it, right? Where there are here, what you have is the fact that you have some amount of memory that you can use. And then if you lack some, then you can automatically buy some for Convex coins during a transaction. I mean, it's completely automatic, right? And if you release some memory because you undef some data, for instance, then you could sell it back, for instance, right? So you have that kind of mechanisms that have been embedded in the network so that you have some incentive to keep things clean. And so there is also this category of innovation that prevents things like wastage, essentially.
Excellent. There's obviously a lot of thought has been gone into that aspect. I'm very happy to see that. Thank you very much. Lorenzo.
So while remembering to our audience, if they wish to interact live with the speakers and ask a question live, they're more than welcome to raise their hands on the Zoom, and we'll get them straight at the top. Having said that, we have another question for Christophe and Baptiste from Ben Sless, who is the next speaker, by the way. How much of these conclusions and techniques could be applied to Clojure's compiler? Anything from inferring nils for tests to Project Valhalla, which should allow the JVM to get past type erasure?
So I try to answer on the Discord, but I'm not sure it would be possible to use our type inference as it is plugged in the compiler. And to be honest, I don't understand the goal of Project Valhalla. So maybe Christophe, do you have inputs on this project? No. So basically, type inference will be stuck to Clojure Dart.
Okay, Christophe, are you with us?
Yes, I'm here. Yeah, I'm not familiar with Project Valhalla, but for the type inference itself, it's really tied to Clojure, to Dart itself. It tries to mimic and simulate the own Dart type system so as to be able to please the compiler, because otherwise the Dart compiler is pretty harsh. There are even some cases which I consider borderline as bugs. For example, I remember with nil labels, you have an operator dot question mark which allows to. No, it wasn't even with a proper special operator. We had one line which was checking a value against null, and if it was null, it was throwing an exception. And then, because the code generation wasn't quite good, further down the line, there was the same test anew, and that compiler was complaining because once it passed the first if, which would throw if the value was null, he was complaining that we were testing a non-null value against null. So the type inference is really there to be able to be as smart as the Dart compiler. Otherwise, we get weird errors and so on.
So yeah,
And
it
it's
seems
really
to
not
be it seems to be premature to like think that there is anything we can like introduce into the Clojure compiler in this kind of sense. That was the original question. That's why I'm asking.
Yeah.
Okay.
So yeah, just maybe Neil and some could be helpful, but I believe there are already some handling of that in Clojure.
Thank you, Christophe. John, any other question for?
Yes. So there is a question from the Discord channel. Could you please explain the consensus procedure used in Convex in regards to POW and POS? How does it differ? How does reaching consensus work?
Oh, that's a very complex question, because this is the hardest part of the whole stack, I think, and it has to it mixes with a bit of economics and game theory. But so proof of stake is a class of algorithms. So convergent proof of stake, which is what Mike has designed in the first place, isn't the very first one ever, but it has been in the workings for like 3 or 4 years, I think, Mike, it was.
But yeah, about 3 years.
Yeah. So could you tell us how is it exactly different from usual proof of stakes algorithms?
So, I mean, I think Adam's exactly right. Proof of stake is a class of systems where consensus is agreed by a stake, so some kind of weight. And Convex does use stakes, and it's a type of proof of stake and algorithm. I think the most important difference with Convex and potentially other decentralized networks is Convex consensus is actually implemented as a CRDT. So it's a conflict-free replicated data type. And these are data types that have this beautiful property that you can merge 2 instances together and get a new instance. And if you happen to do that in a repeated fashion, e.g. by gossiping the values around the network, then as long as the merge function has the right mathematical properties, and there's some lovely mathematical papers if anyone wants to dive into this, you can actually prove that it will eventually converge to a stable state. And that's what you want for consensus. You want this convergence to a stable state, which then forms the basis of your agreement around the ordering of all the transactions, which is then how you compute the updates to the global state. Now, can't go into too much detail here on how that merge function works. We basically found a merge function that enables you to implement proof of stake as a CRDT. Yeah, so that the merge function takes into account the stakes of the different peers, and the merging happens in a way that is consistent with the votes of the peers in the network. So it's all in the white paper if people want to dive into more depth, but hopefully that's given sort of a brief overview. The key idea is a conflict-free replicated data type, therefore it's guaranteed to converge under certain conditions.
And 2 things that are apparent from this is that, so in blockchain, the word blockchain, you have the word blocks, of course, because what you end up with usually at the end is a chain of blocks that are indeed cryptographically linked, right? But here it's a bit different. So transactions are being grouped in so-called blocks. This is what peers emit to other peers, groups, blocks of transactions. But there is effectively no leader. So any peer can emit a block of transaction at any moment, right? Whereas in even other flavors of proof of stake, you tend to have quite often a notion of a leader, so that only one peer at one given time can broadcast a block of transactions. So that's one of the reasons also why Convex is so fast, even on the network level, we could say. And having that kind of CRDT also means that those blocks are not cryptographically linked. So peers vote on an ordering, so there is a sequence of blocks at some point, but it's a bit different from the usual blockchain in that aspect, right? Technically, we could say that it's already something a bit different from a typical blockchain.
Okay, thank you. That was really useful explanation. And yes, I'm kind of looking forward to having a look at the white paper that's on the website as well. That should dive into a lot more detail, I expect. Cool. Okay, thank you for that. Renzo, have you got any more questions for that side?
Yeah, we can go for one more question for sure. And yeah, remember to raise your hand for live interaction. This is for Christopher Baptiste from Jakub. I gather there is some impedance mismatch between Clojure and Dart due to the types, nil handling and such. It seems you have made great progress, but do you think you will get to a point when writing Flutter apps in Clojure script will be painless without running into the mismatch? Or will there remain some corner cases where the interop will remain painful?
So I'm going to start. I'm writing a Clojure Dart application, iOS application right now, and I found the experience awesome. But there are still, like Jacob said, we are not still at the level of interaction greatness like Clojure and Clojure Script. To be honest, I really don't know if we can achieve that, but I don't think types will be necessarily an interrupt will be necessarily the main pain. We really have to find out how we could have a better REPL and out-reload experience. Actually, we don't have a REPL right now, but we tried the design and it's working. But yeah, what's your opinion, Christophe? Sorry, mute. Yeah, on the impedance mismatch between Clojure and Dart, I think we have got it mostly under control now. There are some things which are going to be addressed by what we call the magic cast, which are wrappers which are automatically inserted by the Clojure compiler to make sure that we transform the input into a wrapper of the suitable type for Dart. But yeah, just from the relationship between the two languages, I think we don't have much to fix yet. One thing that's worth mentioning is that we never designed Clojure Dart code to be callable from Dart code. The intent has never been to be able to create libs to be used by regular Dart code. That said, to add to what Baptiste just said, well, we don't have a REPL yet, but we have made a proof of concept very early in the development, and the focus currently is on the batch compiler, which we can then couple with the auto-reloading feature of Dart to produce the same developer experience as the one that Dart developer are used to, or even some people in the Clojure community which work with auto-reload. That being said, writing a mobile application sucks. It's hard. No, it's true. You have to. You really have to comply with iOS rules, and even if you're using Flutter or React Native, you will still have to struggle to compile your application, let's say, or to package assets. It's not like writing a web app or a pure Java Clojure application. You have many rules.
Okay, thank you. We have probably another question from John's side.
Oh, yes, I just unmute myself. There we go. Yeah, we've got a couple of questions. One's actually a follow-up from the last question. So just querying if there's any trade-offs in the Convex approach compared to traditional POS networks. Is that something that's in the white paper, or is there something you can say about that?
I think it's probably a very, very long topic, so hard to answer. I think we have the best approach to POS in the sense that the CRDT seems to be a perfect fit for decentralized systems, and then we use POS. Now, there are obviously challenges with POS. Yeah, I mean, it does require people to put stake on nodes or stake on other people's nodes, and there isn't yet a long history of POS networks and how they behave from an economic perspective. So I think that's still a bit of an open question. It's one of the reasons we're taking a lot of time to get this right, and also to make sure that the economics are viable and sustainable in the long term. But I'd say there's still a bit of an open question around what is the best way to make proof of stake work. I think yeah, I don't think there's too many trade-offs. I think we've genuinely eliminated some bottlenecks and some pain points in some of the traditional blockchain approaches. I don't think we've given up too much, but you know, people can argue this all day because there's a lot of complexity and a lot of different aspects that are relevant. So
sure,
happy to debate further on the Convex channel or something if someone really wants to get into the details.
Yeah, that sounds good. Yeah, on the Discord channel there, asking a couple of questions about that. And just one final question. There's a query about adoption. I guess the question is really aiming at, like, what does Convex need anything to be successful? It's like move from this cool product into actually being widely adopted in production, or is it just a matter of people using it?
Well, yes, two things I'd like to say here is that that kind of open source, community project, whatever we call it, it can show some limits where we have to actually hit actual production. So we have released an alpha version. It was in September, I think, so not that long ago. We are slowly but surely going for beta. But the problem is that when you want to actually launch a mainnet, as it's called, then it's best usually to have some kind of audit, for instance, from a third-party company who will try to break it and ensure that everything just works perfectly, that security-wise things are just smooth. And unfortunately, that kind of steps require a lot of funding, right? And it's a bit hard. I'm going to be honest, it's a bit hard to found that kind of project because it's a bit too abstract. So if you know Clojure and Lisp and all that, then and a bit of blockchain, then you can realize the value of a network like Convex. But if you have never heard about Lisp or anything like that, then it looks just very, very abstract, right? So we have a bit of a Lisp curse going on here. That's the first thing I could say here. And the second one would be about just having a strong community. So that's why we like talking to developers who aren't really into blockchain, because first of all, that's the vast majority of developers today. Only a tiny fractions of developers actually work in blockchain or decentralized tech, because we like to expose that kind of ideas more and more and show that it's interesting for other use cases than just NFTs and cryptocurrencies. And so, yeah, we would like to see more people like that coming in and building a stronger community and have something going on there, a bit more impressive. Mm-hmm.
Excellent. Thank you very much. Well, hopefully people watching this live and in the future will be interested and take up that call to join your community as well. Thank you.
I wanted to just add for Christophe and Baptiste that I saw your TensorGritics Clojure Dart repo. So you mentioned that is something is might appear there in Q1 of 2022. So I wanted just to close asking you where people can go to help you out or follow your work in general.
Twitter. Just follow Christophe and me, and you will have the last news about the project.
Okay. Or create PRs on the empty repo.
Yes, I'll simply watch the MT report.
Okay, well, looking forward to the evolutions of that. And yeah, I'd like to thank Christophe, Baptiste, Adam, and Michael for being with us today, answering questions. Your effort in putting together the talk, very appreciated, very interesting projects. Thank you very much. So we'll take now a longer break before the next block. Enjoy the visual art as usual. Grab some lunch if that's the kind of time in your time zone, or grab a tea. In any case, relax and enjoy the rest of the conference. We'll see you soon. Thank you.
Let's
Hello and welcome back, everybody. I hope you enjoyed that little break. We're going straight into the next talk. Well, actually, the next couple of talks are actually about performance and different aspects of performance as well. So this is going to be really interesting. First up, we've got Ben, who will show us how to start maximizing performance on the critical path of your Clojure code. Ben develops large-scale event-driven back-end systems at AppsFlyer, and naturally has developed a deep interest in performance and profiling. Ben also created the open source performance testing tool, CLJ Fast, and has contributed to performance enhancements to open source projects such as Mali and Reatit. Over to you, Ben.
Hello, everyone. My name is Ben Sless, and this is Dressed Up Performance with Clojure. A bit about me. I'm a backend engineer at AppsFlyer. I'm working on large-scale systems which ingest billions of events every day. And I love Clojure. Most of our backend is written in Clojure, and you might ask yourself, can Clojure remain viable in such a large scale? Spoilers for this question, yes, but you need to change your mindset a bit and to adopt some behaviors and practices which will help you to solve performance-oriented problems. Every discussion about performance should have a bit of a meta discussion about performance, and starting with Donald Knuth's immortal words, premature optimization is the root of all evil, which we should put in context. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. What is our critical 3%? That is our infrastructure. Those are our libraries and our frameworks. And you are a developer. You want to provide a good API for your users. You want to provide readable code for developers, both yourself and colleagues. And you're working on a library or a framework, and you want it to be good, and you want to not only provide a good API, but you also want to provide a performant API. And this talk I consider a spiritual successor to the Naked Performance talk by Tommy in Clojure Trade 2 years ago, and in it he provides three big ideas he lays out. One of them is little things, and those are the little things which accumulate, and on your hot path they have a significant effect on your performance because they accumulate. The other big idea is data and compilers, and the other is algorithm. I'm going to be focusing mostly on the first one, but we will see later how it connects to the second two. And after this talk, I wanted to do some tinkering because that was a very interesting idea, and in it Tommy mentioned, for example, that getting in a map and an enrolled implementation of get-in have significant performance differences, and boy, what a difference. 5 times faster is a dramatic improvement, and that's nothing to sneeze at. There's certainly something there, but we need some new methodologies, some new approaches to even understand how to take advantage of it and how to squeeze the most out of Clojure here. And we need to get into the right mindset to solve those performance problems. But where is your problem? Most likely it's not in Clojure, right? I'm going to assume that your problems are first in your architecture. Maybe you're blocking, maybe you're calling multiple services and waiting for responses. Maybe just your algorithm is not correct, or you're not using the correct data structures. And that's all I have to say about that, because this is not what the talk is about. To solve the low-level performance problems, you need to embrace some things. You need to embrace your runtime, which means you need to embrace the JVM first. You need to understand that JVM is a bytecode interpreter with a just-in-time compiler. The just-in-time compiler can turn that bytecode even down to assembly. And to do that, it needs to see predictable behavior. And what does predictable mean for the JVM? The JVM just-in-time compiler optimizes hotspots. Hotspots are places in your code which you hit frequently. And for example, it can inline small methods. And predictable things are things like monomorphism or branch prediction. What is monomorphism? When you dispatch through an interface to a single implementation, that call site is monomorphic. Branch prediction, if there's an if statement, but you always take the first branch, this is quite predictable. Unpredictable is the exact opposite. code which is very polymorphic. From a single interface you dispatch to a variety of implementations. Allocation is unpredictable for a variety of reasons we'll talk about later, and some negated assumptions, things like array bounds checking or branch prediction. If we can't know how they will behave, we can't optimize them away. Another thing we need to embrace and understand is the hardware. Modern CPUs like contiguous things. What is contiguous? Arrays are contiguous. Things that fit in cache. And Clojure's data structures actually take advantage of it. You can see that they're implemented as with very wide backing arrays, and they are in a width which actually fits to cache loads. The opposite of that would be cache misses. Now, what causes cache misses? Loading stuff from main memory. And when do we need to do that? Memory is loaded in pages, and if the object you are loading is not in the page, you need to go to another page. You need to evict the current cache. A linked list would cause you to do that. You always point to the next node in the list, and you will have to go find it. It may not be in your cache, most likely not. Every new object you allocate is allocated on the heap, and you need to load it. Another thing you need to embrace is Clojure. That might sound ridiculous to you. This is a Clojure convention. This is a Clojure talk. Of course I embrace Clojure. But you need to roll up your sleeves and get right in there. You need to understand the APIs. You need to understand the implementation. You need to not be afraid to read Clojure code or the Java code. You need to understand why some APIs are fast and some are slow. You need to understand when and why allocations happen. And once you do all of that, it's time to profile. Always profile first, and not just profile. Profile living applications. You don't want to test your applications in a synthetic environment. And you have a variety of profiling tools. You have Visual VM and the Java Flight Recorder, very useful. They can give you lots of information. But I'm going to be focusing a bit on flame graphs today. Now, what are flame graphs? A flame graph is a visual representation of % of time you spend of your CPU doing stuff, and on the horizontal axis and in the vertical axis you have a visual representation of your call stack. If F calls G1 and G2, G1 and G2 are stacked on top of F. G1 calls H, H is stacked on top of G1, and we cannot spend more time in G1 and G2 than we spend in F. That wouldn't make sense. Then you can see that their stacks together are slightly smaller than F, same for H. This is a real flame graph. I produced it from stress testing HTTP kit with some code with Rated and JSONista and the entire Metazin web tech stack, let's say. And each one of those stacks, each one of the vertical stacks, we can see is laid down on top of a white block, which is a function entry point. And we can look at them and ask, what's taking so much CPU? Because each one of those stacks is 10 to 13, 15% of our CPU. What's going on there? Where's my CPU behind stack number 1? Keywordized keys. Stack number 2. Parsing the query params in the request. Stack number 3. Building the request map inside HTTP kit. All of those things have been turned into actionable conclusions, pull requests to the respective repositories which produced performance improvements. Once you find out the pain points you want to fix, you can start benchmarking. And your workhorse for benchmarking is Criterium. Like we saw previously, you can use it a lot during the exploration phase. You can try a variety of implementations and to try to compare them and understand why there are so many differences between different implementations. I used it for my pull requests. You can test it for a variety of inputs and see how the results changed based on the different input. And we can see here, for example, a rough 2.5 to 3 times improvement. Another tool is CLJ Async Profiler. Let's profile the cases we've seen previously. When we get in, we can see that we pass through a function called reduce1, and it iterates over the sequence of keys. And we need to understand what's reduce1, why is it slow? If we unroll it, we see that when we go through a series of gets, we only pass through Clojure runtime get before we hit the val.at method. If we dispatch through keywords, we can see how we go through the keyword method before we go to val.at implemented by the map. And if we invoke the map on the keyword, we see there's almost no indirection. What's going on here? We'll see it in a bit later. CLJ Async Profiler, very useful tool. You can use it interactively, you can embed it in your application, but read the documentation. Make sure you set it up correctly and of course understand the results, understand how to read a flame graph. Setting it up correctly, it's all in the documentation, but it mainly involves setting the JVM flags correctly and making sure the kernel will let you see profiling events. Another tool very useful is JMH Clojure. For when you need the most accurate results, this is your go-to tool. You can set up elaborate scenarios, elaborate test matrices, but it requires some learning. If you need the most accurate results, this is your go-to tool. It's important to construct good test cases. Make sure you don't test your code in isolation. If you do, make sure your test cases are not synthetic. You need to understand how the JVM optimizes code. And when you understand that, when you understand how the JIT behaves, you know that you need to make sure that your function doesn't see just one type, that it doesn't just see one type of collection, one type of input argument. Those things matter. Make sure that in a single test case, the same function might see a variety of inputs, which would affect how the just-in-time compiler behaves. Some of my findings. This gets into the territory of things you can apply, not just tools, but conclusions. The big little things, they have a performance overhead which stretches from bad to terrible. Terrible, for example, is satisfies. The rest are mostly bad. Now, you might say, well, merge, that's just 200 nanoseconds. Why should I care about that? When your performance budget is under 600 nanoseconds, 200 nanoseconds make a huge difference. These matter on your hot path, not when you're loading a config file. And there are some fast little things. Mostly reduce KV and transduce, which goes through reduce. And they are fast because, like I said previously, vectors and maps are backed by arrays, and reduce KV iterate directly on those arrays. That is very friendly when it comes to cache behavior. And plenty of my findings are taken from CLJ Fast, which is a library I maintain and develop. And it implements a lot of those things heuristically, and I'll talk a bit about that later too. One of them is that the JIT makes a huge difference. Array clone versus array's copy of 3 times faster without JIT. JIT should be turned on, and it is on by default. Just ensure that. Another thing is the cost of iteration. Compared here is the throughput for get-in versus the inline version of get-in, and we can see that it is about 2 to 3 times faster. Here you can see the throughput change in percentages. We can also see the same for assoc, for example, which can take a variadic number of arguments. And here we can see the relative speed up 50 to 60%. And we can also see a similar behavior for select keys, which is even more dramatic. We can get 3 to 4 times speed ups. Another thing to understand, and which I found, is that indirection has a cost and it is measurable. Why is invoking a map faster than calling get? 2 reasons. One is that when we call Clojure RT get, we pass through an if, cast, reflect, and only then we dispatch to val.at. Alternatively, when we invoke a map, we dispatch to val.at directly. What's important to understand here is that RT get might see a variety of types, not necessarily iLookup, which would make the if statement, for example, not be inlined, or just elided because it cannot be predicted, and then the call to val.at won't be inlined. On the other hand, when we dispatch via invoking a map, we dispatch to the direct implementation directly. There is no indirection and no code that can't be optimized for a variety of reasons. And we can apply this knowledge then to write a small macro which takes the input argument and applies it to the second argument. Then, when we eliminate the indirection, we get more speed, and now we understand the results that we can see in the flame graph. We, from invoke, call directly to val_at with no indirection and no overhead. Another thing is the cost of allocation and iteration. Take equals, for example, when it gets more than two arguments, it iterates over them. Now, both the rest function allocates a sequence, then that sequence has to be loaded into memory, and then when you call next, you allocate a new object. So you both churn allocation, and you always have to load that into cache. Now, the JVM is garbage collected. It can handle that pretty well, but not optimally. And that's what's important to understand here. What can you do then? What you can do is ABC, always be compiling. And what does that mean? It means that you need to do what you can at compile time, and to turn yourself into a little human compiler. And what does a compiler do for you? It does loop unrolling, it does type specialization, it does partial application. And we will see now how you can do some of those things. For example, how can we enroll loops? Multiple arities. Let's take a source, for example. It takes a key and a value, and it might take a sequence of keys and values, then iterate over it. However, we can provide it with multiple arities for 1 pair, 2 pairs, 3 pairs, which will then unroll the implementation. Then we dispatch, actually, to the correct implementation instead of iteration. That can also be done via a macro. Same thing, we take the sequence of keys and values and we unroll that into a sequence of associates. Same with getIn. We take a sequence of keys and we unroll that to a sequence of gets of the keys. We can define everything static. For example, if we have a function which maps a composition of two functions, we can define that composition. This has two advantages. One is that we don't allocate a new object every time we call comp, and the second is that that object can be optimized too every time we hit foo, instead of maybe optimizing it a bit and then throwing it away. It can be optimized many more times because we hit its method, invoke method, plenty of more times. Another aspect of ABCs is to always be closing. And what's important to understand here is that at the JVM, compile time is all the time. We close over everything else. Let's take getIn, for example. We don't know the number of keys until we get them. When we do get them, we can count them, and then we can take them apart and unroll the call to get. But what if we know the keys before we know the map? Then we only take the key and take the map later. We return a function that will take the map and already return the unrolled behavior. We close over the unrolled behavior inside the function we returned. Where can we use that? Here's an example from a library called O'Doyle Rules. We can see it calls getIn on an unknown sequence. It calls updateIn on unknown sequences. AssociateIn on a known sequence. So those are cases, both where we know and don't know, where we can unroll those functions. And this is the bread and butter of what the library does. If we can speed that up, the library will be faster. And another example of closing over everything when we know it, an example is double dispatch. Double dispatch, multi-methods, right? They take a dispatch function, they dispatch to the implementation via dispatch table, then apply it. We take an argument, apply dispatch function, get dispatch value. Get the function associated to that dispatch value and apply that. Starting from the end, we start from the unrolled implementation. First key, first function, otherwise second key, second function, etc., etc. Once we have the fully unrolled implementation, we need sort of current rest implementation, the current key and the rest of the behavior. Here we have a representation of that. Is the dispatch value equal to the current key? If so, call the current function. Otherwise, call a function representing the rest of the behavior, which is currently unspecified. Then, take everything we don't know and turn it into an argument to the function. And let's assume we don't know anything. We don't know the dispatch value, argument, rest function, current function, or current key. Then, we actually do know the dispatch table in advance. So, we can bind those arguments first. And the keen-eyed among you might recognize that this function can be passed to reduce KV. We can reduce over the dispatch table and compose a function which will implement the unrolled behavior. And that is how we unroll a dispatch table. Now, there's another thing here which we can eliminate is indirection. The equals function is highly polymorphic and it reflects on the type of its arguments to dispatch to the correct implementation, but we already know K's type. So let's assume there is a function which will take the key and returns an optimized function which will check if the value is equal to key. We can just dispatch via the type. If it's a string, dispatch to equals, and voila, we have closed over that as well. Now, this is not a high-in-the-sky principle. It is used right now inside Clojure itself. This is the transducer implementation of map. What does it do? It closes the known things when they are known. You map over a function, you later take the reducing function, and only then you get a function that you apply to the sequence of inputs and accumulate a result. And you can carry those closed over values around. If you're familiar with the concept of operators fusion from reactive streams, it's exactly the same. And this principle, writ large, is the idea of data and compilers. You can create data DSLs and use them to emit very complicated and involved hierarchies of classes or functions which implement the desired behaviors. Libraries like Mali and Rated do just that. But if you think about it, what is a sequence of keys passed to get in, if not a sequence of instructions how to get? So those things, those ideas actually converge. Just those are more ad hoc and specialized implementations for the same idea. And that's how you turn yourself into a human compiler. And when you do those things, you make things much easier for the JIT compiler and the CPU. Your type specialization makes call sites less polymorphic. Composed functions are nested classes and the JIT compiler can inline them. When you go through reduce or other implementations which dispatch on the arrays, you make the CPU itself happier. And that leaves us facing towards the future. What can we do in the future? In the future, we can hope for stronger inlining support to be added, for example, to Clojure's core. Currently, we have the inline arities metadata, but we could perhaps have an inline predicate which checks the arguments themselves and let us examine them. And we can see if they are something we can unroll. We can have multipass compilation that will do all the things I've shown you heuristically. It will do them for us, and we won't have to do that manually. And we can also have some more specialized code paths. For example, in the implementation of equals, you can look at it. It's quite interesting, but it is not the most optimal code path at the moment. Thank you all. My name was Ben. This is my Twitter handle. You can find me on Twitter or on the Clojurian Slack. Good luck, enjoy the convention, and happy hacking.
Well, thank you, Ben. That was inspiring and very insightful. I've used time and criterion occasionally myself, but I guess it's not often I've used as much of these tools and techniques to do performance, but I am certainly inspired to do a lot more now on my projects. Okay, before we start the next talk, just a reminder that you can already start asking questions in the Discord channel, which is QA Ben's / Leo Noel, or you can ask them in the Zoom chat as well. We're continually monitoring for your questions, so feel free to ask them as you think of them. And also, we're getting a lot of interesting lightning talks there, and we're also still looking for more if you have them. So in the Discord channel, there's a lightning talk channel, and you can either post your ideas in there, or you can actually just go and vote on other people's ideas as well, just thumbs up or claps, and then we know that they're of interest. And if you're of the persuasion of using Twitter, then please share the talks and ideas that you're seeing as you're seeing them as well. That'd be great to get other people excited about what we've been doing. And you can use the hashtag Reclojure or @Reclojure again to help us amplify the messages that we're sending out. And also just a reminder that there is a third day to this conference on the Sunday. If you've still got some energy and if you've got a lot of interest in data science, then it's definitely worth going along to that. There's details on the reclojure.org website. So while you're digesting that, we're going to have another short little interlude. Oh, that's nice. So, welcome back, and we now have another fascinating talk on performance, improving the performance of your code by applying functional programming to create effective supervision trees, something that Rich Hickey described as situated programs. So Leo is an independent software researcher and a consultant focusing on functional programming, especially those techniques applied to IO-intensive applications and user interfaces. Leo's also created Missionary, a functional effect and streaming system for Clojure and ClojureScript, and is currently working at Hyperfiddle on a next-generation UI architecture. Over to you, Leo.
Functional effects and streaming systems in Clojure. I'm going to explain what functional effect systems are about. We're going to implement one from scratch. Then I'm going to explain why it matters. I'm going to talk about processes, supervision trees, streams, signals. And then I'm going to present Missionary, which is a Clojure implementation of these concepts. I'm going to show what makes it unique and how to use it to solve actual problems. This is the problem space. We want to make reactive programs. Reactive programs maintain a continuous interaction with their environment at a speed which is determined by the environment, not by the program itself. So we're going to have to deal with the imperfection of the real world. And we want to stay in sync with it, and we want the computations to be triggered by events from the outside. So this is very close to what Rich used to call situated programs. And this is what he was saying 8 years ago about usage of functional programming in this context. We actually need a program that's more like a machine, and we're trying to use tools that are for functional programming to do that, and it's a bad fit. So that's exactly what we're going to do. We're going to use functional programming to make situated programs. I'm going to show you that Rich is wrong about it. Functional programming is actually a very good fit for situated programs. And we're going to see why. So what is a functional effect system? We're going to start with an example. So we have a service, a remote service. So it implements a REST API and it provides information about products. So we can give it an ID and it will return information about the product. This is the imperative way. So we write a function. The function takes the product ID and then we construct the request and we call the service. We wait for the result and we return the result. So to get information about a product, we just call the function with the product ID. And at some point, we get the product information. So it's an impure function. It's impure because it performs effect, and that's imperative programming. This is the functional version. So we made two changes here. First, we removed the bang, and then we added this character, and now it's a pure function. So when we call this function, we have referential transparency. So what do we get when we call the function? So we get an effect, and an effect is a description of something to be done. That's the essence of functional programming. Instead of doing, we describe. So in this case, we represent the effect as a function. It's a zero-argument function, it's a sunc, and functions are immutable values. So we can do transformations over effect. And you can use pure function to transform effects. So let's define operators. Pure and bind. This is the bread and butter of Haskell programmers. Pure takes an arbitrary value, turns that into an effect. So it returns the effect that always terminates with this value. Bind is about sequential composition. So we want to do something and then do something else. So it takes an effect in a function. The function is called the continuation, and we're going to construct an effect. The effect will first run the input effect. We get the result, we pass the result to the function. The function computes the next effect, we run that effect, and the result of that effect becomes the result of the bind. Here is an example. So now we want to call two services one after the other. So we have a product service and a supplier service, and we want to get extended information about the product. So we're going to call the product service, and we're going to use bind, and we're going to pass a continuation that will extract the supplier ID from the result. We're going to construct the effect to get the supplier information, and we're going to use bind again, and the continuation will return a pure operation. Pure means there's no more work to be done. We can compute the result. And in this case, we want to merge all the results together to construct the extending information about the product. This is another operator, par. Now we want to do things concurrently. So we take an arbitrary number of effects, and we want to construct the effect that will run all of these effects simultaneously and complete with complete when all of them terminates with the vector of results. This is an IO implementation. It's not a good implementation. We're going to see why later, but it's good enough for now. So we can take the sequence of things and map it eagerly over feature call that will run all of the effects in a new feature. And then we can map the result again with the ref to join all the results. So here's an example. So now it's the same as before, except now we want to call the supplier service and the warehouse service. So we have two services. They are independent, so they can be run simultaneously. That allows us to save time. So we construct the two effects, and then we use par to aggregate this effect and return the composite effect. And then the same as before, we use bind, and in the continuation we're going to destructure a vector and merge all the results together. So that's it. That's a functional effect system. What we've done here is replace actions by descriptions. Instead of doing, we describe. So we represent effects as values, and we define pure functions to transform these effects. And we build our program as a succession of effects, as a composition of effects. So now you may ask, what's the point of that? What are the benefits? And to understand the benefits, we need to talk about processes. Processes are about doing. It's about using resources to compute a result. So when you ask the operating system for what's currently being done, what you get is a list of processes. That's how the operating system reasons about resource consumption. And actually, what we get is not a list of processes; it's a tree of processes, and that's very important. That's what we're going to talk about now. So we're going to look at the previous effect, the composition of services. Now we're going to see what happens at runtime when we run the effect. So here boxes represent processes, and a process is a value that is currently being computed. So the top level process is a bind, and a bind runs in two parts. So we're going to spawn a child process to run the first part of the bind. So we get the product information. At some point it will complete with a result, and now we can run the continuation with that result to get the second part of the bind, and at this point we can spawn a new child process, and this child process is a nested bind. So again, we can run the first part of the bind as a child process, and now it's a parallel composition, so we're going to spawn several child processes. So we get the supplier information, and we get the warehouse information, and at some point we're going to get one of the results, and now we need to wait for the second one, and now we can construct the vector of results, and now run the continuation on that, and now it's a pure computation, so there's no more work to be done, so we can propagate the result to the parent process, and then again to the top level process. Okay, so everything went well here, but now the interesting part is what happens when things go wrong. So we're going to go back in time and focus on the state of the process when we are running the two processes simultaneously, and we're going to assume the warehouse service is down. So it's going to complete with a failure. So what should we do here? Well, we need to propagate the failure. We need to report it somewhere. So we're going to propagate it to the parent process. But we cannot do that immediately because we still have a pending process. We are still trying to compute the supplier information. And it turns out at this point it's not needed anymore. So it's a waste of resources. The whole process is crashed, so we are wasting resources for nothing. So we need to cancel this process. And the process at this point must release its resources. So at some point it's going to terminate with a special result indicating it could not make it to the end because it was interrupted. And only now can we propagate the error to the parent process. And then there's no point running the second part of the bind, so we can propagate the error to the top level one. And now we are ready to make something meaningful with the error. So that's the behavior we want. And actually, that's not what our implementation of PAR is doing. Our implementation of PAR is not doing the right thing because it doesn't discard the pending process when the other one fails. So in imperative programming, it's very easy to not do the right thing in face of failures and supervision. We could write a version of PAR that does the right thing, and in fact, that's exactly what we want. We want to defer the supervision strategy to the operators. That's why we want to use functional programming. Functional programming is about building supervision trees. The idea of supervision is each process must have an explicit parent. A process that interacts with the real world may crash at any point. So when it happens, you want the error to be processed by another process, and this process is the supervisor, and it will be in charge of making a decision about this error. And there's always a right thing to do with the error. At the very least, if you don't specify anything, you want to propagate the error to the parent supervisor and so on, and maybe crash the entire thing at the end. Effect combinators are supervisors. When you combine two effects together, the combinator must define the supervision strategy. That's something we don't have in imperative programming. Imperative programming makes it very easy to spawn new processes, and it's very easy to lose track of the supervision hierarchy. In functional programming, it's impossible to do that. So you get structured concurrency by default. That is, you are forced to build your program in such a way that the supervision trees is properly structured. So all effects need supervision. In practice, there's many kinds of effects, but they have some common properties. What we've seen is elementary IO actions, so it's short-lived effect that terminates spontaneously. In practice, most useful effects are long-lived and they produce multiple values over time. We're going to talk about event streams and signals. All of these are effects that consume resources and interact with the real world. So we want them to have a life cycle to eventually terminate and release resources. We want them to be able to report errors, and we want them to be cancelable. And we want restful shutdown. That is, we want process to be able to know how to clean up themselves. Okay, so event streams. So a stream is a succession of similar events. An event is a piece of data that describes something that happens in the real world, and that is currently being processed to be eventually stored to some kind of knowledge system. An event stream is not defined when events don't happen. it's discrete time, so it's only defined when an event happens. It has no intermediate states. Losing an event is really bad. You want to process all the events. If you miss an event, you will end up with a partial knowledge of the world, and in the end, you will make a bad decision. So to represent streams effect, the effect representation must implement back pressure. If you don't have back pressure, you're going to overflow the buffers, your machine is going to crash, and you're going to lose events. Some examples of event streams: mouse clicks, log entries, database transactions. All of that has no intermediate state. There are things that need to be processed, and they are ordered over time, but they are discrete time, essentially. They don't exist between events. Signals. Signals are completely different. A signal represents the state of an identity. As Clojure programmers, we are usually familiar with this pattern because it's the basis for the epochal time model. So we have reference types in Clojure. We have atoms, agents, refs, and vars, which are they are local database, and they represent identities. And an identity, they all share common properties. They share the read API. So all of these references, you can derive them at any point. They are always defined. So at any point in time, you can take a snapshot and get an immutable value of the state. You can also watch them to get the successive values of the state. Derived computations share the same properties. If you derive a computation from a signal, what you get is also a signal. It's also defined on every point in time. Only the latest value matters. When the state changes, then the new state is the new reference. So you can discard the previous states. It doesn't matter anymore. If you want to represent signals as effects, you want lazy sampling. What it means is when the state changes and some readers want to react to that state, then you don't have to send the new value of the state immediately to the reader. You can just tell them the value has changed without sending the value, and then the reader can decide when is the right time to sample the value. And the reason we can do that is because it's continuous, you know it will still be defined in the future. So we can introduce laziness, and that allows us to save work. Very interesting. Some examples of signals: the mouse position. A mouse is always somewhere, so you can always ask for its position. Physical time, you can always ask what time is it. Spreadsheet cells, if you want to know the state of a cell, you can just look inside. Databases are signals because they always have a state. That's why we use database. We want to accumulate knowledge about the world, and we don't know in advance how the knowledge will be used. So we want to be able to pull the state in the future, so we want the database to be always defined. Derived computations are signals as well. So the queries of a database are derived computations, so they are always defined. All right, so now let's get more practical. So this is Missionary. It's a Clojure library that works in Clojure and ClojureScript, and it's a collection of purely functional operators that work on effects. And there's two kinds of effects. There is tasks and flows. Tasks are effects that produce a single value, and flows are effects that produce multiple values. You can use flows for discrete time or continuous time. In discrete time, we get back pressure. In continuous time, we get lazy sampling. Language extensions. So that's how Missionary solved the callback hell. So this is the previous example about sequential composition. We see the beginning of the callback hell here. There is too much nesting. There is only two successive tasks, and it's already too much nested. So if we increase the complexity, quickly enough, it will become unmanageable. And it's a syntax problem. So there's many solutions to this problem. All of them are variation about the idea of inversion of control. So we want a better syntax to express this thing. So the solution is to extend the language. So we extend Clojure with another operator. That's the idea of async await, but now it works in functional effects. So we have a parking operator that allows us to split the computation. There will be syntax rewriting that will turn this code into a chain of callbacks. So we pass a task to this operator, and we're going to park the computation until the task terminates and we get a result. So it's a functional version of async await, and you have all the features of the language. You just have an explicit operator to park the computation. It works pretty much the same as in Go blocks, but the underlying abstractions are not the same. But the syntax rewriting is the same idea. Now, can we await on flows? That's the interesting part. Remember, a flow is an effect that produces multiple values. So what does it mean to await on something that produces multiple results? Well, it's been done before, but it's surprisingly unpopular, which is a shame because it's a very interesting idea. So here's an example. Now, we want to reuse the effect from before that aggregates information about products. So it's this one, and now we want to have a variable input. So the product ID will be stored in an atom, and we're going to change the state of this atom. What we want is to keep the product information in sync with the product ID, which is the variable input. So we're going to use an AP block. We're going to build the flow that produces the successive values of the atom with watch, and we're going to use a forking operator, this one, and at this point, the rest of the computation will be run multiple times. Whenever we get a new state on the atom, we're going to run the rest of the computation. And what we want is, if we get a new value of the state and the previous value is still being computed, we want to interrupt this previous computation and start the new one. We are only interested in the latest value, so we want to discard the previous computation. So we're going to call the extended product information effect here, and we're going to park on it. And we're going to wrap all of that in a try catch to recover from interrupted exception. In this case, interrupted exceptions are not failures, they are part of the normal process. So we want to recover from them, and in this case, we want to produce nothing. So that's the point of this operator, it's to return nothing. And at this point, we're going to backtrack to the forking point, which is here, and run the computation on the new state. And that's it. So it's a functional version of await. It's a language extension, so you can use all the features of the language. You have macro expansions, you have try catch, we have conditionals, you have loop recur, and all of that is wrapped in a functional expression. It returns a discrete flow, so it's a purely it's a referentially transparent expression. And if you use this flow in a pipeline, you're going to get back pressure. You will also have error handling for free. You will have cancellation. So you get all the benefits of supervision due to functional programming, and you have all of that in a syntax that looks like Clojure. So that's very powerful. Well, there's more operators, but these ones are more standards, and we are running out of time, so we're going to see that another day. So that's it. This is a functional effect and streaming system for Clojure and Clojure script. What makes it unique is language extensions. It's alternative to monads. It's as much as powerful, but it's much more expressive. So it's you can express the same thing, but without callbacks, without losing track of the control flow. So that's much more maintainable, much more efficient. Discrete versus continuous time. We need both. Many streaming frameworks support only one of them, usually only discrete. In practice, you want both because some effects are inherently discrete and other ones are inherently continuous, and they don't have the same requirements. So it's you need to be able to switch from one to the other, and it's useful to have an effect representation that supports both. So that's it. Try it, give feedback, spread the word. Currently, the API is stable. The current effort is about smoothing the rough edges and improving documentation. It's part of the Hyperfiddle stack. We've been using it extensively in the last year. We've been implementing a fully reactive dialect of Clojure on top of it that also works distributed. We are very excited about our findings, so we're going to communicate more about that in the future. So stay tuned.
Wow, that's another fascinating talk on performance. Thank you very much. I'm certainly looking forward to learning more about Missionary and trying it out for myself. Thank you very much, Leo. I guess that there must be quite a lot of questions built up in the back of people's minds now about performance and what Leo and Ben have covered. So let's get this panel started. And while we're doing that, please feel free to add more and more questions into the Discord chat and into the Zoom chat as well. So I see Renzo is here to help me out.
Yeah, I'm helping and see if we can synchronize with all the chat and see if we can get all the speakers online. So I see Leo is connected. See if Leo can connect to us. Can you hear us? Can you unmute yourself? Oh, wait, you can't unmute yourself. Now you can unmute yourself.
I'm here. Hello.
Thank you. Fantastic. And then we'll see if we can get Ben as well.
I think Ben was there. He's disappeared off my list. Oh no, there he is.
Yeah,
he seems to be unmuted.
Ben, are you here with us? I heard the microphone unmuting. Yeah.
Can you hear me now?
Yay! Yes. There we go. Welcome, Ben.
Thank you. Thank you.
Yes, while people are asking questions, let's start off with an icebreaker for you, Ben. So do you have anything interesting or curious or quirky you'd like to share about your surroundings or about what you've been doing recently?
Recently, I've been following down the paper trail of papers behind the mini Canron, which has been really interesting. So I've been thinking a lot about streams and things that I feel sort of like a dog watching TV. Like it's interesting, it's fascinating, but I feel like I don't fully get it yet. But it's also interesting to see how it all connects and congeals together, and how, for example, the implementation of streams there connects with Leo's work, and how that connects with reactive streams, which I also briefly mentioned in my talk. Sometimes it feels like it's all connected. So
what about the little books? Do you have it already?
The little book?
The little books, like the little schemer, the little.
Oh no, but
not yet.
This one.
Oh,
hello.
Good. Okay. Let's prepare for that. Thank you. That was an interesting book to share.
Yeah, I have it at hand.
All right. Yeah. Same question for Leo. Is there anything like interesting you want to share? Maybe an item or?
I'm going to share something about my environment. So it's a prop that has been on my desk for many years now.
Here it is. So it's a paperweight that I use as a rubber duck. So it's not made of rubber and it's not a duck, but it's watching me all the time, and it's been a very good compiler so far.
Nice or creepy, depending. Maybe is sending you energy, I guess.
True.
The spirit of Minerva is giving you some of her wisdom.
Nice. Okay, let's start off with a question for Ben. I think you've actually answered a little bit of this already in the Discord channel. So Jack was asking about he's used the async profiler and flame graphs, but like found it quite hard to interpret. And I imagine there's kind of like a lot of experience, or are there specific techniques you can use to actually understand the results of all this, like performance and profiling?
Yeah, one thing to understand about performance tools in general, that like any tool, you need to both get some experience with them and you develop intuition as you go along, and you also need to like get things wrong sometimes, right? Unless you do the wrong stuff and get bad results or results that don't make sense, you won't know when you're doing the right stuff. So it's usually enough to go over the documentation, and there's a lot of documentation both regarding CLJ async profiler and flame graphs. Brendan Gregg has done incredible work on it, and he keeps on writing and providing material. And the theory of flame graphs is not it's not exclusive to that work in particular. You can find many instances of tools and documentation for flame graphs today. So yeah, it's just experience and just use it until you get comfortable with it, and if not, you can always open issues to any of the respective repositories, ask questions, because I can say that, for example, on CLJ async profiler, Alexander Yakushev is very responsive to issues, so he's happy to answer any questions.
Okay, and just a quick follow on from that. When you are trying to interpret results, can it be very REPL driven, or is it something you kind of need to go away and think about a little bit more about how best to tackle things?
It depends both on the nature of the problem and on the degree of intuition you develop for that particular problem. And this always reminds me back in college when we started learning quantum mechanics, and the lecturer told us, he's shown us the results of some example, and he said, well, this should make you uncomfortable and you should have no idea why this happens, and you also have no intuition for it yet. But as you get used to it and you start swimming in the material and in the mindset, you do get used to it. So at the beginning, you might need some, hammock time or walk time or whatever you do to process the ideas. But later you'll recognize or learn to recognize some behaviors or some pathologies, and you'll be able to just make a snap identification when you look at the flame graph and you say, oh, this stack looks really weird. I want to look at it. And like, why am I using reduce one, for example? Or why am I dispatching via the wrong protocol, which I didn't expect?
Okay, oh yeah, that sounds great. Yeah, that's very useful. Thank you very much.
So we can get to our first question for Leo as well. So I'm going with Jakub, that, by the way, shouts to Jakub for making so many interesting questions. So it's very active. Thank you. Do I understand right that the functional effect system is quite similar to promises, where a thunk is a promise, par is a promise to all, and bind is a .then? But while promises start execution when created, thunks only start that hit lazily when asked for their value. Am I completely off?
So, Jakub, you're not completely off. Promises and effects are similar but different. So as you said, chunks are lazy. So when you declare a chunk, it doesn't run. It runs only when you call it. The other difference is features are memoized, and chunks run whenever you call them. So when you ask for the results for a feature, it doesn't rerun the results. But otherwise, that they both describe an asynchronous result.
Thank you. Hopefully, it was explanatory for Jakub.
Okay, yeah, so I guess I have a question to Ben about if somebody's like starting. There's a lot of really interesting things you've covered, and you said kind of building up experience is quite important. But if you're starting from day one, I mean, is things like time and criteria a useful place to start? Are they a nice gateway drug almost to kind of lead on to the more interesting and more insightful tools that you've got?
Well, let's say when you're getting started, and let's say this is a new application, don't profile, don't benchmark anything, develop your application. And once you have a living, breathing application and you have solved all the rest of the problems, such as blocking and the implementation details, then you should profile it. And if you, let's say, meet your KPIs, go drink milkshake. Don't bother. Really, don't waste time shaving nanoseconds of an application that meets its requirements. But it is good to at least have some profiling results of the application for when you might need them later. But don't go running to optimize it before you need to. And once you do need to, then you need to start with, for example, generating a flame graph, connecting to it with Visual VM to get it's like studying animals. You don't want to study them on an operating table. You want to study them in the wild. And then when you get a good picture of the moving bits and pieces and the hot paths and the pathologies inside the application, then you can focus on them. And then it might be the time to take a specific bit of code and a specific bit of sample input, and then use Criterium to get the initial baseline benchmarks, try an optimized implementation, and compare them. But you don't just go around with the hammer of Criterium and and start beating around your functions, because you'll be it can get addictive. So I can recommend against starting there.
That's very wise advice. Thank you very much.
So going back to Lionel, I wanted to ask you one question. So I think I briefly, and it's for me, I think I briefly saw on your slides the AMB operator, and you also mentioned the previous art. I just wanted to showcase that also Jerry Sassman on design software design for flexibility is talking about the AMB operator. I just wanted to understand if that is possibly the same. He's mentioning McCarthy, and is quite interesting operator. There's like a long explanation, and it's quite interesting what it can do, but it's very simple. I just wanted to understand if we're talking about the same thing. Thank you.
Well, I cannot give a definitive answer because I've not read this book yet, but it's from the same author as SICP, so I guess it's the same idea. The inspiration for the AMB operator that I described is from the book from Zussman, so I guess it's the same.
It's probably the same. Thank you.
Alrighty, I'm going to take a question from Renzo. Actually, there's a few questions that Ben's been answering in the Discord, which is great. We might go and revisit them later on. But Renzo was asking about mechanical sympathy, and if you have any thoughts about the JDK 16 introducing vector operations and how Clojure could take advantage of SIMD, single instruction, multiple data.
Yes, or affectionately called SIMD back when we worked at when I worked at Intel. The most mechanical sympathy problems in Clojure are usually solved by just using backing arrays, which the core collections already do wonderfully. And if you look at the vector API JEPs, you'll see that they're mostly focused on numerical operations. And most operations we do in Clojure are collection oriented and data oriented and less numerically oriented. So while you can get some improvement there, I don't see how. Yes, it's nice, you can do a lot with it, but there's a lot of ground to cover before you can connect that to collections.
Yeah, thank you, Ben. I think I see it's quite like low level, and I mean, if there are operations that can be actually parallelized in that way, they are very deep into the compiler. There might be bitwise operations, or they might happen inside the implementation of core collections, but definitely requiring some work. But I was thinking maybe to take advantage of that part somehow as a library, but I still don't know how to produce anything useful with that. So just very interested in that topic.
If you want to get a peek or a window into how that can interact with the JVM, there's a discussion in the SIMD JSON library regarding that exactly, using the SIMD API for the JVM and parsing JSON in relatively high throughput. There's a thread in the library there. You can read the discussion. I think it's kind of stuck in dead in the water in the meanwhile, but it will probably pick up steam in the future again.
Indeed. Thank you for remembering that. And I remember that the fastest JSON parser in the world is using exactly those techniques, written in C, of course, and assembly, whatever. It would be nice to as an exercise to bring that into pure Java. It won't be as fast, but it would be decently fast. All right, thank you, Ben. So I'm gonna now keep talking and asking you another. Oh, so this question was for you already. So yes, I'm gonna pass it back to John. Sorry, I was confused by me being the the question maker.
Did you have a question for Leo, Renzo, or
yeah, there you go. That's why I'm confused. I should ask the question to Leo, and I was asking to Ben. Yes. Sorry for that. Sorry for the confusion. Yes. So another question from Jakub. So how does Missionary compare to CoreSync and its channels? Is it an alternative, or do they have different use cases?
Well, how does it compare to CoreAsync? I'm going to start with the similarities. So they both implement this inversion of control syntax that looks like async await, and they use both the same technique to achieve that. Regarding the use cases, they can be both to implement streaming. The channels support back pressure, Missionary support back pressure in another way, but it's there is overlap in the problem space. Now they are fundamentally different because it's not the same paradigm. CoreAsync is much more imperative. It's also much less constraints, so there are many things you have to do yourself. You have no supervision in CoreAsync. that means in general, you have to program defensively, because if your Go block throws an exception, then you need to put it into a channel somewhere. So in missionary, you get all of that for free, and the price you pay for that is the style is more constrained. You cannot spawn a process whenever you want. You have to compose effects together.
Okay.
So yeah, that's pretty much it. It's not the same programming style.
Okay, thank you for your explanation. So we have Jakub now online. Was it your question for Leo or Ben? Jakub.
I was actually going to ask myself the question that you asked for me, and the answer was.
I'm sorry, I got you.
So I don't have anything more. Thank you very much.
Sorry, I just saw your hand raised now. Okay, so we'll back to you, John.
Sure, yeah. So Ben, I think you've already answered this question in Discord. I just wondered if you had anything else to say. So somebody was asking what mini Canren is and how does it connect to stream programming. Is that something you want to comment on?
Yes, mini Canren is a logic programming library written originally in Scheme by William Byrd. And it is also the work behind core logic, if you've ever used it. And also the reason I am programming in Lisp today, because I was inspired by Byrd's talk at the Papers We Love channel. And that's how I ended up here. But the interesting thing regarding streams with mini Canren is that you need some method to implement a search of the option space when you're doing logic programming. And the way it is implemented is, think about it as a sort of fair list comprehension. Because if you, for example, have two infinite lists of options, you need a way to fairly interleave them to search the option space. Otherwise, you might diverge, delving into one stream. So you need both fair streaming, fair interleaving, and fair interweaving, which allows you to backtrack the search in case it fails. And that is based on Oleg Kiselyov's work on the logic monad. And he also did a lot of work on streams and operator fusion. And if you read his paper on operator fusion, you find it looks just like transducers, which is amazing.
Excellent. Yeah, that's a lot of fascinating work there. I'm just curious, did you have any questions, Ben, that you wanted to ask Leo while you're here?
Well, I kind of have been pestering Leo with questions for a while now, but I do wonder if there are already any user reports and from people using Hyperfiddle, not Hyperfiddle, sorry, that hopefully will come in the future too, but people using Missionary in production, because I want to start using it actually.
Well, that's the problem with open source, is you never know. No, I'm not aware of any explicit feedback that says it's used in production, but it's definitely designed for production, and it's mature enough now to be. There's I think there are some bugs that need to be fixed right now before, because there are still some edge cases that are not well defined, and if you're not aware of them, then we're going to have unexpected behavior at runtime. So that's the main thing that I want to fix before seeing it's production ready. So that's going to happen very soon. I'm pretty clear with that. So basically all of what I want to fix before switching the production flag are listed in GitHub issues. So we can look at that, and if you have specific questions, feel free to ask.
One final question, actually, regarding missionary, which I just thought of during your talk. Do you have any intent or plans to implement either the sequence or reduce interfaces from core Clojure on flows? Because currently you have the reduces, you have your own implementation of reduce, and it is a bit ad hoc, but if you implemented the reduce interface, you could reduce and transduce overflows immediately.
What would be the benefit compared to what's existing now?
That you could use core Clojure reduce.
Oh, you mean with a blocking reduction function?
For example, yeah.
Because the purpose of flow is to be async. So if you want to use Clojure reduce to reduce overflow, then you need to leverage threads to block until the values become available.
Mm-hmm.
I have an implementation for that that relies on iterable, Java long iterable. I've not decided if I want to add it in core. It would be Java only, that's for sure. But I can show you if you want later. If that's useful to you, let me know.
Okay, thank you.
Thank you both for that. That was very, very interesting. Renzo, is there another question for Leo?
Yeah, we have a couple of questions from Dustin Goetz. I think he's also working with you, Leo, on Upper Fiddle. Is that correct?
Yeah, that's right.
Okay. So he's asking the following two questions, so we'll take them in sequence, I guess. What is Mini Canron and how does it connect to stream programming? And what is your long-term goal with Missionary? And is there a killer app for that?
I guess the Mini Canron question is for Ben.
Oh, we already answered that
okay.
one. Sorry. Yes. So it's just the second one. Missionary.
Okay. So what's
so to skip that then.
Yeah. What's my long-term goal with Missionary? Well, I consider Missionary to be close to done, and I don't expect it to grow much. I think it's a good foundation, and the idea is to build other things on top of that, not to grow the library itself. It's built on two fundamental protocols that don't depend on Missionary. So if you want to make something useful that is compatible with Missionary, it can be a separate library. So the idea is to make an ecosystem grow around these two fundamental protocols. So that's the first part of the question. Now, is there a killer app? The original motivation for it was user interfaces. So I would say in the front end, the goal is to have a better foundations to make better user interfaces with proper incremental maintenance and fine-grained reactivity. It's still pretty much low level to make UI, but it's a good foundation. On the backend side, I would say it's a useful tool to implement distributed algorithm, for instance, because in this problem space, you spend your time dealing with errors, retrying stuff, sending value asynchronously, deal with time, stuff like that. So you need the right basis, you need supervision, you need that kind of stuff. So I would say that would be the main use cases.
Thank you. So with that, I think we arrived at the end of the questions that we collected so far. So thanks everyone for asking nice questions to our speakers. As usual, thanks to Leo and Ben for bringing their wisdom and putting the effort into in their talks today. It was very interesting topics so far in the entire like a UK morning. Thanks again. Thank you very much for coming. Thank you for being here at the KA panel. So we are going now to into another longer break before Paula Giron next talk. I just wanted to introduce Jordan, who will be with us for the rest of the afternoon. So Jordan, you want to say hi?
Hey, good morning. Hey.
Yeah, you have to turn off, I think, again the Zoom feature that is automatically adjusting your volume because you're coming and going, at least for me. But we'll take that offline. So Jordan will be with us after for the next talk, and for the moment, enjoy another long break. See you after the break.
We can't hear you, Jordan. I think no. I think you're unmuted, but it's still the sound is still not coming through. Yeah, I don't think. Try again. Oh, it's very quiet now.
Hello, can you hear me now?
We can hear you, but it's very quiet.
Yeah, you can. Well, I'm going ahead. You can try to see in the preference.
How
Zoom
about
preferences
now?
for the. Oh yeah, there you
Perfection.
Much better. Okay, I just had
Perfection.
to turn up my input volume. Thank you. Hopefully everybody is back from that longer hammock time, leg stretch and break, because I am very, very excited to introduce our next speaker. Very talented Clojurista and good personal friend, Paula Guerin. Paula is an avid Clojure developer and a valued leader in the Clojure community. She has fearlessly led numerous commercial and open source projects to glory through various perilous technical pursuits. She has also given an impressive number of talks at different conferences around the world. Most of her experience focuses on data storage and processing. So without further ado, let's hear it from Paula.
Oh, she's going to give the talk live, so we need to grab her into the. There you go.
Perhaps she needs permissions to speak.
Yes.
Oh, there she is.
I did, and Renzo's allowed it now.
Hi, Paula.
Sorry for like the little hiccup there.
Hi there. Thank you for that introduction, Jordan. That was a little over the top, but
well-deserved over the top.
Yeah, I'm giving the talk live today, and I hope it works out. But we'll we'll see how this goes. Hi, everybody. It's morning for me, afternoon in London. My name's Paula. I work at Cisco Systems. Today, I wanted to talk about data log databases. This term first came out when Datomic came on the scene a little over 10 years ago now, or about 10 years ago now. Datalog had been around for a while though, and I wanted to compare and contrast what traditional Datalog is with where Datomic has brought us. So Datomic was first released in 2012. We heard a lot about it during the release from Rich Hickey, Stu Holloway, a number of the Cognitect people. It has a number of operations associated with it. When we're writing to it, we do this through transactions, which can be based on statements or entities. When reading, there's a few different APIs. We have the Datalog API, which I'm focusing on today. There's also the Entity API. And later on, they introduced the Pull API, which integrates in with Datalog. Since then, there have been a number of other databases come along. We have DataScript, XTDB, which was previously Crux, Data11, Eva, Asami is a project that I work on. And all of these have been referred to as using Datalog as their query language. So what does this entail? For those of you who aren't familiar with these sorts of databases, what if we look at a standard relational database, which is based on tables? So here's a very simple table with some people entered into it. This has proven to be very useful. People have been using it now for something like 40 to 50 years. And many websites and commercial systems are based on data that's structured this way. However, what happens when we discover that we need new information, we need another field? Well, this takes migration, where we'll introduce those new fields, but they may not necessarily have data associated with it. It's possible to introduce new tables, but sometimes it doesn't make sense, and it also has performance implications. We can as new columns come in, we'll find that some of the data continues to be blank. We'll end up with a whole lot of space being unused in the table. And there are major issues associated with trying to migrate a database from one version to another. We'll also notice here that each record in the database takes up a full line. And some of these lines have empty spaces in them now. It's not particularly efficient, although once you go to a particular line in the database, you've got all of that data immediately available to you. So a graph database takes the same data and represents it as a series of nodes which are connected with arcs. You'll see that each of the columns in the tables have now become labels for these arcs. I've left a couple of the labels off in the bottom corner because it's getting a little difficult to see, but you can see all of the data is still there, and we're just viewing it somewhat differently. However, a database doesn't necessarily store it this way. To do that, we're going to take those entities and their label, the arc label, and the node that they're pointing to, and we'll move these into a table of their own, which we refer to as triples. Now, most databases will also have extra columns left out on the side, indicating the time that triple came in, which transaction it occurred with, that kind of thing. But in general, the data that we're interested are going to be these statements where you have an entity ID, a label to connect it then to the value. In Datomic, these are referred to the entity, the attribute, and the value. So what's the difference between these two structures? Well, graphs are much more flexible. As we have new fields, data fields that we want to bring in, we can just add a new arc out to connect that data onto a particular entity. And we need only do that for the entities that we're interested in. We can index everything because we only have 3 columns that we're working with. We can index on each of those 3 columns, but we can then sub-index within them as well. So that if you're indexing by that first column and then the second column, or you can index by the third column followed by the first column. There's only a few different possibilities here, and it lets us find all the data really rapidly. We can provide metadata on each individual assertion. As I mentioned earlier, that's often done with most databases. That can include the transaction ID, the time, the provenance where the data came from. And there's all sorts of other things which can come in as well. In Asami, I have an individual ID for every statement, and then I can make arbitrary statements about statements. It does use more storage space. This isn't as tight and as compact in general as tables are, particularly when there aren't any blank fields in tables for relational databases. And we can also find that this approach has the potential to split entities up. Typically they're not. We generally aim for data locality, but particularly when we've got indexes that aren't being indexed by an entity ID, then we can see data for an entity split up across different servers or different parts of the local hard drive. We're also doing statement at a time selection. That's not entity at a time selection. And consequently, just to see an individual entity, we're going to have to perform a join operation to connect these statements up. On the other hand, we had our relational tables. They're very rigid in their structure. They're not flexible at all. If we want indexes, we're going to have to select the columns that we want to index or the combination of columns that we want to index. That can be extraordinarily expensive. We can have metadata on rows, but that's on the row only. That means that if you've updated an individual field within a row, you don't have an easy way to provide metadata around that update, like the time and date it occurred. In general, if it's well packed, if it's in third normal form, we can use a lot less storage space than a graph may use. This can vary according to specific implementations, but in general, graphs are going to spread your data out a bit more. We have greater entity locality because entities are being represented per line. And when we're selecting lines or rows, we've got to select the entire thing. And that has performance costs when we're processing a lot of data. Column databases are an attempt to get around some of that, but they introduce their own performance issues as well. So looking back at the relational form, how do we do a simple query like finding the first and last name of the person with the Twitter handle of Bingley? Well, that where clause generally implies that we have a filter. We're going to go through each row of the table and pick up on those rows which match the filter that we're looking at. We can index so that we can find that immediately. When an index exists, the query planner will identify that and it will change the filter to an index lookup automatically for you. However, building indexes takes a lot of time, takes a lot of space. And in an instance like this, where not everybody has a value in that particular column, an index may not make sense or work very well for you at all. Let's try the same thing now with data log. We're still looking for the first and last name, but now we need to do a series of graph patterns where we want to find the person who has that Twitter label, and then we ask for their first and last name. Now, our data is already indexed, and here's an appropriate index to look for it. These are the slice out of the statements. We're looking at the entity ID, the attributes, and the names. Because our data is indexed, we'll be able to find the Twitter handle of Bingley quite easily, probably through a different table, a different index, but then using that ID of 3, we can look up the person's first name and their last name, and that's done by a join, where we can simply look that up by the entity ID. So this is what data log looks like, but is it really data log? Let's look at a different graph language, in this case, Sparkle. Sparkle is a graph database, is a graph query language developed for the RDF system. The structure of this query is basically identical. We're still selecting by the first and last name. Our where clause still has the same variables, the same attribute identifiers. We're still referring to Bingley, and the variable first name, last name is still there. Nothing has changed at all. It's a slight syntactic variation and nothing else. Now, for those who are familiar with Sparkle, the colon prefixes for Twitter and first name and last name would generally require a default prefix defined, but that's just a syntactic convenience for us. The structure of the query is absolutely identical to what Datomics queries look like. So what does data log really look like? Well, it's defined as horn clauses. These are implication statements. The first one here indicates that a statement is always true. This is used for representing data that we want to assert as true. And that's that maps onto where we do assertions of statements into our system. There's also rules. That's where a series of predicates to get taken together will result in a statement being true. This isn't the syntax used when data log appears in a database. Instead, we'll describe it this way, where data is a predicate with attribute values associated with it. And predicates need not be need not only have 2 arguments, they can be longer, but in general, they'll only have 2. Or 2 or 1. And then we'll have rules. And you'll note that the thing being implied appears first. and then there's a colon dash, and then a comma-separated list of predicates. So how does this work in practice? Well, we can define statements, data, using particular predicates. The predicates themselves here are parent, and then the values that appear in there are something called atoms. We see that the atom Xerxes has a parent Darius, and the atom Darius has a parent Hystaspes. Data appears similarly. In this case, we have predicates of ancestor being defined in two different ways. So if there's a parent relationship between X and Y, there'll be an ancestor relationship between X and Y. But also if there's a parent from X to Y and an ancestor from Y to Z, then there'll be an ancestor from X to Z. Now this is a recursive rule because that second ancestor statement refers to itself. That's a very important attribute on Datomic, not Datomic, sorry, a very important attribute in Datalog in general, having this recursion. And there may be many different rules, many different predicates being created based on other statements, and there can be loops and all sorts of things in there. So that's how we assert data, and that's how we define rules on the data. What about querying it? Well, in this case, we have the question mark dash, and we ask for a predicate with variables to be filled in. In the case of parent XY, it'll find all statements that match that. For ancestor, we can then say from Xerxes to X, and then that'll find that list of ancestors. Oh, and it's missing from Xerxes to Darius, I'm sorry. So what are the operational features of Datalog? Well, there's order-free evaluation. It doesn't matter which order those rules came in, or if statements were interspersed between them. It should not matter how that works. You should get the same result. Depending on the way that evaluation is determined, there are a couple of cases where evaluation under one algorithm can give you slightly different data than evaluation under another, but in general, it's going to be the same. Well, in pure Datalog, it will always be the same. Then we have recursion, which we saw. There's a guarantee of termination. And also Datalog itself should not have any negation associated with it. Now, these requirements and the implications of them were heavily researched through the 80s and compared extensively to relational algebra or SQL. Since then, relational databases have adopted recursion. I've rarely ever seen it used in practice. So when this was being researched, we see back in '89, it was compared to relational databases. I'll clean that up a little bit. As I said, most relational systems will now include recursion in some way. Standard SQL can make that very difficult to access. Now, I've mentioned there's no negation here. Datomic does have it. It's actually an extremely common extension, and it was referred to numerous times from the 80s going forwards. It's this negation which can lead to different sorts of data coming out depending on the mechanism for processing. But what is that mechanism for processing? Well, the most common one is top-down. In this case, you start at your query goal, and you're going to merge that against the rules. If you've got no more possibilities for merging, then you need to exit. Then you'll find those statements where the atoms do fulfill the expressions, you collect them, and you keep going back to the beginning again. You merge against rules once more. If there's no more possibilities, you exit. And this loops over and over again until you found all of the data. Like Prolog, this is doing depth first search. It's usually done with the depth first search. You can also do breadth first. Now, another approach is to use the bottom-up evaluation strategy. Sorry, there's numerous different techniques which are used for doing this. Now, using the bottom-up strategy, you start with all of your provided data and you evaluate your rules to create new data statements, which then get asserted back into the database. You'll note that the output of rules was always a predicate. This looked like the input of statements. And so we can assert these directly in storage. We keep repeating this until we reach a fixed point. Now, this takes advantage of database operations, which are very fast. We only need to evaluate this a single time for multiple queries. If there's an update to the database, we note the delta, and we don't need to evaluate all rules. We can just work on those deltas. It can use a lot of storage depending on how much you're trying to infer. And it may evaluate data that isn't needed. However, that can be faster anyway. Recently, I had a case of something with some pathological data that was taking 90 seconds to evaluate with a top-down evaluation. I changed it around to using bottom-up, and it reduced this time to just over 100 milliseconds. Okay, so the sorts of terms that we see in Datalog are the rules and the data that we were referring to earlier. But there's actually two types of data. We've got the data which came in that we defined ourselves, and then we have the ancestor data that comes out through the evaluation of rules. The data that was put into the database is referred to as extrinsic data, while the data coming in is while the data being inferred is intrinsic data. In bottom-up evaluation systems, the intrinsic data gets mixed in with the extrinsic and it becomes extrinsic. It's the top-down systems which have a very clear delineation between the two. So Datalog is often compared to predicate logic because it looks like it. However, it isn't predicate logic. However, if we look at it this way, as if it is predicate logic, we can consider each edge in the graph, the node, the predicate to another node, as if it's a two-argument predicate. Now, in something like Datomic, we're more familiar with labels like this of attribute on an entity and value. So we can map Datomic's approach onto what we're looking at here in Datalog. So let's put in some extrinsic data. We'll declare our atoms of Xerxes, Darius, and Hystaspas to start with. First of all, I want to declare them as entities and give them an ident. That's going to make it a little bit easier for me to talk about them. So when I want to put in these statements of parent connections, I can do that by adding Xerxes, Periant, and Darius, and I can refer to them directly now through those ident labels. But what about the rules? We've got those two ancestor rules. We can define this in Datomic using rules. You'll see that we have the two clauses of the rules below. The first line is the name, and then the remaining lines is a definition of the rule. And these look like queries, although you'll see that they can refer to the other rules by name as well. We can put this, we can start querying the database now. If we want that simple query where we're asking for the parent connection from X to Y, that just becomes a pattern lookup in a find query in Datomic. Unfortunately, the labels can be we'll get internal identifiers. And so we'll want to add in ident statements so that we can get the labels out. But what about using those rules? That becomes much more complex. Well, here we can take our rules as a vector and we add them in as a parameter at the bottom of the query. And you'll note that the in clause is now expanded to include that percentage that can pick up on the rules. The where clause now isn't referring to graph patterns like we did. It's now referring to the rule that we're looking for. Graph patterns can also appear in there as well. But now you'll see that the request for a rule is looking a little bit different to the graph patterns, whereas in Datalog, we use the same predicate form for everything. Again, we're going to get internal identifiers out if we get X, so we can just update that to ask for the ident. Well, based on this structure, is Datomic Datalog? Doesn't match the syntax, but it does have an intrinsic database, extrinsic database via the rules. It does have recursion, and it does terminate, does guarantee termination. It does also have extensions, which Datalog generally allows, like negation. So semantically, definitely we meet the criteria of Datalog, but syntactically, we don't. So is Datomic Datalog? I believe that it is quite justified in calling itself Datalog because it provides all of that functionality defined in Datalog and much more. We have aggregates, we've got negation, there's a whole lot of functionality that extends on Datalog, but we meet all of the semantic requirements that Datalog has in it. So when Rich came out and called his Datalog, his database a Datalog system, he was absolutely correct. It meets all of that criteria. However, the query language for Datomic is a graph query language. It is not the Datalog language. That syntax of predicates and horn clauses simply does not exist in Datomic at all. And it is part of what defines what Datalog is. So when we're talking about a query language, Datomic's query language isn't something that I would refer to as Datalog. And I'll often make this statement to people anyone who wants to listen to me on it. If you want to argue with me about that, then you can find me on the Clojurian Slack in the Asami channel. I go by the handle Qual, and that's on Twitter as well. So.
All right, thank you so much, Paula. We learned so much about the similarities between Datalog, and we are going to go into a 5-minute break here, and then we are going to get back and hear from Eric Normand. Howdy, folks. Let's get you rolling back from that short break here. I hope you're enjoying your Saturday with us. Remember to ask any questions in the Discord channel, on the Zoom chat, or best of all, during the Q&A panel, you can raise your hand. But before we do Q&A, I'm very excited for our next guest here. Hello to Eric Normand. If any of y'all are wondering how I got so smooth at being a Clojure personality, well, the secret is that I learned from watching the best. Hailing from New Orleans, Louisiana, Eric Normand has a passion for teaching. His instructional content has been instrumental in many of our personal development journeys. You can listen to his thoughts on his podcast titled Lispcast and read his thoughts straight into your inbox by signing up for the Purely Functional TV newsletter. Without further ado, let's see it.
Hello, my name is Eric Normand, and I'm going to be speaking about the art of domain modeling. I want to thank you for attending my talk, and I also want to thank the organizers for putting on this conference. I know it's a lot of work. I believe that modeling the world is a human way to understand how things work. From the beginning of humanity, we have created models. We imagine what an animal might do so that we can better hunt it. We tell stories about situations so we can learn from experiences we never had. We use science to develop models of many aspects of the world, and now we have computers to build and test models very quickly. Why do we model? Models help us see further. We can only experience the present. Models place the present into perspective with the past and the future. For instance, if it's raining today, in the present, we can place it in this larger cycle, most of which we don't experience very easily directly. Models help us learn and understand, cure disease, and feed more people. And from a capitalist, maybe economic standpoint, better models help us create more value and lower costs. One way software adds value to a business is through new features. So we can translate this: more value means new features. And since maintenance is the most expensive cost of software, the primary way to lower cost is to require less maintenance. Unfortunately, both the speed at which we can add features and the cost of maintaining the existing features are unknowns until after we do them. We can estimate, but we get the estimates wrong. In business, we call this a lagging indicator. You can't control the metric directly because it's too late to change it by the time you measure it. So intelligent people in the software industry have developed a leading indicator for maintenance and maintenance cost and feature speed. They call it software design. Software design is a bunch of rules and advice, sometimes it's measurable, of things you can use as a proxy for cost and speed. For example, software design might recommend functions of no more than 5 lines of code, meaningful names, and low coupling and high cohesion. The argument goes that if your code is messy and hard to understand, it will be harder to maintain and modify. I believe that. It makes sense to me. But why does our code get so messy in the first place? Is it because we're lazy or under intense pressure from management? Maybe. But I also believe that good software designers have an intuition for modeling that they don't know how to express. They can give us rules of thumb, but those designers, their software, isn't just short functions and good names. There's something more that they're not telling us because it's very hard to figure out their expertise. Okay, to help explain this, I want to tell a story. Maybe it's a fairy tale, but I think it has some truth to it. Here's a diagram showing the geocentric model of the universe. It's neat and tidy. Everything is named well, the lines are all clear, you can follow the lines all around the circle. And it works pretty well. At any point on the calendar, you can figure out where the planets will be, mostly. But the diagram is complicated. There are all these curly cues and crossing lines. If you want more accuracy, you need more curly cues. And a chart like this requires lots of maintenance. Management goes to the first programmer. There's 3 programmers. Goes to the first one and says, "We need a new feature. Please add another planet." The programmer responds, "Well, that's going to take a long time. Can't we clean it up first?" So management asks the second programmer, "Can't you clean it up a little?" And that second programmer, she responds, "I've been to the clean diagramming workshops. We use all the best practices, like using sharp pencils and clear labels. We could get rid of some lines, but then we lose accuracy." Finally, management hires a software design consultant and asks her, "Please help us with our technical debt. We can't add new features quickly, and it costs a lot to maintain our diagram." the designer says, well, what if we put the sun in the middle? The programmers rejoice. The diagram is easier to maintain and easier to add planets, and management is very happy. I hope the moral of this story is clear. The model makes a huge difference. I've seen this happen before. Not this particular model, but I've seen it before. A team follows a software designer's rules, but when that designer sees the code, they think, wait, there's a better design than this. And then the team says, but we followed your rules. We've got short methods. We named everything well. What else could we do? And it's a bit like talking about how sharp your pencil was when you drew the lines, or how good your labels are on your diagram. One of the issues is that most software design advice is about the code. It's all about long methods or too many classes. It's all about the code. The advice fails to look at the system you're modeling. They never even mention that the thing at the center might make a difference, whether it's the sun or the earth. They just talk about what your code looks like. And I think that's the main problem. I believe that the quality of the model is a leading indicator of software design. So a better model leads to better software, leads to lower maintenance and faster features. Now, I guess I'm taking it upon myself to figure out how to make better models. I think it's stuff that people already know, that they're already doing, that you gain with lots of experience, and some people are better than others. And I want to figure out what they're doing and somehow write it down and systematize it and make it accessible for others. I'm still very early in that process. I'm going to introduce some ideas in this talk that are not 100% done yet. It all follows this one principle: iterate early while it's cheap. Another way to put it is, let's focus on the domain complexity and get it right before we add in all of the other stuff. Architecture, language, implementation, that all adds complexity. So let's work on just the domain first. To do that, we build a domain model. It's an abstract specification of how a small part of the world works. A small part of the world, that's the domain. Abstract means it leaves out unnecessary details, like what database it runs on or what language you write it in. And specification, well, that just means it has to be complete and correct. Domain models have these three parts. So at the bottom right, we have information. That's the relevant information that you need to capture. There's the operations on that information and invariants about what must always be true within the model. And we're going to go over those a little more. All right, at the risk of being too concrete, I've divided it up into three phases, the modeling process. There are phases that kind of go from more abstract to more concrete, and they're put in this order because, like I was saying before, if you iterate earlier while it's in an abstract phase, it's cheaper. Okay, so if you can learn something at the abstract phase, the cost of that learning is very low, but the value is still high. As you go into implementation, you start learning stuff. It's harder to change, becomes costlier to do that, to re-implement that learning. It's not a strict ordering of phases. You could also think of them as different perspectives that you can take at different times. You can move around in these phases. You don't have to move strictly forward. In the first phase, abstract, you work out what your operations will be in an abstract way. You don't implement them, you work from the signatures. we're going to use an example of an example domain of a pizza shop. Here is the kind of thing that you're working with in this abstract phase. So your operations are just going to be your function signatures. So that means just the name, the arguments, and their types, and the return type. And here I'm using Clojure. Notice I don't have any implementations. It's just the first line of the function, and there's no way to notate the return type, so I'm just going to put it as a comment afterward. And of course also the names of the arguments are implying their types, right? Because we don't have types in a static type in Clojure. There's no way to annotate that. If you're using something like Haskell or TypeScript or Java, you have types, use them. They're a very nice way of working with just the function signature. I've given 2 example invariants. You're going to have many more, but notice that these invariants are talking about the behavior of the operations, especially when they work together. And notice we're already starting to answer a lot of questions about the model with just these 2 invariants. And of course, you would have more than just these 2. An example of a question we are answering, this one is saying, this invariant is answering the question, can we have toppings with no cost, right? And this is saying no. The cost of a pizza is less than the cost of that pizza with a new topping T. Okay, so this is for all pizzas and all toppings. This will hold. So what this is saying is that toppings always add cost to the pizza, which is a reasonable assumption to make about your model. It's also reasonable to make another assumption. You could say that, well, they're less than or equal to, right? Some toppings are going to be cost 0. They're free. You could also say some toppings will reduce the cost of a pizza, right? So then you wouldn't really be able to say much at all about all toppings. And this one is saying that, well, if you add a topping and you remove a topping, then it's like a no-op. It's going to be the same pizza as before. Kind of makes sense, right? Okay. In this phase, for the information, I just like to keep it very minimal and just make notes about what concepts we need to track. So here I've noted that we need a notion of cost because we have this here. We need a notion of size. We need the pizza and the topping, of course. And then we have to have a quality for pizzas and less than for cost. Okay, and I could actually write them up in the operations, but I've just put them down here just as kind of like a general notes to myself. We don't want a data model yet. It's too early. We just want to work at this high abstract level with the operations and how they relate to each other. The primary measure of a domain model is fit. That is how well the model models the phenomena in the domain. So one question you would ask at this point to determine fit is, can I make every kind of pizza in the model that I want to make in real life? Okay, that's a question of fit. Then you can ask if it's simple. This is a much more aesthetic quality. You can ask, is it simpler with the sun in the middle or with the earth in the middle? What about with Venus in the middle? In terms of pizza, do we want to limit the number of toppings? Maybe we can solve that problem at another layer, a layer on top of this one. So we're just going to push that concern out from this model. And that's like a business concern, how many toppings you can have per pizza. So yes, you can imagine a pizza with 200 pounds of mushrooms. Is that reasonable to make? Probably not, but like I said, we're going to solve that problem in another layer. In the next phase, we build a very simple implementation of our operations so that we can run scenarios and learn from them. In this phase, the runnable specification phase, we implement cheat functions. So we take all of our function signatures and we build these in-memory representations of them, and we reuse operations that our language gives us, and we just do it really simply, really easily, whatever we have at hand. What we don't want to do is bring in stuff like a database at this point. You don't want to like make AJAX calls. It's too early to build in that kind of complexity. Just this something like very easy to work with that's well understood. Works in memory, so you can run it 1,000,000 times if you need to. All right, and our invariants, we're going to take them and turn them into tests. So here I've made a property-based test where I'm generating pizza. So, you know, for all pizzas and all toppings, if we add the topping and then remove the topping, it's the same pizza. Okay, same invariant as before. And then in the information, we're going to just apply basic data modeling, which is a whole book in itself, but we don't have time to get into that. Okay, so you'll learn a lot at this phase. You can even try to build a pizza. You can tweak the spec if you learn something like, oh, I wanted to build this pizza and I couldn't figure out with the operations I had how to make it happen, how to build that pizza. You might learn that, and then you can go back and modify your operations and change the invariants, etc. Okay, once you've learned all you want to learn from it, you can start to add other non-domain concerns. So just make sure they're still abstract. I put it in this phase. It might be you could call it a different phase, but in this phase or this part of the phase, you want to add abstract non-domain concerns. So if you want to run it in the browser, you already have that in mind, then you know you're going to have to do AJAX calls with the server. That's very concrete. AJAX calls on the server, that's concrete. But asynchrony, now that's an abstract idea that you can start building in and making sure it works without going down to the concrete level. Same thing with concurrency. You don't know if it's going to run on multiple cores, but you can build in concurrency, and you know that things might need to change over time, so you build in mutability. This is the phase where you might say, well, let's use event sourcing. It's a very abstract idea. It's going to just be a log of events. It's abstract enough to fit into this phase. You want to think about all this stuff now before things get complicated and you have to deal with actual deployments and things. Okay, then you have the implementation phase. You take your model and you build it for real in your language and architecture. You have tests already, so it should work for the first time. Well, yeah, right, I'm joking. But at least you can know how it fails, right? Because you have all those tests. And you also have the runnable specification, which can be like an oracle to tell you how your real system, your real implementation should behave. So you can build tests using that. Okay, in your tests, there's many ways to implement invariants. It really depends on your language. If you have types, use those. A lot of language features have their own built-in invariants. For instance, the synchronize keyword in Java means only one invocation of a method at any one time, even if it's invoked from multiple threads. Tests are good, especially property-based tests. And data structures can maintain invariants. For instance, sets don't have duplicates. You can also do runtime checks if you have to. And your brain can work out simple invariants too. You can write down proofs. You can put the invariants in documentation. Just remember that invariants that aren't run from your pipeline, your deployment pipeline, they don't work when you're not there. So you have to make sure to get them right. Okay, there's a lot to say about data modeling, but I want to bring up the idea that you can actually analyze the domain independent of the language features you're going to use to implement that domain. And these are some of the things that you'll see in your domain. So alternatives mean it's a choice among several possibilities. So for instance, each ingredient is a choice: mushrooms or peppers or spinach. Okay, combinations mean choosing many things, and so they have a kind of multiplicative effect when you count how many possibilities there are. So the pizza can have several ingredients, so it's a kind of combination. So if you have 3 ingredients and 10 ingredients to choose from, your pizza has 3, there's actually 10 choose 3 ingredients, possible pizzas to make, modulo the pizzas that are the same because you chose them in different orders. Okay, each ingredient has a cost, so you're mapping ingredients to a dollar amount, right? So that's a mapping. And of course there's quantities like the dollar amount, names like the toppings are going to have names, and then collections of things. For instance, an order is a collection of pizzas. You can look in the domain and find those things, and then later you map them to features in your language or database or however you're going to implement it. So when you're doing that mapping, you have to take into account one more kind of high level issue. How often does a thing change? And I'm calling that volatility. So if a thing never changes, you can just hard code it. Okay, I'm calling that closed. So we might bet that we will always have 3 sizes of pizza: small, medium, large, and so we code them that way. We just code it as, there's these 3 choices. We use an enum in Java or something like that. And if we ever find out that we're wrong, like, we want a 4th size, like an extra large, then we just have to modify the enum. We have to go change the code and do a new release. And it's rare enough that we're gonna just eat that cost. Okay, it's not that big a deal. And we're calling that closed. You just have to change the code. However, we know that we do different discounts monthly. So we don't want to have to modify the existing code to add new types of discounts because that could introduce bugs. Instead, we want to be able to add new code without touching old code. One way to do that is to implement a subclass in Java. In Clojure, you might use multi-methods, and I'm calling that open. And then finally, we know that ingredients can change daily. You can run out of mushrooms one day, or you can find a new vegetable that you want to make as an ingredient in the market, and it's only available, this week. So we don't want to do a release for that, a daily release just to say that we ran out of mushrooms. We don't want to go through that. So we want to make them runtime values, first-class values that we can store in the database, and we can modify it at runtime. All right, there's a ton more to talk about, but I think that this gives a pretty good taste of it. I hope it whets your appetite. If you would like to follow along with my exploration of these ideas, please listen to my podcast and get on my newsletter. I discuss these ideas there. I'm also interested to hear your thoughts on domain modeling. Thank you very much.
All right, that was wonderful, Eric. So we are going to do a Q&A panel with Paula and Eric. Are you both here? Cameras on, mics on.
I'm searching for Paula. I think I got Eric. Oh, here's Paula. Fantastic. Okay. And Eric, I enabled an Eric as co-host. Sure, let's see if it's the right Eric or not.
Okay, I also see Paula here. While we get that set up, I would just like to remind people that at 17:30 UTC, we're going to have an interlude of lightning talks. There are 5 slots at 5 minutes each. 2 of them will be taken by the community leaders, and 3 are still waiting for the final vote in the Lightning Talks channel. So if you go on over to the Discord channel talking about Lightning Talks, we'd love to hear from y'all. All right.
Yeah,
I'd also like to.
I see the right Eric. Just give me a second and see if we can get it. Yes,
Sure.
Eric, can you hear us, Eric?
I hear you. Here I am.
Fantastic. Thank you for coming in. So we have both of them. Jordan, do you want to go with the first question?
Sure. And I will remind the audience members that they can post questions in the Q&A Discord channel. We love to see your hand raised. We'd love for you to talk directly to the speakers or just post in the Zoom chat. So we will start with an icebreaker question for Paula. So I've seen that in celebration of Clojure getting the Clojure Java math namespace, you've ported it over to ClojureScript, which is super awesome because we love to see you doing more ClojureScript stuff. You said that unfortunately you've run into the problem that the JavaScript math isn't as capable as the Java math though. So you've had to re-implement a lot. What was the toughest part of doing this?
The IEEE remainder function. There's a there's a function for dividing one double 64-bit double by another one and then finding the remainder value from that as accurately as possible. And that was really tough to get right. The code was available in C on the JDK because it's released as GPL. Anyway, I ported it into JavaScript, and then once I had it working right there, that helped me get it right in ClojureScript. There's a lot of bit operations, and there's expectations of having access to different word sizes and you can change the pointer types. And this is what C was doing internally. And the way I had to make that work in ClojureScript was really quite difficult. But yeah, I've got it working, and yeah.
Okay, let me do like the icebreaker for Eric as well. And we want to ask, what is your favorite dish to cook and why it's not cookies?
Because I would eat too many cookies. That's the answer to the second question. What do I like to cook? I like to cook gumbo. I really like to cook gumbo. It's fun.
There
it's a
you
nice
go.
process.
And what are the ingredients for that?
Well, first you start with a roux, which is flour and an oil, and you toast the flour in that. Gumbos have a pretty dark roux. If you're used to making a roux from French cooking, it's much darker, and so it kind of has this exciting aspect of testing your cardiovascular health because you can burn it, and you want to take it right up to the point before you burn it. So it's kind of a game of chicken with your flour. Then you can put whatever you want, but I tend to put in okra. Gumbo is one of those kind of like empty your fridge of all the little ends and bits that you got left over from other things, and just throw it into a big soup.
Well, hopefully next time I'm in New Orleans, you will cook some for me. I'm holding you to that.
Yeah.
So we have a hand raised, Egg Davis. Are you here, Egg Dave? Mr. Egg? Let's see here.
I think it was my fault.
No blame.
Now I can unmute. Sorry about that. Yeah, I asked this on the Discord, but then I was reminded that you all are enjoying questions being in person. Eric, I was thinking recently about causal loop diagrams. I don't know if you've run across those.
I just clicked on the link that you shared. I have not come across them, so I'm gonna check them out.
Yeah.
Are these are kinds of like systems analysis feedback loop kind of things.
Exactly. Yeah. And I mean, mostly I've seen them as like ways of exploring physics stuff. But just recently occurred to me that it could be really interesting as a way of modeling business domains.
I'll check them out. Thank you so much.
Okay, so let's get Paula back in here. Ray on the Discord asked, Paula, can you tell us something about your graph database, Asami? What was the motivation behind it and what sorts of problems it's a good fit for? I would like to add, how long have you been working on it? And tell us a little bit more about the name.
There's a lot of aspects to that question. I had been working on a previous RDF database called Mulgara for over 10 years. That was written in Java, and I lost interest over time because it was written in Java and I was into Clojure by that point. I had an idea of re-implementing in Clojure, but hadn't really got to it until an element that I'd written for Mulgara was a rules engine, which does this bottom-up evaluation for data log. And I had this idea that I could redo that for any graph database if I just hid the database behind a protocol. So I tried this with Datomic and showed my boss at work, who said, you should try this for at work because we need to do some inferencing. And he didn't like the idea of working with a commercial system. He said I could take the rules engine, which was open source, and do, I needed to talk to an open source graph database. We weren't aware of DataScript, and so I started doing something in memory, and that became Asami. And then I kept adding features to it in my own time, including the storage layer, which I did last year during a pandemic. And it grew a lot from that. So it's like Mulgara, but it's entirely in Clojure, and it's it's taken on a lot of the new indexing ideas that I've had in the last 20 years. As for the name, we had a number of projects at Cisco where my manager was really into Avatar: The Last Airbender and the sequel Korra. And so a number of projects were named after characters in those shows. Well, the character Asami was Asami Sato. While some of the other characters had these like superpowers with the bending, she didn't have anything like that, but she knew technology and she would build things for herself so that she joined in with her friends. And I like that idea because you know, I didn't have a graph database, and I built one myself.
Yeah, that's great. That's one of my favorite fun facts about Asami. Let's go back over to Renzo to hear more from Eric.
Yeah, so I have a question for Eric. Do you think that the traditional roles found in most agile software companies are equipped to handle the domain-driven model that you are advocating for? And could we need to add additional supportive roles between product managers and technical leaders?
Wow. I have not thought much about how this fits in with the sort of black box ticket machine that we've created with the current agile system. I'm not a big fan of the way I see agile working, so I'll put it that way. What I see is that business people, project owners or whatever, product owners, whatever they're called, just add tickets, and then the programmers just do the tickets. And there's very little, because it's easier, the asymmetry of it. The programmer is working longer on the ticket than it took to write. So it's always easier to get a longer backlog than you can actually finish. And so the programmers never really have time to get a global view of the tickets coming in and like, what model are we actually making? And so I don't know if it would fit into Agile at all to say like, hey, let's take a break and do some design work and some sketches, and like maybe all these tickets don't make sense anymore.
So I will elaborate, Eric, because that was actually a question from me.
Okay.
So I think that traditionally we have like the product people and they know all the product stuff and they don't care or know about the code. Then we have all the code people and they know all the code stuff and that's all they care about. But not a lot of companies have like the glue holding them together. And a lot of times, software engineers or, customer success people will try to fill those roles. But I guess I think your domain-driven model kind of advocates for the requirement of an additional role in a company that's like between understands technical but isn't leading technical and understands product, isn't a product manager, but can help those two.
So I mean, this is something that I don't think I'm prepared to discuss fully, but there is a great book called The Inmates Are Running the Asylum. And it's about the problem of just having these two roles of like business and dev. And it argues for a third design role because the business they're really trying to maximize profits, right? So more income, less cost. And the programmers are kind of trying to make their job easier. Do the job, but do as little as possible. And there's no one advocating for the user, really. And the user is the kind of the person that the model has to serve ultimately. It does help the programmers, right, by having it if you have a good model, the model that actually serves the users, it's easier to write code that serves the users. If your model is different from what the users actually need, then you're going to have to write all these complicated code to like adapt it all the time. And that's what's going to lead to all this complexity. So I think that that's a good direction, like having this third role who's kind of advocating for the user. And then that lets you have some sort of team of maybe a special team of 3 stakeholders who can come together and talk about the model outside of the code. I think that's another problem in Agile is that the programmers are asked to do both the low level, like let's make these tickets happen, and the high level sort of evaluate these tickets and like understand the context and switch between that really quickly. And so you never have you're going from this like engineering, like just get it work, like whatever it takes, get it to work. And then you have to switch to wait, maybe we don't want to do this. What's the context? Like, and that is very hard for your brain to do that. And I've seen it happen in companies where it's like a programmer will be coding up to the wire. Now we have a meeting to like evaluate these tickets. Like your brain needs an hour at least. Maybe you even need like a week if you've been doing coding a lot. So I find that that's another problem. Like there's a human aspect, a psychological aspect missing from Agile.
Yeah, the cost of context switching is certainly a cost we underestimate. Okay, going back to Paula, we have a question from Jacob on Discord. He says, comparing the performance of retrieving a whole data entity, for example, a person, from an RDF database versus an RDBMS, is the former significantly slower because it has join on each attribute, or is it just as fast because all of the attributes are stored next to each other in the EAV index?
It's a little bit slower, but in general, your bottleneck is in is in your storage. And these days that's often as likely to be in the cloud as it is locally. And so the work to bring those things together into a local entity is trivial in comparison to waiting for this stuff, even coming off disk. If you have a lot of things cached, yeah, there's a small performance cost there, but generally when you retrieve this data, it'll usually be co-located. You can bring it in, you can restructure it and return it. If it's in memory, it'll be a little bit slower. And if you run it through, say, Criterion, you'll see that difference. But in general, you're going to see records come in and be restructured as an entity at a similar pace. It's the tertiary storage, which is the real cost. And yeah, locality is normally all right when it comes to that tertiary storage.
So we can perhaps take the next question from Felipe live.
Hi, am I on the mic?
Yes, all good.
Hi. This is a question for Eric. Hi, Eric. Great talk.
Thank you.
So I want to ask a bit about the process, because what you've described is obviously a process by which you come to certain results. But a big part of how this thing ends up you having the need for this process is the fact also that there is a disconnect. The people that have the model, maybe they're not talking all the time with the people that don't have the model in their heads. So even in the example you gave, it's like a multi-step process by which at some point someone realized maybe we should look at the model. So my question is how do you actually, in what ways have you had success? Actually putting down this model, collaborating with other people on this model, and actually iterating over this model in the times that it's actually important to change it and update it.
So these are all really good questions, and it's a little bit outside the scope of what I had in mind. But it's a really good question. So now I'm thinking maybe I need to talk about it, but I'm also thinking maybe I focus too much on process and not enough on the sort of underlying groundwork of what you can even do at a domain model level before, and at an abstract level before you get into code. So thank you. This is really good information. So but I do want to answer your question. So what you asked about what successes I've had. So there are successes when I'm working on my own, definitely I will realize, oh, this model needs to be different. And then I go back to a more abstract level and I can work there. Of course, I'm working on my own project. I don't have to answer to anybody. In terms of on a team, I've seen it work in the small. So maybe you realize that a small part of your domain could be different. So for instance, maybe you're doing some kind of user interaction in a GUI, and you realize, oh, if we just kept a log of these instead of mutating stuff in place, that would make all these things that we have to do easier. And so then that's a small place, and the GUI code changes so frequently anyway, no one's going to be bothered if you'd change a bunch of callbacks to do something different, right? In the large, I think I think that one of the jobs that I need to do is to make it apparent make the argument for how valuable this can be, that it can speed up your development, certainly, but it can also be, because software is basically running businesses now. Like the business, how it works is like in the code. I think that it can give you a real business advantage apart from just like the speed of development. I think that it can give you a clearer view of, like, it can give the business, the whole company, a clearer view of the system that they're working with. And I like to use this example of like double entry bookkeeping. It's like, can you imagine a bank with a different model who's just like flailing all the time because they're not keeping books that well, and then someone comes up with the bank that comes up with double entry bookkeeping is like beating them, and it's simply a change in model. The whole business is based on a different model. It happens to be encoded in their information system, but that's happening more and more. And I think I need to come up with find some real world examples where someone with a better model actually succeeded in competition because the model was different. And it wasn't just, oh, we were swamped by technical debt. It's more like the model made their business better. So thank you so much, Felipe. I hope that answers it. And we can talk offline. We can talk in the chat if you want to go deeper.
Sure. Let's do that. Thanks again.
Thank you, Felipe. Up to you, Jordan. Any more question for Paula?
Yes. So I'm sure there are many people that are looking for opportunities to contribute. And I'd like to give you a chance to a space where you have next steps you'd like to suggest to people where they can learn more, perhaps previous talks you've done in the past, good starting points for people to learn more about Asami and what you're doing.
I've written a lot on the Asami wiki. I've tried to put a lot of effort into like describing each of the different elements, how to go about using them, what the structures look like. There's even a number of pages on what the architecture is and how things interact. It's not perfect, but there's only so many hours in the day. Another place to go is Datomic. They have extensive documentation. They have a very fast-moving project and a lot of people working on it. So I have seen the docs get out of sync with the project on occasion, but it's generally quite good. So these are two really good sources. Well, I like to think that the Asami source is a good one. I put pictures in there and things, but while Datomic doesn't present itself really as a graph database, and it's not particularly strong in that way compared to some which are out there, it is a graph database and you can use it as such. So in general, looking for graph database resources can help. But I think working through the Datomic documentation is probably your best bet. And then if you learned about graph databases, you could build on top of that. Was there a second part to that question?
I think you answered it.
All right.
Thank you.
So let's see. We are approaching the end of the slot, but we should have time for another couple of questions, I believe. So for Eric, we have, well, I can't pronounce that, something King. Eric, is there a standard timeline, for example, 2 weeks to a month, during which modeling must mature once the project requirements are completely understood? This is the first part. And then there's a second part. Eric, would you describe, or to what degree, to the idea that a design be centered around areas of volatility? Thank you. So the first one, Eric, again, is to during which modeling must mature? So what is the period where modeling must mature once the project requirements are completely understood?
Right. Again, this is a process question. And now I'm very much regretting talking about process. It's not like I don't want to talk about process as much as it seems the questions are implying. I want to talk about stuff like the sizes. That's an alternative. You choose one of these three sizes, and that is an abstract thing that we can do before we jump into code, right? And that I want to catalog all these choices, these possible ways of modeling different things, and then also talk about how those can be implemented in code. So, Clojure has these 7 ways to implement alternatives, and Java has these 3 ways. And, I want to do stuff like that. And so it's much more about sort of the Lego bricks of domains, of domain models, how to analyze your domain to find what those things might be, and then how do you translate that into a language. The idea of process, like, have a 3-week sprint and then write down all these things on sticky notes, and like that, I don't think I'm that good at that, so I don't want to touch that. The thing about whether to design it around areas of volatility, I think that's very important, and a lot of architects, software architecture experts talk about that. How this is one of the key areas of key insights of David Parnas in talking about modularity, is you want your modules to encapsulate this volatility. An example of this is, the wrong way to do it is you break up a house thinking about the areas of functionality. So you think of stuff like, there's the kitchen, that's where you make your food. There's the bathroom, there's the bedroom. And so you think of those as the modules, and then you connect them together with doors, right? But really, when you look at your house, the modular stuff is different. If you look at the volatility, you say, wait, we need to be able to plug in different appliances at different times, right? You don't want to build in, they used to do this and they've learned it's a bad idea. Like, you build in your vacuum cleaner system into the house. No, you want a modular vacuum that has a plug that's also modular, and you can, the different, that's the interface. It's like a standard interface that allows any module to be plugged into the house. And then you have your plumbing, right? And that's a different module. You want to be able to put different fixtures in without ripping down the whole house and changing all the walls, the plumbing in the walls. So looking at stuff in terms of what changes, your furniture, it's very modular. You can change out your furniture. You don't have to touch the house. You don't have to rebuild anything. So to look at the volatility, I think is one of the first things you should do. And that's kind of just architectural advice. It doesn't speak so much about the domain model, the model of the house. I brought up volatility mostly because when you're implementing it, you have to make this choice. There's different ways to implement alternatives. You can make an enum, you can subclass an interface, or you can make it values that are like strings that you can put in a database, and all of them have their uses. There's not one that's the right way to do it. But how do you decide between them? It's all about volatility. And I think that's something that's just not discussed that much. I think that there's a tendency to say like, well, let's just subclass everything. And enum is, oh, that's just for like simple things, like simple strings that instead of using constants. Like, I think that that's the wrong way to look at it. You should look at it much more like you have to change an enum if you want to add or remove something or change anything. You actually have to go open that code and change it. Whereas a subclass is open, you can just add a subclass. And then the runtime stuff, well, you just add a new row in the database. Like, you don't even have to touch your code. So yeah, that's the answer to that.
Okay, great. So we are getting close to our break before our next session here. So we have one last question for Paula from Ray on Discord. And Ray says, when I see data log, I think of Prolog and logic programming. Is there some synergy between Datomic and core.logic? Can the two be used together to solve more interesting problems than just data retrieval?
I haven't done a lot of work with CoreLogic. I do know that David Nolan put some effort into connecting it to the asserted statements were connected to a database as opposed to simply being in memory. I'm not sure that that would be the best approach to handle a lot of scaling issues. The sorts of rules which I was describing that Datomic can use, I think will be much more performant, but it's harder to apply than Datalog, I think. And I mean that connection to logic programming and Prolog is quite real. It's specifically designed to be like Prolog, but over a corpus of data as opposed to a space which needs to be searched all the time. There have been numerous attempts in like the last 40 years or so of trying to integrate the two. Certain things have been done that like in like this top-down logic programming where solutions are searched for, the way that that Prolog does, the way that systems like Mini-Cameron or CoreLogic do. These can solve certain sorts of problems while Datalog can't really approach those. However, Datalog has these restrictions on it which let it work really, really well with databases, graph databases especially, I think. And while there's similarity there's also things which one can do that the other doesn't really have a very good handle on. Personally, my experience has been that logic programming hasn't required the scalability that databases provide us. And well, I mean, when I say logic programming, the complex stuff that CoreLogic and that Prolog are really strong at doing, I haven't seen them applied to really large corpuses of data to great effect. While if you can restrict your logic language down to what can work in Datalog, that works against databases exceptionally well. There hasn't been a lot, there are a few cases, but there haven't been a lot of instances where you want that processing power of, say, Prolog or CoreLogic being applied to massively scalable data. And, you know, the fact that those two don't often need to intersect has been fortuitous. But yeah, so I know Datalog can be put over the front of a database, and David Nolan has done that. Not Datalog, sorry. CoreLogic can be done over a database. David Nolan has done it, but I haven't seen it being picked up and used anyway.
Okay, great. Thank you, Paula. So we are at the end of the Q&A panel, and we would love to thank Paula and Eric for speaking today. And if you have any more questions, Paula and Eric are both very active in the community. Please reach out to them on Slack or email, and I'm sure they'll be happy to answer any questions you have. All right, we're going to do
Let me just add about the preparation of the lightning talks, which is soon approaching. So we have a selection of 3 lightning talks. So 3 were proposed, and we're picking all of the 3 up. If you have any more votes you want to cast, is still available, or you want to get one proposal in, you can still get your proposal in, and assuming is highly voted, we'll arrange for that. So stay tuned for the lightning talks, and yeah, enjoy the break. Hello and welcome back to another sections of talk of this second day at Reclojure 2021. So in this second from last block of the day, we are having Ashima and Christopher. So Ashima is a programmer with a degree in pharmaceutical sciences, an interest in using computational techniques to draw helpful insights from biological data led to her foray in computer science. She has since been working as a software engineer and loves dabbling in all things tech. And she has contributed to various projects in the Clojure data science ecosystem. And so we are being joined in this talk with Ashima, also from Daniel Zlutski. I think I never pronounced his last name until now. So let's see if Daniel is also with us, and I might need to co-host him. There you go. Daniel, are you with us? We'll give him another second or two. In the meanwhile, I just wanted to inform you that the lightning talks are lining up steadily now. So we have a program, and the lightning talks will be at the end of the panel of this block. So we'll be ready for that. Daniel, are you available now?
Yeah, can you hear me okay?
I can't hear you. It's just me, or maybe it's just me.
I can, yeah, loud and clear.
Yeah.
Yes, yeah.
Thank you. Hey, yeah. So Ashima is having some power cuts on her side today. So she asked me to briefly talk at the moment, and then later she will be able to join. And I hope to give some context about this talk that Ashima hoped to give. The talk that Ashima will give is about VizCLJ, a new data visualization library that is focusing on beginners mostly. And what we hope to talk about is a little bit of the background of why this library VizCLJ is coming along and what was needed. And I think Ashima will talk about that, but maybe now we could mention a bit of the other libraries which are kind of well known to some of us for data visualization. Please stop me if I'm talking too much, but I guess that there are two libraries called Vega and Vega Lite, which are JavaScript libraries. And Clojurians seem to love them very much because they match the Clojure approach of using plain data structures to describe everything. And then many of the Clojure tools for data visualization, they use Vega and Vega Lite specs to specify data visualizations in a declarative way. And then there are a few Clojure libraries that are adding many ways to create Vega and Vega Lite specs. And one of them is TechViz, for example, by Chris Neuenberger, which is just a nice collection of ways to create very nice and useful plots of these kinds. And another one is Hanami. And I thought maybe we could just for a few moments see what Hanami is about so that we get a feeling of this. Is it okay? Maybe I'll share the screen for a moment and we'll just peek into Hanami, a library by John Anthony. I guess you can see my screen. I'll just move some fingers around so that it is easier to see. And right, so you see we have some data here, and that is just a little table of data, right? X and Y, and these rows, they are just Clojure maps, right? A sequence of maps. I generated them using this tablecloth library that we saw yesterday, but never mind about that. We just have those, like this vector of maps, right? A very plain data structure, and we want to plot it. So here is how we can do it with Hanami, and let us do it and then see what it means. So you can do something like that. You can use the Hanami common namespace, and it has these functions transform. And transform allows you to pick a certain template. So let us pick a line chart, for example. And then you just need to add a little more information so that this template will be filled in with our information of data, for example. So we can say, for example, data, and give it the rows of data. And what we get is this data structure, which is a Clojure data structure corresponding to a Hanami, to a Vega Lite spec. Vega Lite is this one of those JavaScript libraries following the grammar of graphics culture. And I hope, in the Q&A, probably you will discuss this a lot. And so here, we got this spec, and depending on what tool you use, you can tell it somehow that this is a Vega spec. And here I'm using some library called Kindly that is saying this thing is of kind Vega. And now we can plot it. And you see we got this random walk in the plot, which is just plotting our data using a line chart. And the idea here is that if you were writing any of the other data visualization libraries who are using Vega, you would need to write so much more. And Hanami allows you to be very much concise. And it is all plain data going on behind the scenes. So, you can add more substitutions here in the template. For example, we can have another background color like purple. Right, and then you see we get another thing, and so it is all plain data structures. That is the Clojure joy. And you see now I printed this template structure, which is just a plain data structure. And this Hanami library is so powerful because it actually implements in a very tiny, nice way on top of Spectre. It implements, in a sense, the lambda calculus in a way that allows you to create complicated maps by templates and defaults. So that is Hanami, and that is the kind of the background to what Ashima is going to show in a moment.
Fantastic, Daniel. Thank you very much for the little introduction here. I think it will be helpful. And so we can start with the Ashima presentation.
Hi everyone, this is Ashima. Today I'll be giving a talk on VizCLJ, which is a data visualization library for beginners. Before we start, a little bit about myself. I work as a software engineer and have been dabbling with Clojure since the last 1.5 years. I've contributed to some of the libraries in Clojure's data science ecosystem, mainly Notespace and tablecloths. In today's talk, I'll be covering the following. We'll start with a brief overview of Vega Lite and Hanami. These are the underlying libraries that sort of form the foundation upon which Viz is built. We'll then cover the basics of Viz and see some example plots. Following this, we look at some of the documentation and error handling that we have in the Viz library. We'll also take a look at some of the problems that we faced and the lessons that we learned along the way while building this library. Before we begin, on a side note, I'm using a tool called Notespace to render my namespace into this notebook format. It's a wonderful tool and you should definitely check it out. I've added a link here in case anyone's interested. So let's begin with some setup. Here I'm importing the libraries which I'll be using during my presentation. Along with Notespace, I'll also be using this tiny library called Kindly to specify how I want the different elements to get rendered on the page. I'll also be using tablecloth for generating some data sets. Apart from this, I've imported Hanami so that we can compare its syntax with that of Viz. Our focus while creating this library was to build something which would be easy to use, have a consistent syntax, have excellent error handling capability to help users debug their code, and have extensive documentation. The reason why we chose to focus on these issues was because upon discussion with beginners, we found that these were the top problems faced by them while trying to learn a new library in Clojure. I want to make it very clear here that Viz is not a replacement for Hanami. It's just a starting point for people looking to get their feet wet and explore Clojure's data science ecosystem. Once they feel like they've developed a basic understanding, we encourage them to move to Hanami in order to be able to create more customized and complex plots. Let us now look at how Viz works under the hood. It basically generates a map with all the values that we pass within each function. This map is then converted to the VegaLite spec by Hanami within this Viz function. One thing to note here is that we can change the order in which we call the different functions without having any impact on the final result. For example, I could call type after specifying X and Y, and it should still work perfectly fine. Since all we are doing is essentially creating a map, we are free to change the order in any way we like. Let's jump right in to see some examples. Here we are using different data sources to generate the visualizations. These include from a local file or from a file on the web. We can also use a tablecloth dataset as well as a sequence of maps. You'll notice that in case our data has columns named X and Y, it picks those up by default without us having to specify anything. We also have the ability to specify color. Another thing that I would like to mention here is that you can use keywords instead of strings while passing parameters into the function. This syntax might feel more familiar and comfortable to seasoned Clojureans. For those of you familiar with Hanami, you might be aware of the usage of substitution keys. These are the default values which are used to generate templates. They may be replaced with values of our choice depending on the customization that we desire. While using this, we have provided the ability to tweak and play around with Hanami's substitutions. This is key to allowing the user to start exploring and learning about Hanami and its features while using this. In this case, we are using the key background to change the background color of the chart from the default floral white to this grayish color. You'll have to make sure to do any substitutions before passing your map into the final Viz function. Another option that has been provided is the ability to tweak the VegaLite specifications which get generated upon calling the Viz function. As you can see in this example, we are changing the background color within the VegaLite specification. Apart from being a great way to learn the underlying libraries, this way of tweaking Hanami and VegaLite can be leveraged by advanced users who are using Viz but would like to have the ability to generate charts with features which are currently not available. We also have the ability to transform the data within the Viz pipeline. Consider this example where we have data having numbers with different orders of magnitude. The scale seems to be off in this case. We can transform the data using log to linearize the situation. Let us now look at an example of a histogram. One point of note here is that even though VegaLite offers us the ability to perform statistical computations on its end, we are choosing to instead calculate the billing data at our backend and then send that computed data for generating the plot. We'll look into this choice of performing the computations in the backend in more detail when we discuss the design decisions. Another interesting API that we have is for generating multiple layers of charts. In this example, we are passing a map with all the required key value pairs, and the layers API is generating a single layer using the data. We also have the ability to pass Hanami substitutions within the map as seen in this case, where we are changing the color of the mark. We can create multiple layers using the same dataset, like in this example, where we are creating a point chart and a line chart using the same data. Another feature of Viz is the ability to pass Hanami templates as the type of the plot. We can also create different layers using different datasets as seen in this case. Another interesting functionality that we have is the ability to generate regression lines. In this case, similar to histograms, we are choosing to do the calculations at our backend before using the data to generate the Vega Lite spec. In future, we hope to add the ability to generate regression curves as well. Let us now look at error handling in the Wiz library. Currently, we have a very rudimentary setup for catching errors, which covers only the most basic types of errors which may come up. This is an area we are planning to expand on in future. As you can see here, we have created a macro which removes all the stack trace and confusing error logs and instead prints out a concise error message which serves to highlight the exact issue. So for example, if the user has typed an incorrect file path, we are throwing an error informing them that the file does not exist. Another example that we have here is of the user trying to plot a column which does not exist in their dataset. In this case, we notify the user that the column which they are trying to visualize seems to be missing. The last example that I have here is of creating a plot without specifying the type, like maybe point chart or line chart or bar chart. You can see the appropriate error which gets thrown in this case. Moving on to the documentation part, we are currently working on providing users with mainly two types of documentation. The first is API docs generated using a tool called Codocs, which automatically creates documentation from Clojure source code. This is helpful for people wanting to understand the use of each API or looking to explore the different parameters that can be passed to each function. The second type of documentation is tutorials, which involve a little more hand-holding. These are targeted at new users, explaining the entire setup process and giving a walkthrough of some examples. We have found that a combination of both of these produce the maximum results when it comes to adoption of libraries. Easy to follow tutorials are an attractive option for beginners, and once they become familiar with a tool, they can begin exploring the API docs to understand the nuances and possibilities of achieving more complex results. A key part of our development process was continuous interaction with the users. This helped us get feedback from them right from the get-go. We would showcase our progress during the routine study groups with Cycloge, which Cycloge organized, and would then hold an open discussion to hear users' thoughts. This helped us make key decisions and made sure that we were staying true to our goal of improving users' experience with Clojure's data science tools. Another advantage of having people experience our libraries at such early stage was that as developers, it helped us make decisions regarding the priorities to focus on and also made it easy for us to pivot in case of a misstep. This would have been a lot harder for a much more established library where a lot of effort has already been put in. While creating Wiz, we spent a lot of time exploring libraries in various other languages which use Vega under the hood. These include Altair in Python, Vega Lite API in JavaScript, and ggwiz in R. One of the ideas that was picked up from these explorations was to use a pipeline instead of a map. This would definitely mean losing some of the flexibility that a map provides, as seen in Hanami, but would make our syntax much more simpler. More number of functions, as in the case of a pipeline, would also give us the ability to add checks and error handling at each point. A challenge that we have faced continuously throughout the development process is regarding the trade-off between simplicity and customizability. This is a challenge that almost all libraries face at some point or another, and depending on their goals will make a decision that best satisfies their target audience. In our case, since Wiz is being designed specifically for beginners, we chose to focus on simplicity. But we did not completely ignore giving the users the ability to add their customizations. Wherever possible, we have given the option to tweak Hanami substitutions or the Vega Lite spec. This we feel is enough to cover most of our use cases. Another major decision that we made was to have various computations happen at our backend instead of leveraging Vegalite's features. This was inspired by R's ecosystem, where all the statistical tools can be freely used in transforming data while creating plots. We are trying to achieve something similar to that by using Clojure's own statistical libraries to perform the computations. This provides us more flexibility while transforming the data and also makes our code much more efficient since less data is needed to be sent to Vegalite to generate the spec. Going forward, these are the areas that we are planning to focus on: staying flexible and evolving to support more use cases, adding backend side transformations similar to what we saw in case of histograms and regression layers. We hope that this will give users the ability to enjoy the whole of Clojure's statistical computing ecosystem. Then continue to hold experimental user sessions to learn more about the user's experience and have the results from these shape the future path. More statistical error handling using some schemas like maybe Mali. We might consider adding video tutorials for people preferring to watch rather than follow a document's instructions. We might also consider integrating with specific libraries for domain-specific visualization grammars. For example, grammar for visualizing machine learning models or for visualizing time series. That's all from my end, folks. But before we end, I would like to take some time to thank the following people without whom this talk wouldn't have been possible. Thanks to the Reclosure organizers for providing me with this platform to showcase my work. I would also like to thank Daniel, who is the co-author of the Viz library and whose help was integral in planning and creating today's talk. I wouldn't have been able to do any of this without his constant help, support, and guidance. I would also like to thank everyone who attended the Cycloid study groups and gave valuable feedback, which helped shape the direction of this library. Lastly, I would like to thank all the maintainers of the libraries, which served as the foundation upon which Viz could be built. And finally, thank you to you all for listening to my talk. Hope you found it useful. Have a great day. Bye.
Thank you very much, Ashima, for your heroic effort to put together this talk. We know it was a lot of effort for you, so thank you very much. So we are going to have a quick 5 minutes break before the next live talk by Chris Small, who we are searching, by the way. So if you see him, if you see a Metasaurus, please send it to the talk, to the Zoom. Thank you. So hello and welcome back. So we need to do a little change in the program because we can get Christopher Small on the call. So what I suggest is we go ahead with the panel. So anticipating a little bit the panel that was scheduled in about 25 minutes from now, and see if we can get Christopher on the call. Then we'll go ahead with this talk. For this though, I need to understand if we have Shima available on the call, and if she is, we can start from that. Let's see. I think I saw him before. Yes. Okay. Sorry. I need to make her co-host first of all. Ashima, can you unmute yourself if you are available?
Hi, can you hear me?
Yes, I can hear you. And yeah, thanks for like being ready unexpectedly, a little bit ahead of time, but that's nice to see you crystal clear. So we'll, as I said, we're going to anticipate your like the panel at the end of the talk. So making a few questions to you before we until we wait to see if Christopher is on the call. That I see him now, and if he can, join the call and tell me if he's able to give the talk or not, then we'll take it from there.
Yeah, hi.
Hi,
Sorry, I'm a couple
Chris.
minutes late here. How's
Yeah,
everyone
no
doing today?
worries. So is it okay if we go ahead with your talk then?
Yeah, let's do it.
Okay. So Ashima, thank you very much. And maybe we already tested that you're able to connect for later on. So stay on the call. Don't go too far.
Yeah,
And
sure.
we'll go ahead with the questions with the panel at the end of the of Chris' talk as expected. So about Chris. So Chris is a math geek turned software engineer and data scientist. About a decade ago, Clojure graced Chris with the miracle of simplicity. That's nice. And he has been passionate devotee ever since. He is currently the research director at the Computational Democracy Project, a nonprofit which seeks to make governance a better reflection of the public. Will be using
Of the public will.
Of the public will. Sorry,
Yeah.
of the public will. It will by using data science and machine learning and Clojure to map out the synthesize the opinion landscapes around complex issues, helping people better understand the other side, overcome partisan divides, and find consensus. That's a nice introduction that I badly misspelled a couple of times. Sorry for that, Chris. So
No problem,
I'll let you the stage and you'll take it from there. Thank you.
Yeah, actually, I mean, I think you basically given the talk. I mean, that's all I had to say. So, no, obviously, I'm just kidding. Yeah, thanks so much for having me. It's great to be here. I really appreciate everyone participating in this conference. This has been a real honor for me to be sharing the stage here, the virtual stage with Stephen Wolfram and with Gerald Sussman. Obviously, both legends in programming in computer science world, and in particular with Stephen, was really fortunate that as part of preparing for the conference, I got a chance to actually give him a demonstration of Clojure, which was pretty surreal, having had Mathematica as my first experience with a programming or computational language. And so really cool event this year to be able to be a part of. So thanks everyone for being here. So without further ado, I'm going to go ahead and share my screen. Let's see. Sorry, just a minute. Sorry, having a hard time figuring out which one of these stops is the right one. I think it's this one. Nope. Hold on.
There was something sharing, but then it was black and it went away.
Yeah, I got it here. It was the wrong one. Okay. Back up to the top here. All right, excellent. So again, thanks for coming here and being part of this this talk today. Again, my talk is Scaling Deliberation with Data Science and Clojure. So this story starts back in 2010 with the Arab Spring. Around this time, you saw across the Arab and Muslim world people rising up to demand change from their governments. Shortly thereafter, we saw the Occupy movements, which started here in the States and sort of trickled around elsewhere. And these were really about looking at the fallout from the financial collapse from just a few years earlier and how the big banks had gotten bailout, but Main Street America had sort of gotten sold down the river, or a lot of people felt that way at least. And so there were protests organized to demand that something change. So a group of friends and I were looking at all of these, this sort of turmoil and seeing these movements, which were these sort of large leaderless movements, which were able to get people out into the street, but in many ways failed to achieve their ultimate ends. And we sort of started asking the question, how can technology actually help people understand each other at scale? And part of what we realized here is that the technology at the time was good enough to get everyone out in the streets and protesting, but it was unable to bring coherence to the crowd, right? So Twitter and Facebook were able to get people there, but they weren't able to figure out, like, what is it that they're all here for? What is it that we all want, right? Because in many cases, different people want different things, and finding that middle ground that everyone can get around is extremely challenging. And these sort of vacuums of power provide opportunities for those who are organized and who do know what they sort of clearly want to come in and take advantage of the situation. And this is something that we saw in particular with the Arab Spring. So our idea to this, at the time I was working at Fred Hutch Cancer Research Center in the computational biology department, studying viral epidemiology and cross-species transmission, emergence of infectious disease, stuff which has, of course, become sort of relevant lately. But in the course of that job, I'd become familiar with a number of machine learning methods that we were applying towards some of these and related problems, and started wondering if we could use the same sort of techniques to solve this problem of helping people understand each other. So the idea came around to use these techniques specifically to create something that we now call an opinion space. Or maybe I should say to create a model of what you might call the sort of true or latent opinion space within a population of individuals. So the start of this is what we call dimension reduction. So if you think about a large number of people voting agree or disagree, yes or no, 1-0, if you will, to a large set of comments submitted by other participants, you can think about every person's position in this landscape as being some point in an n-dimensional space, where n is the number of comments in this discussion. Dimension reduction is a technique for taking data in a very high dimensional space and sort of compressing it down into a smaller dimensional space. And ideally in such a way that you preserve some amount of structure of the original space. And where things get interesting with different methods is how much of that structure to preserve and how and what structure to preserve, and what degrees of freedom do you have in sort of creating this new space, and what sort of patterns do you show. A very simple method for dimension reduction is called principal components analysis, which you can think about as taking a set of points in a space and rotating it around until you're able to sort of create the biggest shadow in the projection that you're trying to find here. So on the right here, we actually see all these little all these little circles here, these are profile icons or profile images, excuse me, avatars from individuals in a conversation, and their positions here relative to each other are actually based on this dimension reduction. So here really quickly we get a sense of if two people are close together, they probably tend to agree, but if they're further apart, they tend to disagree. So already just by creating this space that we can actually visualize and kind of think about a little bit more intuitively, we're able to start to get some progress. I mean, our idea here was that by reflecting back to people their position in the landscape and others, that we can start to build some understanding and solve some of these challenging problems. The next sort of phase of what we had in mind for analyzing what we thought of as the opinion space was to apply clustering to find opinion groups within the conversation. And so specifically here, as a start anyway, and still we use the k-means algorithm, which is a very simple clustering algorithm, which basically just tries to find these centroids, these centers of the clusters, and cluster all the points around them. And Lloyd's algorithm is a sort of iterative step for moving those centers closer and closer towards an optimal solution. So very simple to understand and easy to sort of interpret. Now, by taking the results of these analyses, we can start to visualize the landscape as I described, but we can also use these opinion groups, these clusters, to aggregate vote data and use those aggregations to start to figure out what comments were actually most reflective of each individual group, as well as where is there actually unexpected consensus between groups. So as an example of this here on the right, you can see that if you click on the group, this whole shape on the right, this larger opinion group with 119 individuals in it, once we click on that, we can see the statements that were important to that group. Again, as identified by these opinion group based aggregations. So this group in particular felt that during the campaign they found out that 75% of minimum wage workers are 20 or older. I think it's the right thing to bring higher outcomes to this group of people. Right? So this is something that really highly identified this group as being different from the other. And if you look at these bars above the overlaying the opinion groups, you can see how much more this group agreed with that comment than the other group. So just by clicking around and sort of exploring this interface, you're able to start to build an intuition for what people think and feel. So once we'd kind of come up with this idea and started working on an implementation, we decided that the best way to sort of move forward this project, which was starting to seem promising, we built a prototype and it was working and doing the thing, and we decided to start a for-profit startup to fund the mission and vision that we were trying to accomplish. We thought that if we can find a market that this technology can be applied to, we can use the funding that we get from seeing to that market to further this sort of mission that we had of affecting the way that people make decisions together at kind of a broader scale. So this is where Clojure enters the picture. Again, we built sort of a prototype of this system with the math having been implemented in R, which was, it's a language that I'd used a lot at Fred Hutch Cancer Research Center, and was great for this kind of prototyping phase of it, where you just wanted to get something working and see if it did the thing, but didn't really feel like the kind of language that we wanted to implement, a big system in. Even just simple things like reading in and out JSON just felt sort of much more challenging than with a lot of other languages. I won't go into all the problems with R, but as much as I love, what it's really good at. I had recently started using Haskell a little bit, as well as OCaml, and was really taken by the functional approach to programming. So I started looking to see if there were functional programming languages that would be good in the sort of space that we were in. So this is, of course, how I came across Clojure. And some of the things that appealed to me about it pretty quickly were the fact that it was on the JVM, and that it felt like it had so much potential in the big data space. And I put big data in scare quotes here because if you think back, this is about 10 years ago now, data science wasn't really a common term then. It was still sort of a nascent thing, and really back then big data was sort of the buzzword and all the rage. And Clojure had a number of different libraries, from Storm to Hummingbird to lots of different tech organizations were starting to use Clojure to do kind of big data processing, and so it felt like a good space to position ourselves. We'd also considered languages like Scala, but ultimately decided on Clojure in large part because it just felt more cohesively and composably designed. And I haven't spent extensive time with Scala, so I know that a lot of people really love it, but we just got this sense that it was trying to be too multi-paradigm. It was trying to be a little bit of everything for everyone, and we really liked that Clojure just felt like it had made a bunch of decisions that all kind of worked well together, and just felt like a really well-designed system to build software with. And the other thing that really attracted us to it were the superb concurrency primitives, and obviously, Scala has plenty of strength in this area as well. But this was something that really was a foundational aspect of Clojure's design, and so it felt like a strong point language. So moving forward a little bit, we started this organization, and we're beginning to try to explore different markets for the technology that we had built. When in 2014, the sunflower movement happened. So this started with a rotten trade deal between Taiwan and mainland China, which almost the entire population was against. This was something that had been pushed through kind of by upper level bureaucrats, and it had been sort of fast tracked through the standard political processes, and it was made clear to the people that it didn't matter what they think, this was going to happen anyway. So this ended up being sort of the straw that broke the camel's back, and a largely student-led, but also organizers from older generations set of protests resulted in a peaceful occupation of the Taiwanese parliament. So and when I say peaceful, to be clear, there was no destruction of property. They actually cleaned up when they left. Just to contrast with some recent events, it was, but part of what made it peaceful, and part of what set the tone for, this was not something that was, again, destructive or malignant, was the fact that this civic tech organization called Gov0, typically written G0V, had sort of come in and set up the kind of technological infrastructure that they needed to make sure that this movement wouldn't go south. So specifically, they rolled out fiber optic cables out into the streets. They were setting up makeshift Wi-Fi antennas with Pringles cans, if I understand correctly. I mean, it was just this really remarkable thing that all these people came out and made sure that there would be internet for people to collaborate and get help if needed. And very importantly, that everything was able to be recorded and live streamed. So there was no opportunity for the media or other powers that be to come in and say, oh, look at these violent protests that are being destructive. Everything was above board, and Gov0 played a huge role in that. So much so that in sort of the aftermath of the people actually getting what they want and revoking this trade deal, the government was sort of in a moment of crisis, and then Digital Minister Jacqueline Tsai, if I understand correctly, actually came to a Gov0 hackathon and asked them if they could build a platform for rational discussion and deliberation of policy issues that the entire nation could participate in. So this was obviously a pretty bold request, but it gave birth to what is now known as vTaiwan, which is an adaptable process using many different tools, but which uses Polis for the core understanding at scale component. So this process has now been used to deliberate and legislate issues on a national level. And initially, vTaiwan was just about virtual, the virtual space for V for virtual. So issues around, digital, online, and in particular, some of the issues which it was used to deliberate were successful regulations of Uber, Airbnb, both of which have, of course, been challenges for polities around the world to sort of figure out how to deal with. You have these huge organizations that are very powerful and found ways of sort of getting what they want. But with this process, they were able to come up with a solution that that really ended up being good for all sides. And you were able to see that even though there was a lot of contention around these issues, there were also points of common ground, and that those points of common ground could serve as anchors on which to build or foundations on which to build solutions for everyone. So this has gotten recently a lot of press. It took a little while, as you might imagine, right? When something happens on the other side of the world in Taiwan, it takes a little while for it to filter down to the English-speaking world. But eventually it did. And so some of the articles which have been published, which you can take a look at if you're interested in learning more, include the MIT Tech Review article titled "The Simple but Ingenious System Taiwan Uses to Crowdsource Its Laws." Wired put out an article called "Taiwan is Making Democracy Work Again. It's Time We Paid Attention." And very recently at The Atlantic did a wonderful piece called "How to Put Out Democracy's Dumpster Fire." So all of this has been absolutely amazing for us. I mean, I cannot tell you how insane and surreal it feels to, a decade ago have started working on this crazy project, which just seems, pie in the sky, to having a nation actually make decisions using this technology and to start to get the kind of attention that the project has been getting now. Where things got a little challenging for us, though, was realizing that if we wanted to continue growing in the civic tech space, we needed to open source the software. And the civic tech community was just not willing to go and take it other places without that. And so this led to some kind of immediate challenges. So how do we monetize an open source project? The sort of natural answer to that was, well, we can do consulting, but that leads to further challenges. How do we scale a consulting practice without taking VC? If you're looking at a consulting business, you're looking at much higher dollar amounts than software as a service. And so now your cost of acquisition of clients is higher, and you get into this sort of cycle where without some kind of funding to push that project forward, you just kind of dead in the water. And at this point, we've been working on this for many, many years, and realized that we didn't want to take VC because we'd seen what happened to other organizations in the similar space who had gone that direction. And so a few years ago, in 2018, started the Computational Democracy Project with the goal of carrying out the mission and vision that Polis Technologies Inc. had started. And just this last year, we finally received official 501c3 charitable status from the IRS. So this has been again just the conclusion of about a decade now of work on this project, and it's fantastic to be able to share with you today that both we have this organization and that it's achieved 501c3 status. But back to Clojure. Don't have a lot of time here, so you have to race through a little bit. But so this is supposed to be an experience report of Clojure in data science usage. So some of the good, Clojure was obviously a joy to learn and work with. I wouldn't be here if that wasn't the case. As a data-oriented language, that it's just data philosophy really makes sense for data science. That has just continued to be the case. It also has a really sharp and highly leverageable set of tools and libraries, which have been throughout a really, a great experience to work with. And again, the amazing concurrency primitives that are built into Clojure have been really valuable for us. So the sort of awesome potential, though, that I see for Clojure, and that we're starting to apply now, not necessarily to the core tool itself, but with the kind of data analysis that we do with the data that we collect, and that others can potentially take advantage of from the data science Clojure community, We have Clojure script, which means that, Clojure is really, as far as I'm concerned, the only sort of data science capable language that can do anything from big data to running a server to, running machine learning algorithms, that also has, a viable and well-trod front-end target for building interactive clients in Clojure script. We've also now, as a community, largely converged on Vega and Vega Lite for data visualizations. So these are data visualization languages which are very philosophically compatible with Clojure's It's Just Data approach to things. And there have been amazing advances in terms of the kinds of numerical computing that we're able to do with Clojure. So Dragon's work on Neanderthal and Deep Diamond have been just absolutely amazing in terms of what we've been able to accomplish and making Clojure a really fast language for implementing numerical methods, and for doing deep neural networks. Yeah, I don't want to say more recently, not similarly recently, we've now, Clojure has always been built on the idea of interop with the JVM and Clojure script. And this has also been, I think, something that really speaks to Clojure's potential as a language for data science. So we can interface with libpython CLJ to the Python world and actually create two-way bindings where, Clojure programs are able to call Python functions and Python programs are able to call Clojure functions. Similarly with Clojure, we can interface with the R world. If we need to implement things in that language, then we can still take advantage of them from Clojure as a glue for stitching things together. As we saw Stephen Wolfram demonstrate yesterday, we now have, well, we've had for a while, but we've now had some dusted off bindings to the Wolfram language, which just opens up an entire world of really fantastic possibilities. But I'd be remiss if I did not also share some of the ugly, some of the challenges that we've faced with this. So first of all, 10 years is a long time for any code base, even Clojure. It has definitely been the case that I've found that Clojure project from years ago is much more likely to fire up, down the road. Without mucking around with things than basically any other language that I've worked with. So this includes JavaScript and Python and a number of others, but Ruby certainly. But it's still the case that after 10 years, there's going to be some stuff that's changed, even if it still works just in terms of what the community is using for different tasks, different approaches to things. We've evolved a ton in 10 years. Clojure is only a little bit older than 10 years, right? So there's a lot that's changed in that time. We've also had increased scaling demands. So we were able to get around some of the scaling issues of implementing these algorithms in Clojure prior to Neanderthal and Deep Diamond and such, by being kind of careful about the algorithms we chose. But for various reasons, we're now starting to hit up on some of the limits of the system that we've built. And some of the stuff is incidental and not necessarily at all Clojure's fault, more my fault for having implemented this stuff as my first experience using Clojure. But also, and this is kind of the third bullet point here is kind of in reference to the first, moving away from core.matrix to the TechML stack is something that we'd really like to do to take advantage of all of this interoperability that it provides with Python and kind of the rest of the emerging Clojure ecosystem, which is really exciting. But more kind of to the point, there's a really difficult question which has arisen, which is, as a nonprofit, we hope to be able to take advantage of volunteer efforts. So a lot of the work that it took to take this initially, for-profit startup software as a service package and open source it, that was sort of, it's easy to open source something. It's not easy to take something that was built to run on a single instance and make it so that anyone can go and fire it up, to build that DevOps infrastructure to make it deployable and have repeatable process for getting things running. And a lot of that has been driven by volunteer efforts. But a problem sort of emerges with respect to Clojure in that, Clojure is really a small community. And so as a nonprofit, we have to ask ourselves, when we build a new piece of infrastructure or, some new part of the system, if it's not, already implemented in Clojure, is that how we want to implement it? I personally would always like to implement something in Clojure over JavaScript or Python when it makes sense. But we also have to think about who's going to maintain that. And again, as a nonprofit organization, how can we make sure that that we can actually take advantage of the volunteer base we have available? So what I am part of my goal here in putting this talk together was to ask you as a community to help with this process of modernizing the Clojure code base, and showing that we as a community can punch above our weight, and that this is largely for selfish reasons. I want to use Clojure as much as possible at my work, but I also think that there's a real opportunity for us here as a community, in that this is a really exciting project that's turning a lot of heads, and I think that it's a wonderful showcase of the kind of cool stuff that Clojure can be applied towards. So I'm going to end there, but I just want to say again, thank you so much for having me. And sorry, I went a little bit over, but I'm excited to chat further here and take questions and that sort of thing.
Thank you very much, Christopher. You're vaguely over, but definitely okay. No worries about that. And thank you very much for delivering your talk. So now we are going into the second from last panel of the day. I can call again the attention from Ashima and see if you can connect back to us and if you can hear her voice. Ashima, are you here?
Hi.
Yeah, fantastic. So we're both here. So I'll be joined by John. Let's see, is John available as well?
I'm here.
All right, fantastic, John. So we are all ready here for another amazing Q&A session. So as usual, I'm going to ask Ashima my icebreaker question. And the icebreaker question is there anything interesting in your surroundings, an item, or maybe something else that you want to share about you?
I think maybe I would like to share this. This is like my workout mat, but it's made of wood, like straws. So it's an insulator. You could work out on like a really cold floor and it would still remain warm, and it would remain cool on a warm floor. So it's like a great way to work out in places which have like huge temperature fluctuations. So yeah.
Nice. I also saw it was like nicely decorated as well, colorful and everything.
Yeah.
Cool. Yeah, I think sometimes I don't see them around here where I live. But yeah, I mean, it would be nice to find a shop where I could find them. Maybe Amazon has them. We'll see. We'll put a link. John?
Yeah, I was just thinking I could do one of those myself for a bit of yoga in the morning when the floor is cold. Chris, have you got any curios you'd like to share with us?
Yeah, I've got a bunch of crystals on my desk. So I recently, if you listen to the podcast I mentioned that I've gotten into rock hounding as a result of my child, and I don't know. I've never been like that into. I mean, obviously crystals are cool, but when you find your own crystals in nature, it's just this surreal experience. Like, wow, I dug that out of the ground. I mean, look at this like perfectly shaped, thing. It's just so yeah. My room is quickly. I've organized the camera so that you can't see too much of the mess, but there's like rocks everywhere in the rest of my room right now, outside of the cone of observability here.
Excellent stuff. Thank you very much.
Yeah.
Yeah, that's really cool. So I want to invite, of course, again, our audience to like raise their hands for live interaction, ask the questions here, ask the questions on the dedicated QA panel channel on Discord. So a few of the questions, Ashima, you already asked, you already answered, but I mean, we want to share the same answer with everyone else here in the call. So apologies, or maybe good for you, you already prepared the answer. So here's the first. How would you suggest I choose between Oz, viz.clj, Hanami, or other option for data visualization?
Great. I guess the answer which I gave was basically Hanami would give you like the most amount of customization possible. And like if you want to go in depth, then that is definitely the option to choose. But if you are just starting out and you have never done any data visualization in Clojure, I would recommend starting off with Viz. And like I said, we have these options to substitute, like create Hanami substitutions. So that will help you slowly, like gradually learn Hanami as well, along with using Viz. So Viz would sort of fulfill your initial requirement of creating small charts, and then you are slowly learning Hanami in the process. Other than that, we also have TechViz, which has like certain specialized plots if you have those needs, like for example colorful histogram or something, so you can check that out. And if you don't want to use any browser options, then I think CLJ plot would be the one to go, which is which is right now in progress, and Tomasz is sort of building it. So yeah.
Okay, thank you.
Can I add a couple of points to that?
Of course.
Yeah, great.
Sure.
So yeah, that's that I think that sounds great. As far as Oz is concerned, this is something. So we did a workshop on this just earlier this week, and I think there's kind of a challenge with Oz in that it has evolved into kind of a Swiss Army knife. It's got a lot of different tools, or it's got a lot of different things that it can do, and so I think a lot of people aren't necessarily even aware of everything that that it has available. It is, it's a set of reagent components which have now been made more flexible as far as how you get data in and out. So you have access to the Vega View API for inserting or changing data sets. It's also we've been working on similar things to NoteSpace and Clerk with our namespace as a notebook functionality. And so just released version 2.0 earlier this week, which has some really cool stuff to check out. We're actually evaluating forms in parallel now, not just doing the dependency graph and then computing one after the other, but actually when we see the two forms are independent, we can compute those in parallel now. There's and I think say the other thing that really stands out with Oz is that for a long time now it's been designed with the goal of being able to produce static documentation or scientific documentation. So PDF output is on the horizon. Been kind of designing around that for a while right now and getting close to putting that in place. But also if you want to build a static website like a blog or just produce kind of a data science report, you can use kind of the notebook functionality of Oz and then spit out a static HTML document that looks really nice. So I think, but just to kind of cap all of that off with Oz, that's Oz specifically, right? I mean, it's a Swiss Army knife. Use it for what kind of makes sense for you. I feel like it's a good first tool to grab if you think you might want to be doing a bunch of these things, because then you have everything there. But the other thing I'll say is just that it's really fantastic that as a community, I mentioned this in the talk, have converged towards Vega and Vega Lite as data visualization languages, because it means that we've got a lot of interoperability, right? You're not locked into any one of these things as long as they're all kind of using these this underlying language. So for example, you could take Hanami's templating mechanisms for more concisely describing data visualizations, and you could use them with Oz, or as you mentioned, you could use them with Viz CLJ. So there's the answer is use everything.
Yeah, and Ashima, it was also suggested that you publish the docs on cljdoc.org, and you mentioned that. You tell me.
Yeah, like I was not aware of that library, so I'll definitely check it out. And if it suits our needs, then I would definitely use it.
All right, thank you. John,
Excellent.
any more questions?
Yeah, I've got a few questions for Chris. Actually, while you were talking about Oz, I'm just curious, does Oz implement the complete Vega Lite specification? And is it just Vega Lite or is it Vega as well? What's the kind of situation there?
Yeah, so it's just wrapping Vega and Vega Lite. It's effectively wrapping well, it's kind of doing two. Again, it's complicated to describe what a Swiss Army knife is doing because sometimes it's doing different things. But the standard sort of usage where you're at a REPL or a Clojure process and want to visualize some data kind of interactively, that opens up a web browser and you can interact with a Vega or Vega Lite visualization there. So it's just using the embed API to embed in a page. But if you're building statically compiled output, if you're building a web page, if you're, again, hopefully in the future here pretty soon, if you're building a PDF, it's going to use one of two mechanisms to try to statically compile an image. And incidentally, you can just use Oz to statically compile an image, just kind of by itself outside of the context of scientific documents. If that's what you want, that is something it can do. But to do that static compilation, I'm see who worked on it. I want to say Jack Rusher and what is it? I'm forgetting. I'm forgetting the name of the organization that did this work, but Dark Star was the name of the project that was using
Light Science.
Yes, thank you. That's using Graal to compile Vega and/or Vega Lite, I guess, so that actually from within the JVM now, using Graal to interpret or whatever compile the JavaScript in the Vega libraries, it's able to now compute at least the SVG. I think that if you want PNG, which sometimes is better if you have bigger data because you don't want to have an SVG with too many nodes. That could be a little bit problematic, but I think there you might still have to use the install the npm Vega CLI to get it to work, but which is the other mode. So Oz will use the npm Vega CLI as a fallback. But if you want SVG output, it will call out to the Dark Star library to produce that.
Dark Star. That always reminds me of the movie. If you haven't seen the movie, then it's worthwhile watching that. I think it's a classic.
I don't know if I have.
It's a classic old one. Yeah. One of the early sci-fi movies out there.
Reminds me of the orchestra.
Yes. Nice. Cool. And so, are there any good tutorials to help people get into using Oz if it's such a big Swiss Army knife, or should we look at the workshop you did earlier on this week?
Yeah, honestly, the workshop, we ended up kind of getting into the weeds a little bit. My goal was to really try to do a lot of demonstrations, and unfortunately not for. I mean, whatever. It was actually great. I mean, people ended up being a little bit more interesting in asking questions about how things worked and kind of future direction stuff. So not necessarily, but I do want to put out soon a better, just full kind of video that outlines and details all the things you could, or actually maybe a bunch of separate videos that show the different features. One that kind of gives you an overview and some that go into the details.
Okay, that sounds cool. Yeah, if you want any help with that, I'd be happy to get involved with that as well.
Yeah, that'd be fantastic. Yeah.
Cool. All right, great. Okay. If anybody's got any more questions, feel free to keep on piling them in. I'm kind of curious if we switch back to Polis a little bit. I know I don't really want to kind of air your dirty laundry, but I'm kind of curious in the original tech stack and perhaps how you want to evolve that and some specific parts of this awesome potential of Clojure data science that you want to unleash in this project as well. What kind of thoughts do you have on that?
Yeah, absolutely. So one of the biggest things that I really want to do with the code base is, and this is kind of funny, but at some point we kind of re-implemented the code base using, not re-implemented, but we set up Sierra's component library for dependency injection and lifecycle management. which seemed like a good idea at the time. I mean, it's kind of what everyone was using, and we wanted to be able to kind of start and stop the system more cleanly. And I mean, certainly it solved that part of the problem. But it came with the cost of just making the code base a lot harder to work with, which I think, especially from a data science perspective, is very problematic, because I think that when you're designing software to be software, when you're doing software engineering, you can kind of tolerate a little bit more of cantankerousness, shall we say, in exchange for kind of a cleaner system design where you can have a test environment running at the same time as your development environment. I mean, the component can do a lot of stuff, right? But I've recently come to the conclusion that for the kind of interactivity that you want with a data science project, in order to kind of dig into a namespace and start evaluating stuff, having to muck around with finding the right component from the system thing and then sticking that into the right function call every time, it's just really kind of annoying. And so I'm thinking that it would be great to re-implement an either. I'm interested in considering integrant, but I think probably mount is kind of the seems like the simplest, or maybe it's easiest. I'm not sure, but seems like a very straightforward solution that kind of solves the problem of making things more usable from the developer perspective. There's also the other big thing, and this is a major thing again. I touched on this briefly, but we implemented using core.matrix, which at the time seemed like a great idea because core.matrix has this really modular design where it's built against protocols. So you can actually implement the core.matrix API using whatever kind of underlying data type. So that felt like a really powerful feature initially, but since then, and I'm not someone who's deep in the kind of performance and numerical computing side of things. That's not necessarily my bag. I'm more experienced with like the algorithms and the the analysis side of things, not necessarily the nitty gritty of how they get done. But I recognize that a lot of the Clojure community has moved more towards the TechML stack, and that really buys us a lot in terms of it solves some very real kind of pressing problems with performance, I think, and also again gives us the opportunity to interface more with Python, with R, with the rest of the kind of data science sphere in other ecosystems. So that's a transition that we'd like to make. So those are the two biggest things that come to mind right now. I'm kind of going through a very long old issue queue, and if you go back to the talk, the link that I shared to to our repo, you can go find the GitHub project on that page, and that's where I'm starting to break things down a little bit. You can search by math or Clojure to find Clojure related issues, and things are there's a priority column there, so you can take a look at that to see what's pressing in our mind.
Excellent, thank you.
Yeah.
Okay, we have another question for Ashima. I think she's answering straight away in the channel, but like we'll get her live here. So since Viz doesn't have the Swiss Army knife dimension, does it have a notion of when it will be done? In other words, where will Viz be going, and what do you want to do with it next?
So I think it will still be like in the alpha stage for at least a few more months. Usually we decide our directions based on the feedback that we get from users. Like that was our process we decided to follow when we started building it, and it has worked very well for us so far. So we would like to continue with that, just showing it in the study sessions and watching how people react to it. That would probably be the main deciding factor. There are a few more things which we would like to explore, like some specific use cases, such as, I mentioned like the time series data visualization or something like that. So maybe we'll also look into that. So, yeah.
All right. Fantastic. So I think we will take the 5 minutes break in preparation for the lightning talks that are coming after. So there's going to be a little bit of live scrambling, getting things ordered and the timing right. So stay with us. But before we stop for the break, let me thanks again Ashima for her awesome talk, her effort, and Chris as well again for his talk and being with us today, answering all these questions. It is amazing. Thank you very much. And now the break. Thank you.
Thanks, everyone.
Thanks.
Thanks.
My favorite break so far. So welcome back after this first quick break. So this is the interlude for the second day. So we are going to have like a special time with something a little bit more improvised. And today we organized a list of lightning talks and the community experience report that now I'm going to show you quickly, just to show you what the thinking is. Hopefully you can see my screen. So we are going to have 5 lightning talks. We're going to start with the Boston Clojure Bridge community led by Elena with a quick introduction and experience report about their experience. We are going to have the Spanish-speaking community updates with Mauricio and Leandro. We're going to see Mecha, an animated music editor in ClojureScript. And we are going to see an introduction to Omnitrace by Lucas. And finally, Athens, a multi-client event synchronizer. So hang tight. We're going to try to get all of this in quick sequence. So if I now find my sharing capabilities, yes, give me a second. I'm orchestrating everything. So can Elena unmute herself and see if we can see her on screen? Yeah.
Okay.
Elena?
Hi.
Hi, Elena.
Yeah.
Nice to meet you.
Can you hear me?
Hi. Yes, I can hear you. Okay. So
Okay,
whenever
excellent.
you're ready, you should be able to share your screen and you should be able to.
Okay, and you should be able to see my screen now, right?
Let's see. I don't think. Yes, sorry. Yeah, it's just here.
Okay.
Yeah, go ahead. Thank you.
All right. Hello. So I'm Yelena Machkasova, and my co-presenter actually is not here, but he's probably more entitled to speak about Boston Clojure meetup. So Mark, I think he pronounces his last name Champagne, but I'm not sure. And he was lead organizer for Boston Clojure meetup since 2016. So Boston Clojure meetup, here's a link, and let me get to this. So this is our page, and now I need to get back to my other slides. Sorry. Oops. Sec. Yes, it's a little improvised.
Yeah, sure, of course. Go ahead.
Okay. Yeah. Okay. There. Oops. Yeah. There we are. So this meetup has over 600 members currently, and Mark counted 95 meetups that were held, and it sort of stopped as COVID started. I was actually supposed to give a talk in March, and that never happened. And then restarted as virtual in April 2021. And actually that opened a few opportunities for having remote talks. And we had some participants from other countries and had to adjust our schedule a little bit. The meetup was founded in 2011 by Eric Cobran. So I don't know how it relates to other meetups, probably was one of the first. And Mark was the lead organizer, as I said, since 2016. This is the current group of organizers. So Tom for a while was hosting in person until COVID happened. And Jeremy is very active, and John and myself. And now it's virtual, which is actually quite convenient for me because I don't live in Boston. So it's a little ironic that I'm talking about Boston meetup, but I did my PhD in Boston. I lived there for a long time, and I have a lot of friends and some family there, so I kind of consider it my second home, and that's how I'm involved in it. As one of the organizers, I would like to advertise our next talk, which will actually be by Mark. And here is the title, and it's going to be this coming week. So hope to see you there virtually. And another thing that I wanted to mention is that the same group around 2016, 2017 ran 3 rounds of Boston Clojure Bridge. So that's an outreach. This is an international organization that aims to increase diversity within Clojure community by offering free beginner-friendly Clojure programming workshops for underrepresented groups in tech, so specifically for underrepresented genders. So this is what this looked like. This is our first Clojure Bridge in 2016 at Akamai. So this is the organizing committee. And it's a little hard to tell how many learners we had because lots of people sign up and then don't show up as it happens. One thing that any organizer knows, you need to be patient and understanding. But we had about 20, 25 learners at each of them, about 10 to 15, maybe 12 mentors, and 2 tracks for those new to programming and for those new to Clojure. And so these were our meetups, 2 hosted in Akamai, and 1 hosted at MIT. And we did a little bit of change in curriculum from traditional, well, and there is no standard, so every group does something a little different. So ours was somewhat based on Minneapolis curriculum and some other things. And one nice thing that happened because of that is it's always an all-day Saturday event, but some groups had mandatory Friday install fest, which made it less accessible, and we made it optional so that people could install their own software, and we sort of streamlined that process. And another interesting thing that it featured was career panel, and lots of participants actually mentioned how valuable that was. So I think I should probably stop here. Do I have more time?
No, we are about the time. So if,
okay.
if that was,
yeah, so if anybody has any questions, I'll be on Discord. I would love to see more Clojure Bridge happening. And so anybody who is interested, we should talk. Of course, they're better in person. Okay, thank you very much.
Thank you, Elena. Really nice to know what other meetups, what other organizers are doing around the world. And in this respect, we are having another experience report, this time from the Spanish-speaking community. We should have Mauricio and Leandro online. Let's see if we can get them. Ooh, I can hear you very far away. Try again.
Just a moment, please.
Yes, no, you're coming now. Try to talk. Either you, Mauricio.
Can you hear me now?
Yes, it's working perfectly.
Nice. Just a moment. Let me share my screen, please. Share screen. Oh, nice. Oh, nice. Cool. So, can you see my screen? Yes.
All good.
Yes. Okay. Just. So, sorry. Just a moment, please. Setting up my camera.
Okay, I think you can hear me now also, right?
Okay, nice. Can you see me?
We got you, Mauricio, as well.
Yes.
Wonderful.
So
see you. See both of you and hear you as well.
So you should be able to, yes, I think you can see the advertisement panel. Well, hello, thank you very much. We are Mauricio and Leandro. Can you hear me, Mauricio?
Yes, I can hear you. Just fine.
Nice. And we are presenting the Spanish-speaking Clojure community, or probably a Spanish-speaking Clojure community. We don't know whether there are others, so there could be others. Contrary to a normal community, like we share the language in the sense that normally a users group would be based on a physical location. So that was the case with people from the Boston community. In this case, we are based around the language. Why is that? Because, well, even though many of us do speak English with the varying degrees of fluency, there are things that you can always express better in your own language. So that's the basic reason why. We also have people who come from different native languages, like Mauricio. Maybe you want to speak a little bit about you?
Yeah, sure. So I was invited to the Spanish-speaking community mostly because I am right now living in a Spanish-speaking country, but I am originally from Brazil. So I'm kind of in this strange situation when I do have, like, I am in the community of Clojure Brazil and Clojure US and also Clojure Spanish. So it's quite interesting for me. And yeah, we are still a small community. We're trying to organize more meetups. I think we only have one meetup organized so far, right? And yeah, so that's mostly how I met the group. And unfortunately, I couldn't go to the first meetup, but I am really wanting to share more about the community because, well, we are, as I told, still small. We want to grow, and Spanish is a really big language. It's one of the most spoken languages in the globe, so there's no reason why you should be so small. Our goal, I don't know if Leandro told everybody, but it's word domination. But we don't talk too much about that, otherwise people will think we are supervillains.
We won't be able to achieve it otherwise.
So is this a link that you're posting here on the slide a good place to know a little more about your meetup?
Actually, we are a Telegram group, basically.
Okay.
In the Spanish-speaking world, Telegram is very popular, so we started with that. We have around 70 members. Some of us are like experienced in other communities. For instance, in my case, I worked at the local community in my hometown in Argentina. I also helped in a Clojure community in Buenos Aires a few years ago, where I used to live. We also organized a Clojure Bridge in, I think, 2017. And I think Mauricio also has history with the communities.
Yeah, mostly Ruby and Clojure community in Brazil.
So yeah. For us, it's very important to be here so the rest of the world can know about us and get the word known. So please join our group and let's get in touch. Thank you very much.
Fantastic. Thank you very much.
Yeah, one of you already joined it. Thank you.
Yeah, and if you have specific questions for either Leandro or Mauricio, reach them out in the Lightning Talks channel, which is just, one place where you can find each other, and then you can take the conversation wherever you think is more comfortable. All right, thank you very much, Mauricio and Leandro, for bringing this experience to us. I'm going now to switch to like a more technical, entertaining lightning talks. We have Mecca, an animated music editor in ClojureScript by Bobby Towers. And I'm going to, for this, I'm going to show you this.
Okay, I can do this. What I want to do is show the individual parts. And so yeah, this is all of the music data, which it's just a sequence of maps. Each map is a note that has a time, an instrument, and a pitch. That is literally it. And each one of these is what I would call a pattern. This is base 1. So, and it takes a time and a root so that you can modulate it or transpose it to whatever. And so we're just dispatching it to reframe here. We'll get a smaller one here. And so yeah, this base 1 pattern, this was what it all started from. And where's my up? Where's my up? Where's my up? All right. That's it. Base 2. And so then we could concatenate those. And I think that should be right. And so that's all there is to it. And so then the whole song is just this just giant ass concatenation. And so let's hear it once just for completeness. All right, thanks a lot. I love y'all.
Well, not sure what I was looking at least at the beginning, but it was awesome. Thank you, Bobby. It was really nice things to watch. And yeah, I have questions, but I'll need to move on to the next lightning talk. If you want to know a little more about this mix, concatenation, exactly, of music, art, and graphics, go to the Lightning Talks channel, and you should see. I don't remember his handle, but you should see the screenshot of the Lightning Talks to talk with Bobby. All right, moving on. So the next thing is the next Lightning Talks is introducing Omnitrace with Lucas. Is Lucas available?
Yeah, hey, can you guys hear me?
Yeah, I can hear you. We can see you.
Okay, perfect.
All good.
And
All right,
I'll
take it
try
away,
to share my
Lucas.
screen. Thanks.
Yeah.
Huh. Can you see my screen?
All good.
Okay, perfect. So Omnitrace, I started it like a week ago, not 2 weeks ago now. The idea was that I really liked how flame graphs work for performance stuff. And it's really sad that you can't really use them to debug and to look into code traces of other stuff. And the idea was to build a tool that lets you use it. The basic thing is you have got, it kind of works like Said, just on the Clojure script side plus on the Clojure side. You can say, okay, I want to run something with a trace, like you say, okay, I want to run traced and what it is that you want to run. This is just a function. And once I run it, I get the usual output that the function has, and then I can tap it. The flame graph is just Vega.js specification with all the data from the run. And if I tap it and then jump over to Portal, I can see the trace with all the stuff that was called from this function. Here I can zoom in, I can zoom out. It's not very helpful in such a small graph, but still I can click on it to hide the side stuff. I can mouse over it to see in the tooltip what it was called with, what the return was, and so on. I can also move it around and stuff. The other thing that's currently working kind of is integration with debugs. The idea is to inner trace a function. We've got a factorial function that's here somewhere. And when I trace this, I can see that in the workspace, I've got like the normal graph I usually have, but I've also got an inner trace that's telling me, okay, here num at some position, at the value 3, and so on. So I'm basically tracing every single call in this factorial thing, and then also putting it into the graph so that I could display it in the flame graph. Currently, there's no display for this yet, but I've got the data now. I just need to show it.
Can you, Lucas, can you make it slightly bigger, the font, if it's like a quick thing to do?
Yeah, I already did that once. I can do it again.
Oh, no need for that.
size.
But people can read it.
Sure. Is this better? Do you need more?
No, I think that's
we can
okay.
go to
Thank
24,
you.
I think. Okay. So, okay. We can do inner traces. Like I said, we can uninstrument the stuff we instrumented. We can reset stuff. We can also do tracing. The deep trace does not only work on your own code, it works on the libraries that you're using as well. Currently, there's a blacklist for the core namespace. You can disable that blacklist and then run the code with tracing into the core namespace. So here you can see I've got traces on keep and I don't know, where is it? On keep and plus. Well, I guess you can't see it since it's too small, but you'll have to believe me that this is the tracing into the core namespace. We can also set that back. The problem that usually arises from such tracing libraries is that the data is getting too big. And here we've got max call sites where in every call site he remembers how often something below it was called. So if I trace the testing function and then run it 100 times through a map, I can see, okay, we only remembered 100 of those calls. So that my trace doesn't get too large. You can set how large it should get. And the final thing that's already working, you see this exception. It's because this thing is throwing an exception, but it's getting handled inside the call trace. And here you can see, well, I guess you can't because it's too small, but usually you could see the arguments that went into the exploding call and what the exception was at that type, so that if you do something like this, you know which one of those exploded and so on. Or if you do a deep trace and something explodes on the way, you also know what happened. What I'm currently working on, or what's already working, if I can get my pull request into Portal, is that if you press a key here, you can jump into the code because this trace knows where this happened, so which file it was, which column it was, and so on. And if you press D, it's gonna start your, well, it's gonna take VS Code at this or Emacs or whatever, and it's gonna show you which part this is in. And the other thing that's already working as well, just waiting for the pull request to go through, is copying of the execution, so that when you press the C key, you get this into your buffer, so that you just have to paste it in. And no, it's too small. The call args that were used get pasted in as well, so that you can run it from like deeper in the graph if you want to play around with it in a REPL again. Yeah, what I'm currently working on is getting the data in here on the fly instead of pushing all of it in at the start. Right, with this graph, it's not a problem. At some point, it's going to get too big for Vega to handle. So if I click something like this, it would be nice if the stuff below it gets loaded after and is not already present. Yeah.
Thank you, Lucas. We need to
switch
to the next one. No worries. I need to keep the time here. I know it's difficult. It's all improvised, so really appreciating the effort. But I think we got a gist of what Omnitrace can do, and if anyone wants to know more, the link was posted on the Zoom chat, or go back to the Lightning Talks channel and ask as many questions as you want to Sirik, right, on Discord. And thank you very much, Lucas. It was really interesting.
Yeah, thank you.
Oh, cool. So we are going for the last Lightning Talks of the day. Felipe Silva, are you here with us?
Yes, I am.
Hi, Felipe. Thank you. So we are going to see Athens, a multi-client event synchronizer. Take it away, Felipe.
Hi, my name is Felipe. I want to clarify something here. Athens itself is not the synchronizer that we're talking about. Athens is the application that uses the synchronizer, and I think I can like give you a quick idea of what it's meant to do. And let me share my screen because that is inherently relevant to like why we need a synchronizer. Like generically, look at this. This is just like some notes about Reclojure, and I can come here and edit some stuff. And it says here F. That stands for me, Philippe. The important part here is that like this is actually a multi-user application. Like you can't see other users right now because I didn't ask anyone else from my team to come here, but this is inherently a multi-user application. And I'm gonna stop sharing and just talk a little bit about that. So like it's one of those traditional architecture where you have reframe and you model everything with events. And like a lot of the state that you were seeing was actually represented in DataScript database. And it's really nice to have a DataScript database because you can like do very complex things in memory and still have a database. But then how do you actually, like if you have multiple people working on the same thing, how do you make sure that your database is in sync with their database? And that's not so trivial. And like this inherently is very client-side heavy. Like you do a lot in the client side and you just, in your head, you kind of think, oh, I just want to synchronize some bits with other clients, but we want everyone to be at the same state. And if you've ever used DataScript or any of the other data log databases, you kind of have this intuitive notion that if you have like your history of transactions and like the whole state is determined by that history of transactions. So would there be a good way of actually synchronizing all those transactions with other versions of the same client on other people's computers that like to arrive at the same state? And that's what we try to do. We haven't published this as a library, but it's what we use to do this in Athens, where we kind of came to this concept. Well, if you actually have this list of events and you have a part of them, it's purely just exists on your client. There's kind of like the optimistic ones. And then there's like the real ones that were already propagated to everyone. But you can still look at this as like a whole list. And you can say, well, while you're synchronizing this little bit, how about you still operate over it and you still go over your reframe and your DataScript database and you apply everything optimistic. And then when kind of like reality changes from behind you, you just go and like remove everything, apply the new tip of reality, and then apply all the optimistic stuff. This is what we try to do in hopefully a generic enough fashion. And this little, sorry, let me try and find it here. I think it's this Chrome window. In this little library, it's a single file. We call it event sync. The idea is that if you have like this model where you have a certain log of what should be reality, you can split it into phases, into stages even. And some of these stages are more grounded in reality than others. Like some of these are actually on the server. Some of these maybe were persisted to the local storage on your client. And some of these are purely in memory because they went nowhere else. I think I already put this link in Lightning Talks channel. This link contains an example of how it works, how it deals with some concurrency cases. It just operates over the concept that you can view a list of events that are being synchronized still as a single list of events that has a certain order. But then you just need to know when you go back in time and something got inserted in the middle and when you need to kind of decide what to do about the inconsistency. And I think that's time. Thank you.
Well, thank you very much, Felipe. This was perfectly in time. So if anyone wants to know a little more about this model or synchronization, please go back to the Lightning Talks channel and you can get in touch with Felipe and ask any more questions. Thank you very much, Felipe. I appreciate it. Your improvisation here. Okay, so I'm going to head over to, I'll remove the screen share if I
Hello.
Yeah, over to John. I cannot find the comments here.
Okay, while Renzo's doing that, we've got 2 more talks before the keynote. Ooh, it's all exciting. And so, yeah, the next 2 talks are going to be very interesting, as all our talks have been. So next up is Tovier, which I've hopefully pronounced his name properly. He'll be using the SICM library, the Structured Interpretation of Mechanics, to show us how to represent the mechanics of the world, like such as throwing a ball in the air, and all using Clojure. Tovier is a full-stack software developer from Hudstadt and based in Nigeria, and has worked with many different languages, although he says his favorite language, of course, is Clojure. And he has some other very interesting interests, such as 3D math visualization in virtual reality. So over to you, Tovier.
Welcome to the presentation on automatic differentiation in Clojure with SICM utils. My name is Tovier Moses Ozi. I'm a software developer based in Lagos, Nigeria. My contact details are on screen. The GitHub link for the repo this presentation is based on is on the screen as well. This talk is based on the SICM utils library, and this is the link to the GitHub repo for the SICM utils library. The SICM utils library itself is based on a scheme library called SCM utils. SCM utils was developed for the book Structure and Interpretation of Classical Mechanics by Gerald Sussman and Jack Wisdom. Many Clojurists are familiar with another of Gerald Sussman's works, Structure and Interpretation of Computer Programs, SICP. Also, there are many other resources I consulted in the process of this making this video. There's an article on dual numbers and automatic differentiation by Sam Ritchie, and there are many other videos for the SICM utils library. Have you seen a math equation that you wanted to explore? Where do you turn to? Python, MATLAB? We can actually handle all of those problems right within Clojure. During the course of this presentation, we'll look at a small physics problem. What happens when you throw a ball straight up? And we'll answer a few questions like, how high does the ball go? How fast is the ball traveling at any point in time? We will be using the following libraries in our exploration. The depths.eden is shown on the screen. We'll be aliasing the SICM utils.env namespace as env, and we'll be referring several functions from that namespace. A quick search for the height of a projectile thrown up online gives us the equation shown on screen, where y is the height of the projectile, v0 is the initial velocity with which the projectile is thrown, t is time, and g is acceleration due gravity. We can write this equation out as a Clojure function, which is what you see on the lower left, the height function, which takes 3 arguments. You'll notice that the math operators have the env alias from SICM utils. They are all from the SICM utils.env namespace. The env namespace provides these versions of the Clojure core functions because these versions are genericized. That means that they can operate on more than numbers. For example, the minus operator can subtract symbols, matrices, and other data structures. We could write the same function using the Clojure core functions, as you can see on the right, but then they would not be able to support many of the SICM utils capabilities. On the screen, you see my Clojure namespace rendered to a browser window by the Clerk library. Let's call our height function with time of 2, initial velocity of 20, and acceleration due gravity of 10. We get 20. If we call the height core function with the same arguments, we also get 20. Remember, the height core function uses the Clojure core versions of the math operators. We can also call our height function with Clojure symbols, and what we get is an expression in prefix notation showing the symbolic form of our equation, of our function. But we cannot call the height core function with Clojure symbols. We will get an exception if we do that. So how do we convert the prefix form of this expression to the usual infix notation that we're familiar with? We can use the simplify and to infix functions from the SICM utils library to create a render function, and if we call our height function with that render function, we will get a text version of a symbolic version of our function in infix notation that we are familiar with. We can also render our function to LaTeX. We'll create a render Clark version that renders the function in LaTeX, and this is what it looks like. We can rewrite our height function as height time, a function of one that takes one argument, time. We do this by substituting fixed values for the initial velocity and gravity. In this case, we'll take an arbitrary value of 40 for initial velocity and 9.81 for gravity. With our height time function in hand, we are now ready to plot a graph of height against time. First, we'll use a utility function to round all values to 2 decimal places. Then we'll get a set of time values, a series of time values starting at 0 and ending at 8.4 with an interval of 0.2. We'll map our height time function across those time values to give us height values, and then we will map against both time values and height values to create a series of Clojure hash maps with a height and time key. This series of values will go into a Vega-Lite plot created by Hanami, and finally we can call the Clark Vega-Lite renderer on our height plot, and we get a graph. From this graph we can tell the approximate maximum height of our projectile, which is somewhere around 80, and the maximum height happens somewhere at the 4-second mark. Quick refresher on slopes and tangents. For a straight line, the slope can be calculated by picking any 2 points along the straight line, then dividing the vertical change between the 2 points by the horizontal change between the 2 points. The slope of a straight line is always constant, but for a curved line, the slope is always changing, and you can get the slope for any point on a curved line by calculating the slope of the tangent at that point. The tangent for a point on a curved line is a straight line that touches the curved line at only that point, at least for all points that are close by to that point. If you extend the tangent on a straight line, it may actually touch the curve at some point, some distance away from the tangent point. The slope is a measure of how fast y is changing with respect to x, or in the case of our height time function, how fast the height is changing with respect to time, the velocity of the ball. We can approximate the tangent to the curve at any point, to our height curve at any point, by picking a point very close to the point we're interested in and drawing a straight line between the two, and then we'll calculate the slope for that straight line. How fast is the ball traveling at time 2? Well, at time 2 the height is 60, and then we'll pick a second time which is close to the first. We'll pick 2.1. At 2.1 the height is 62, And then to calculate the slope, we'll subtract the first height from the second, and divide by the horizontal interval, which is 0.1. And that gives us a speed of 19.9 meters per second. That is the speed of the ball, how fast the ball is traveling. We can generalize this to a slope at function, which takes any function, a small delta, and the point at which we want the slope. So calling our slope at function on the height time with a delta of 0.05 and a time of 1, we get 30. At a time of 3, we get 10. At a time of 5, we get -9. That means the ball is, instead of traveling up, it is now falling. And at a time of 7, we have -28.7. The slope function tells us how quickly the height is changing at a particular point in time. But this method has a shortcoming. It's an approximation. It is possible to draw a tangent line at any point, for any point on our height curve. So just as our height is a continuous function of time, the slope is also a continuous function of time. So perhaps we could somehow transform our height function into a slope function, a function that takes only time and returns the value of the slope. One way to do that would be to modify our slope at function, and this is the result, an approximative function that gives us another function. The result of this function we can call on time, and it will give us a slope. But this function is also an approximation, so even if we get an approximate velocity out of this function, it will always be an approximation. Let's try the D operator from the SICM utils library. The D operator is similar to the approximative function, but it is not an approximation. It is an exact transformation of the height function into a velocity function. And we can write a small function to compare all the three approaches we have looked at so far: the slope at method, our approximative function, and the D operator from SICM utils. So we'll map over a series of time values and display the results in Clark as a table. Looking over the results, we find that all methods are very close to each other, but the velocity obtained with the D operator is not an approximation, unlike the other results. So with this, we come to an understanding of what the derivative is. The derivative of a function y is another function z that tells us how much the output of function y changes for small changes in the input to y. And the process of obtaining a derivative from a function is called differentiation. That is what the D operator is doing. It is transforming the height function into another function, velocity, and the velocity function tells us how much the height function is changing. We can call the D operator on velocity to get acceleration. Now that we have acceleration and velocity, let's expand our chart. So we'll generate velocity values from time values by mapping velocity against the time values, and we'll do the same for acceleration to get acceleration values. And we will want to make our chart a bit fancy, so we'll do things like add a line function to draw tangents, and finally generate plot data, a series of maps with keys for acceleration, height, time, and velocity. This is the Hanami template for plotting the height plot data. And finally, we call the Clark Vega Light renderer on our plot on our Vega Lite data, and this is what we get. We can see the height in blue. The blue line is the height, and then the purple line is velocity. The scale for the purple line is on the right. And finally below we have the green line, which is acceleration. It's flat and it's minus 9.81. We also notice that the velocity starts out at 40, and as the time increases the velocity drops until somewhere around the 4 mark. The velocity hits 0 and then becomes negative. So basically the ball thrown up, as the ball is thrown up, the velocity keeps on dropping, and at a certain point the ball stops rising up and starts falling back down to the ground. So our initial questions were, what is the maximum height of the ball? At what time does this maximum height happen? And how fast is the ball traveling at any point in time? We have answered how fast the ball is traveling because that is the derivative of the height function, velocity. What about the maximum height of the ball? One of the applications of differentiation is to find maxima and minima of functions. So at the maxima or minima of functions, the value of the derivative of that function is 0. That means the value of velocity will be 0 at the maximum height. We can call our velocity function with symbol t to view the symbolic representation of a function, and then we'll equate that representation to 0. So we can solve for t. T solves to 4.08, and so that means the time at the maximum height of the ball is 4.08. Also the velocity, the maximum height is the height at that time, which is 81.5 meters. There are a bunch of rules taught in introductory calculus for doing differentiation, such as the exponent rule, which says if you have a function of x to the power of r, the derivative is given by taking r to the other side of x, then subtracting 1 from r. And this is valid for any real number r. The d operator from SICM utils is able to reproduce this rule and all the other rules from calculus. We can see this for a small set of functions by mapping the rendering of the original function and the derivative of that function using the d operator over this set of functions. And what we get in tabular form is this result. So for x squared, a d operator produces 2x, x cubed, 3x squared. And down here we have our height function and its derivative. The d operator uses forward mode automatic differentiation. This is different from other computational approaches to differentiation, such as numeric approximation. Numeric approximation is closer to what we were doing with the slope at function, or symbolic differentiation. Symbolic differentiation is like keeping all the rules for differentiation in your computer program. That is not what the d operator does. Rather, it represents every value in the expression to be differentiated as a dual. A dual is a value with two parts, the original value and the derivative is the second part. We attach a tag of epsilon to the derivative. And once this is done for all values in the expression, the d operator proceeds with normal simplification, adding all the terms, subtracting, multiplying, and if along the process a term comes up with a tag with a power of 2 or greater, that the value attached to that tag is discarded. A rough explanation for this is, think of every tag as a very small number, and for increasing powers on a small numbers, we get more and more insignificant values. So we can discard higher powers of the epsilon tag without affecting the result, the accuracy of the final result. And this approach of forward mode automatic differentiation allows for obtaining the derivative of any program, because you can, provided the value in your program can be represented as a dual, you will be able to do differentiation on it. For example, if you can represent a closure feature as a dual, then the D operator will be able to obtain a derivative of the feature. Here's a breakdown of how the D operator would go about differentiating an expression such as this. First, every value would be represented as a dual. So we have the cos x squared term. That term is actually a composition of two functions, so the dual representation is not straightforward. So the derivative will be written as unknown at this stage, but there is a rule in the SICM utils library that says that if you have a function and the argument to the function is itself a dual, then we can write out that function as the first part of the dual will be the function called on the argument without the dual representation, and the second part of the function dual representation will be the derivative of the function on the argument without the dual representation. So applying that to our cos x squared term, we can now write out the dual form of cos x squared as cos x squared plus epsilon 2x minus sine x squared. The dual representation, the derivatives for exponent terms like x and trigonometric terms like cos and sine are already inbuilt into the D operator. Then the next step is to carry out simplification, basically multiplying and adding all these terms together, and in the end we end up with a single dual, and you can see that the first term on the dual is the term we started out with, and the second term is our derivative, and that is what we're interested in, so we discard the rest and keep the derivative. During the course of this presentation, we have seen a good workflow for exploring physics problems in Clojure using the SICM utils library and a few other Clojure libraries. We have also taken a surface look at the implementation of the D operator for automatic differentiation in SICM utils. The SICM utils library does a lot more than automatic differentiation. It has a large and growing list of operations that it supports, and you can see many of these at the link on your screen. That link takes you to a web page filled with worked examples of many physics problems. Thank you for listening.
And thank you, Xavier. That was a lot of maths, but it was expertly explained. So thank you very much. An excellent presentation on using SCIM with another example of using the Clerk notebook as well to tell that story. Now we have another generative art interlude. I love that music. Excellent. So our final talk before the big one. And we have next Marcus coming to unleash Clojure on the world of physics again, with the help of Bob Dylan this time. Prior to being a Clojure freelancer, Marcus shared a desk with other traders, some of them also fellow physicists, in an Australian bank where they spent ages, a decade even, replacing Excel spreadsheets with reframe apps. And before that, Marcus was implementing trading systems in banks all over Europe, while covering his knowledge by doing a master's course at Oxford. He's also been at CERN in Geneva, where he wrote his diplomatic thesis and got to know C++, but like most of us, never really got to understand when to use which of the OO patterns that are out there. Over to you, Marcus.
Hello, I am Marcus. I'd like to show you a graphical environment for learning Clojure and physics. To warm up, let's get our hands on some Bob Dylan lyrics. Come gather round, people, wherever you roam, and admit that the waters around you have grown, and accept it that soon you'll be drenched to the bone. Come, writers and critics, who prophesize with your pen, and keep your eyes wide. The chance won't come again, and don't speak too soon, for the wheel's still in spin. For the times, they are a-changin'. What I just presented is widely used in learning poems by heart. Maybe you have seen mobile apps of that kind. The method is also well known in computing education. It was termed Parsons Puzzles in 2006. It is a topic of active research, at least since then. The title of my talk is Functional Physics, Code Along with Visual Blocks. The table of contents does not show this title. We need to complete the puzzle. I think that puzzles are ideal for learning functional physics. A puzzle is asking you to think about the design of an algorithm. You do not worry too much about the actual code. Your focus is on the problem domain. The syntax of the language matters less to the user. This feature is very compelling when it comes to Clojure and Lisp. The attitude towards Lisp in science is best described on the Pirate website. Pirate is the programming language for introductory computing. You heard about it on Friday in the talk on data centricity. Quote, much as many of us love parentheses, we fear that Lisp will always bump into an acceptance threshold due to its syntax. We are delighted to see the growing adoption in industry of languages like Racket and Clojure, and maybe the days of parent phobia are over. But academics are far more hidebound than industrial programmers. I also see that the Lisp acceptance threshold exists among scientists, and for very relatable reasons. For a physicist, a method or theory is a valuable and hard-earned thing. It will only be given up when experimental facts force her to do so. I think that an academic needs to be hidebound like this to have any chance of making real progress. Plus, scientists always have concern for their self-efficacy. This means they will be inclined to look at a new method or experiment only when it is short and elegant. The most elegant formulation of physics I know of is presented in the SICM book by Sussman and Wisdom. SICM stands for Structure and Interpretation of Classical Mechanics. But this approach involves programming in Lisp. And typing on a keyboard is certainly not as elegant as writing with pen and paper. Because of this, I wanted to bring Clojure nearer to pen and paper with the method of Parsons Puzzles. Let's start with the algebra. This workspace shows a simple math example. We calculate the average of 20 and 40. Drag 20 in front of 40 and divide by 2. The result is 30, as expected. This was the first example of solving a physics puzzle. For a scientist, I think it is clear enough. But a note is in order. A programmer who knows that CLJ tiles is written in Clojure expects a notation which differs from the common one. To clarify this, we open the parser by right-clicking on the workspace and type +1, 2. You can see that the parser converts Clojure code into the usual infix notation. The reason, of course, is that the notation in the workspace should be as similar as possible to pen and paper. The code which is generated is displayed on the lower right. It is proper Clojure code. The code is for informational purposes and read-only. It is handy for pasting into an editor and starting to develop own programs. The idea is that users will learn to read Clojure code while solving puzzles from easy to more and more difficult levels. It is important to say that normal users will only work with the mouse and not use the keyboard. The parser only is needed for creating puzzles, which is the task of dedicated coders. While normal users are not concerned with creating puzzles, they certainly want to understand them and investigate the puzzle pieces. This will be covered in the following example. When I run this workspace, I get an error message. It is actually not called error message, but code interpretation result. Sometimes a workspace is not yet meant to run. You did not make a coding error, you just ran early. So the name error is simply wrong in the case of puzzle solving. Right-click on the number 2 and inspect. You now see 3 reasons why no end result is shown. The first reason being the variable the average dangling on top. The second is for the ill-formed def. The third again for dangling the average. There is more than one reason displayed because inspect tries to run every expression separately. This is different from the run button, which stops evaluation at the first ill-formed expression. Move the number 2 out of its block and inspect. All of a sudden, you get a result. Clojure was able to evaluate the expression despite all the other unsolved issues. The value 2 is printed together with its type, which is number. The display of types is possible because, within CLJ tiles, parts of SICM are spec'd via Clojure spec. I think the type number is the most important one in functional physics. This is because numbers provide the connection from theory to experiment. I think types help in learning physics with SICM. Usually, data is presented to the user just as a string of characters. It all looks very similar. But when additional type information is displayed, the data gets a shape. When it is typed, a piece of data is experienced more as a thing of some kind, a text, a symbol, or a number. Later on, we will learn about several other mathematical objects. Types will make learning about them easier. Another idea for flattening the learning curve is to present the same puzzle at several difficulty levels. So we look at 2 different workspaces which contain the same puzzle. Here we see a simple function definition. The puzzle is very easy to complete. In the violet block, the function sayWelcome is called with the value Clojure. When the workbook is run, the text Welcome to Clojure is printed. To show a bit more in detail of what is going on, inspect the parameter called what. Indeed, it carries the value Clojure and is of type text. On the next page is the same puzzle as before, but split up a bit more. You can see that the blocks have different colors depending on the number of slots. Blocks with 1 slot are violet, 2 slots is green, 3 slots is blue, and there is the pink block with no slot. Now we solve the puzzle. It should help that we have already obtained the solution before by solving the simpler version of the same puzzle. Here, the colors play out nicely and separate the different blocks in a clear manner. The blocks with 1 or more slots are all constructed in the same way. They start with a name, like defen, printline, sayWelcome. The defen is not special in any way. It is just displayed vertically. This can be changed using the context menu. But that does not make sense from a code formatting point of view. We go on to a bit more sophisticated math now. I will show the printing of column vectors. With this, we enter the domain of the SICM book. Originally, the SICM utils are written in MIT Scheme. In the last years, the SICM utils have been ported to Clojure by Colin Smith. Sam Ritchie enhanced and ported them to ClojureScript. The workspace I show here has an explanation at the bottom, so it should be easy to complete. As you can see, in SICM, column vectors are created with a function called up. After pressing the Run button, you see the correct result. 1, 5, 9. Inspect the whole green block. First of all, the vector is now nicely formatted. And second, we see that the result is a column vector which consists of 3 numbers. Now inspect the right blue block. Here we get a new type, an expression. If you inspect pi, you get a hint why this is. Pi is a symbol. Apparently, when the function sign is fed with a symbol, it returns an expression. So we already have 4 different kinds of mathematical objects in this simple example. There are numbers and symbols, which we already know from standard Clojure. In addition, we have a type called column vector and a type expression. They are provided by the SICM library. All of those mathematical objects can be used in calculations. In other words, we have a computer algebra system in the browser. Now fill the upper left slot with the green block. Press Run. The result is printed nicely formatted as before, this time without the types. Up to now we had 2 kinds of blocks. On the one hand, the simple pink block, and on the other hand, the remaining blocks, which are mainly for calling functions. There is no obvious way to do higher order functions. For this, the beige block is introduced. It always has exactly 2 slots. The first slot carries the higher order function, the second slot carries the one single argument. Look at the violet block, which has the familiar form for calling functions. Its one slot is filled with the string 3 equals. Now inspect the block. The result of this block is a function with exactly 1 parameter. We want to find out what this unnamed function does. For this, we fill the first slot of the beige block. After pressing Run, the result is the text 3 equals 3. So the string 3 equals within the violet block is concatenated to the number 3. We are given the definition of the higher order function above. It is called this returns a function. It takes some text as an argument and returns an unnamed function. This unnamed function itself takes a number as its single argument and returns a text which concatenates all the data. The beige block takes exactly 1 argument. Every functional programmer knows what this means. CLJ tiles demands currying of higher order functions. Thus, the beige block is another stepping stone to Lisp. The insistence on currying makes code containing higher order functions more readable. The most important application of higher order functions within SICM is taking derivatives. In the following workspace, we will take the second derivative of the trigonometric function sine. For this, we need to remind ourselves that pink blocks not only take texts or numbers, but also the names of functions. Inspect the pink block T. It is a symbol. Inspect the other pink block. It is a function. While its name is not displayed at the bottom, the block itself reveals that it is the trigonometric function sine. To calculate the second derivative, drag square d into the first slot and sine into the second slot. Inspect the whole block. It is a function, but it is unnamed. We need to apply it to some argument in order to explicitly see how it looks like. So, finish the puzzle and press Run. The result is minus sine, indeed the second derivative of sine. Now, take another look at the result. It is interesting to know its type. One might guess it is a function. The derivative of a function always is a function, after all. That is perfectly true, but there is a catch. Inspect the whole block. It is not a function, it is an expression. Inspect the inner block. A function. This is the real second derivative of sine, an unnamed function. It is notable that this unnamed function knows nothing about a symbol or a variable named t. You can even replace t with pi. Inspect, and you get a meaningful result, the number 0. In the last step, we calculated the derivative of sine at point pi, and we got the number 0 as a result. There is a more general version of this. It is called a functional by physicists. This is a construct which takes an arbitrary function as an argument and returns a number. Again, while a function like sine takes a number as an argument, a functional takes a function as an argument. On blackboards in physics classes, sometimes a dot is used as a placeholder for the argument within a functional. The corresponding notation in blocks is quite obvious. I split out the sine block to leave an empty slot. This slot now can be filled with any function, and the result of the block will be a number. Hence, the block is exactly the thing which physicists call a functional. This block cannot be executed anymore. In the context of the interpreter, this functional does not exist. But in the context of physics, it does. This well-known construct of physics is just not understood by the computer in this form. But a tutor can create, interpret, and explain it very well to students. So, my claim is that graphical blocks can form an independent notation beyond their execution as a computer program. But then, they require a tutor. Concerning notation, you might have noticed that the beige block can be misused. With it, one can construct a normal function call. For example, sine of t. This notation should not be used. The correct notation is revealed by the parser. In the beige block, the sign can be removed. But in the violet it cannot. So the violet block is not in line with the Lisp idea that goes by the slogan, code is data. We have already seen another such break in tradition when we had a look at algebraic expressions with infix notation. Again, the reason is that the notation should look as similar as possible to pen and paper. Coming from this complex topic about notation, I'd like to add a remark on Parsons puzzles. As far as I know, CLJ Tiles is the only environment using Lisp for those puzzles. A Google search leads to a Python implementation. The original paper by Parson et al. Is from 2006. It seems that from the beginning on, the idea was to arrange whole lines of code. Compared to the line-by-line approach, the use of Lisp offers a new vision. Parsons puzzles in really 2 dimensions. And with this, Lisp offers a much vaster space of possibilities to construct tutorials. A sophisticated possibility was the example just shown before. Because the puzzle showed a rather deep idea, it required a tutor to understand. It is important to note that a domain expert does not need to know how to program. The puzzle is already there and can be used as easily as writing formulas on the blackboard. Even more, I think the cognitive load is reduced by using puzzles instead of pen and paper sheets. This concludes our deep dive into puzzles that show the principles of functional physics. Let me come to a more higher level overview of a specific physics example. At Clojure West 2017, Colin Smith showed the example of the driven pendulum. The demo is on his blog page. In the last chapters of CLJ Tiles, the equations for the driven pendulum are developed puzzle by puzzle. I will give a brief overview of this example. It starts with a very simple workspace containing the definition of a freely moving particle. In the next steps, we introduce the kinetic energy and the gravitational force. This demo here is meant as a high-level overview, so I will not go into details. But all the workspaces have a description and a solution for further studies. As an intermediate result, we arrive at Newton's equations for a particle in the gravity field of the Earth. As a concrete example, think of a flying cannonball. Notice that the equation has two parts, because the ball can be shot forward and upward, and anywhere in between those two main directions. In the next workspace, we make a pendulum out of the cannonball. We suspend it as a weight on a pivot. Thus, it now describes a swinging movement. This step is arguably the most difficult part to understand. Notice that Newton's equation now consists of only one part because the weight can only move at a fixed distance around the pivot. In the last step, we introduce the moving pivot and arrive at the final equation. This concludes my overview of the driven pendulum, and we come to the summary of the talk. I presented examples in theoretical physics as a series of Parsons puzzles. Anyone can attempt to solve the puzzles just by opening a web browser. Puzzles help smooth the rough edges of Lisp. CLJ Tiles achieves this with the following features. Math formulas are presented in the commonly known infix notation. The various colors separate nested expressions, and they do not start with parentheses. This combination is meant to resemble more the familiar math notation for functions. Higher order function calls have their own special block, which takes only one argument. Evaluation of expressions is very easy using the inspect functionality. The indication of data types helps in understanding the various objects that populate physical theories. So, puzzles help to overcome the acceptance threshold for Lisp. But Lisp in turn augments puzzles. It really levels them into the second dimension. So, lecturers can present sophisticated examples that go way beyond beginners' tutorials. All in all, Lisp and puzzles are a good match. For an outlook, I can only say that CLJ Tiles was a private endeavor. I'd like to thank all the people who gave me advice and support. The dream is that CLJ Tiles opens the door to Lisp. A small crack into some of the physics classes that are traditionally based on pen and paper. Thank you for watching.
Thank you, Marcus. That was so much fun and an excellent way to learn. I like these visual tools. They do help me pick up and manage concepts a lot easier. Right, now we've had our two speakers, we'll have our panel. Do we have our wonderful co-speaker, Jordan? I see we have Renzo gate crashing in.
Hey, I'm here.
Hey.
Renzo, what's up?
What's up, Renzo?
Just joining the nice crowd.
He wants to ask his own questions, I'm sure. Shall we see if Marcus and Tovier are around? Where are they? If they'd like to unmute themselves, do they need to be made co-hosts?
Yes. My bad again.
That's all right. You've been working very hard.
So you should be able to mute yourself.
Yeah, hi.
Marcus.
Hey,
Hello,
Marcus.
everyone.
Hey, Javier. Excellent. Everybody's here. Let's get this party started then. So I'm going to be asking questions to Marcus, and Jordan's going to be asking questions to Tovier, although I get a feeling that that might end up being mixed up around, but I'm sure we'll all have fun while we're doing this. All right, so I'll start with a nice icebreaker for Marcus. So is there something interesting or curious on the desk around you that you'd like to share?
I brought my lucky pick.
Nice.
Which, yeah, it helped me get through those 10 years of being on the trading desk and working on. You tend to get superstitious when you do those kind of things. And yeah, it's still with me and brings me luck.
Excellent, thank you.
Right.
Jordan.
Okay, and I would like to have you first clarify exactly how to pronounce your name, Tovier. Is that?
I think you've got it basically right. It's even hard for people in my country to pronounce, but I pronounce it Tovier.
Okay, Tovier. Same icebreaker question to you. Is there something around you or in your surroundings you'd like to share? Any fun facts about you you'd like to share?
Not in my surroundings, but a fun fact about me is I do like to do some gardening when I'm not coding. Yes.
Oh, what's your favorite thing to garden?
Basically make a lawn and clear out the weeds. Yeah.
Yeah, very cathartic.
You can come around to my house if you want. Excellent. Okay, let's have the first question for Marcus. CLJ Tiles, I think this is a wonderful project. I'm just curious about what your inspiration for creating it is. You mentioned kind of breaking that crack into how lecturers teach physics. Was that one of the things that drove you there?
Yeah, exactly. So I started with learning general relativity, and there is this wonderful book, Functional Differential Geometry, right? So to show it from Gerald Sussman and Jack Wisdom, and I started to learn it and had to install Emacs and all those tooling. And I thought, well, that takes quite a while, especially on Windows machines. And 5 years ago, it was even more difficult. And so I thought, well, it takes quite a while till someone can start really to learn the physics part of it. And I thought, well, there needs to be something done about it to get physicists more into this kind of understanding their own subject. And as I said in the talk, it's very understandable that scientists, they don't pick up tools very easily that are not known to them, because they have their tools and are used to them and know how to use them. And so it needs to be made easy. Not only simple, but easy. And that's really what I was up to when starting with this project, right?
Excellent, thank you.
All right, and I just want to remind everybody in the audience, there are several ways to get your questions on the docket. We'd prefer that you just raise your hand in Zoom, and then you can ask your question directly, or you can put it in the Discord channel, or you can write it in the Zoom chat. Okay, so next question for Tovier. So kind of same thing. What inspired you to get into all of this? Were you exposed to SICP or SICM first?
Well, the inspiration is I did my undergraduate in mechanical engineering, so I had some exposure to physics. I've not read the SICP book. I've started reading the SICM book, and because of my exposure to physics, I I'm interested in math and physics equations. I watch maybe YouTube videos where I see equations, and sometimes I would like to play around with these. And when I saw the SICM utils library in Clojure, since I'm also interested in Clojure, I thought this was a good intersection of interests. I could get to analyze these equations right from within Clojure. And also, another factor is there are a few Clojure developers here in Nigeria. So I looked for online communities to join, and there was the SCM utils community. So that got me going, meeting other Clojurists and discussing the book. And when the suggestion came about to give a talk at this conference, I was happy to get involved.
Oh, wonderful. Good to hear from you. So back to John with Marcus.
Yes, thank you. So there is a question from Discord from Jakob. He's asking if you've actually tried the puzzles approach with any of the students yet, and if so, how did it go?
Yeah, that's the LACMUS test, and that's still missing. So the answer is no. But I tried. So there is. I'm based in Vienna, which is not in Australia. No kangaroos here, and there is an institute for the physics for teaching physics, didactics of physics. And I went there and showed them my project, and they were very helpful and friendly. But the thing is, they said, well, we are only doing grammar school level. So your project is very, very nice and everything, but still we don't have students for you to try it out. You would need to lower the level of your content, and then it would be possible. But I'm not really sure if I want to go down that road. And on the other hand, I talked to university people, and they said, well, we have Mathematica here. So we are teaching with Mathematica. And I say, well, yeah, it's open source and everything. I say, yeah, that's the same point all over again. They have their tools and they work. And so answer is no. I tried. I will take any chance I can get, but the tool is there. It's there for a reason, and maybe there is my lucky pick. And I still got this far, right? So the next talk is by Gerald Sussman. I never thought I'm gonna get this far with my project, which is something. And I'm still knocking on wood that someday someone will come up and say, yeah, I'll try to show this to my students. But it didn't happen yet.
Yes, well, I'm with you with the pig. I wish you all the success in that range. And yeah, a lot of people are learning a lot more outside of university now. So maybe there's like a community that will pick that up outside of university as well. And
the thing is, obviously I have some friends from my physics studying days. They are at university. And even their students mostly learn mechanics the usual Newtonian way, and until they come to this Lagrangian way, that takes some time, and so that's another issue. It is a way of teaching. I mean, I'm all in for it, right? And then I'm sure many are, but finding students. Is well, yeah, but that's why I'm here actually to present.
Yes, and let's hope many of those students get a chance to kind of see this video and see what they're missing out on. Thank you.
Okay, Jordan. Another one for Tovie here. So it sounds like you are familiar with Sam Ritchie and his work he's done porting SICM to Clojure script. How much have you worked with him? To what extent?
Well, mostly so far, the extent I've worked with him is consuming his work, but I'm starting to get more involved. For example, the SICM utils group I mentioned earlier, we met several times earlier this year to discuss the book and the library, and Sam was at those meetings. And of recent, I've taken a closer look at the library, not just consuming it and doing the exercises in the book, but with a view to contributing as well. So I hope to maybe get a PR merged into the library soon and make other more significant contributions.
Yeah. Sam is a great guy, and he would probably really appreciate that. He loves to work with the community. Okay, back to John and Marcus.
Okay, so I'm quite curious how you actually built CLJ tiles, or any particular libraries and tools that helped you build this project?
Well, I mean, there is, of course, the Clojure script port of the SICM library by Sam Ritchie, and Colin Smith did the Clojure version. So that's, without the port to Clojure script, the whole project would need to run on a server, obviously, and that's not necessary. So that was a precondition to be able to deliver something like this. And then there is the Blockly library, which is maintained by Google. So it's basically a connection of those two. Everything else is reagent, standard Clojure script front-end stuff. And as far as I can remember, nothing really more.
Yeah, and the rendering of the evaluation results, that's quite nice. Is that some kind of math library?
Yes, that's math.jax. But the tech, that's a really low-hanging fruit, because the SICM library has all the technology built into it. So it's just, there was nothing to do for me to get all these nice results and output. It was already there. I just had to plug it together. So yeah, it's just really it fits really. It had to be done. It just had to be done, in my opinion. Yeah.
Wonderful. Thank you very much, Jordan.
So I'm actually going to I think this was a question from you, John. So I will let you ask about the use of Clerk to Tovier.
Oh yes, I did like. I noticed you were using Clerk in there. I just wondered, what the learning experience was with Clerk. Was it something that was new to you when you started, or were you already familiar with it?
I was new to Clerk. I'd seen the presentations on other Clojure Conference, so it was on my radar, and it was basically a choice between NodeSpace and Clerk, since I'm working with Windows WSL on Windows Subsystem for Linux. So I think for some reason Clerk performed better there, so I chose Clerk. And but once I picked Clerk, there were no problems. It was very easy to get it going and get it working.
Excellent. Thank you.
You can go ahead and ask a question to Marcus now too, I guess, putting all the work on John.
Oh, making me work. Oh, it's getting late. Oh, yes. What do we got next? Oh, yeah, I was quite interested in the error handling stuff as well. That looks very friendly, and that's obviously one of the aspects of Clojure that people pick up on as not being that useful. Was that quite easy to create? Is that kind of extensible?
Yes.
Yeah.
The next thing is, I forgot the of course it's the Babashka SCI. So the Babashka for Clojure script by Mikhail Borkent, which of course don't have to mention. Everyone knows him, and without that, I wouldn't have those error messages. I think it would have been much harder to implement all this thing with self-hosted Clojure script. So the SCI interpreter again delivers on that for free for me. So it's again another stone helping me there without any effort from my side.
Yes.
What I'd like to mention, if I have time, the thing
Sure.
is the evaluation is not a REPL-like evaluation. So it's more like a print line debugging. So the program runs through every time you do an inspection and get an error message. And yes, SCI does that very nicely.
Excellent. Thank you very much.
Looks like we have a hand raised here, Mr. Egg Davis. Let's make sure he can unmute himself. Cool.
Yeah. So a question for Marcus. I'm not familiar with Lagrangian mechanics, so it's possible my question is completely incoherent. But I think that when you made the distinction of the function L, that's the Lagrangian function? Yes.
Yes,
okay.
yes. Mm-hmm.
And so the you talked about there being an issue there where that was sort of distinguished from ordinary functions, right? The ordinary function tiles where the function could not be removed from the function L's where it could. Do I have that correct?
Yes, I mean, what you are referring to is, I think, is that the usual way in CLJ tiles you define functions is in a way where the first part of this definition cannot be removed and only the arguments can be removed from that block. And this is for convenience reasons for the physicists who are familiar with this kind of notation. And it kind of contradicts the Lisp tradition. And what I wanted to say in the talk is that I'm deliberately breaking the Lisp tradition in order to make it easier for scientists to slip into it. But for doing higher order functions, you actually need something that is more in the Lisp tradition. So I introduced another concept for higher order functions. Whereas in the Lisp language, everything is one concept. You don't make a distinction between calling a function. It's all Eden data. It's all one data. Code is data, right? And in CLJ tiles, I break with this code is data paradigm in order for having this simpler expressions having displayed in a more visually appealing way, and in my opinion, more easier way to read them. So it's only well, not only the purpose of CLJ tiles is to make things easier to read. And that's why I chose to break the Lisp tradition for simple function calls. I hope that answers your question. It has nothing to do with Lagrangians really, or physics at all. Yeah. It's just how I distinguish between function calls and calls of higher order functions.
Totally. If I'm not taking up too much time here, organizers, please feel free to cut me off. But that was all sort of the lead up to my actual question, which was, that makes sense, but it seems like it does also sort of open space for user error, since they can remove that function and leave themselves in a state that can't run. And what I'm curious about is whether giving functions or expressions, whether there's the possibility to use a different puzzle connector shape to distinguish those to prevent that user error. Is that something you've taken a look at?
Okay. Well, no. The idea is that you have puzzles and connect them, and you can do whatever you like, and there is no prevention for people to make errors. They should make errors. They can start all over. It's not for developing really. It's really for playing with puzzles and understanding physics. There would be the possibility to kind of implement guardrails and things like that. And I started with, but I didn't figure out how to. There are so many combinations, what to prevent and how to do it. So I don't think I can ever find a solution to that, and I'm not so sure if that's really necessary to implement those guardrails. Another thing is, if I have time, there is in the usual Parsons puzzle in computer science, you usually have a success message, right? You get a star or whatever. Yeah, you did it right. In CLJ tiles, that's not the case. You just do whatever you like with the puzzles and look at the result. And there is no way in this kind of high level physics area. There is no way around grabbing the book, reading it, and understanding what's going on. I don't think, or maybe, well, I don't know how to prevent errors in this kind of realm, so to say. So well, short answer, no.
Yeah,
you can do whatever you like.
Thank you, Egg. Thank you. And so we are going to a question from Discord for Tovier. Having always resisted my colleagues' automatic MATLAB and Python recommendations, what is the comparison of capabilities available in SICM utils?
Well, I'm not in a position to make a comparison. The extent of my use of MATLAB is for plotting graphs. So I've not used it for differentiating functions or solving equations. And I've not really made use of Python for solving equations as well. I made that statement mainly to point out that it is possible to do some of these operations within Clojure. So perhaps you are working at Clojure for most of the day and you see this interesting equation. Now there's no need to context switch. You can just pull in a Clojure library and continue your exploration from there. I'm sure MATLAB and maybe there's other Python tools that have many years to have built up a lot of functionality that the SICM utils library does not have right now. But with time and more community effort, I'm sure we'll catch up and add all of those features to the SICM utils library as well.
Yeah, that makes sense. I'm going to ask you one more question, Tovier. So you said that the Clojure community is lacking there in Nigeria. I'd love to hear what initially attracted you to Clojure and Lisp languages and what piqued your interest.
Well, I started programming somewhere around 2017. And as a new programmer, I thought this could be easier. There was just a lot of stuff to learn. And somewhere along the line, I came across Rick Chicky's talk about simple made easy. I didn't really understand what he was talking about, but what hooked me in was the simple part. So at least someone was finally talking about how to make programming simpler. Now I understand that it's actually about not entangling all the parts of your program. So that got me interested. And about a few years ago, I started trying to learn Clojure seriously and dig into it. And about 2 years ago also, I finally got a job working in Clojure. So since then, I've been continuing with Clojure.
Great. Thanks so much for that response. And over to you, John.
Thank you very much, Jordan. So I'm kind of curious, Marcus, if there are any features you still hope to add to CLJ tiles, or if you're looking for pull requests. And you kind of mentioned it might be quite challenging to add like different concepts outside of SICM. Can you give us some idea about what would actually be involved in that?
Well, as I tried to explain before, that the most time spent on this project was for coming up with the example. There are 137 puzzles in there, so I couldn't show them all in the. Yeah, so I put most of the effort was figuring out the puzzles. with books from Getting Clojure from Russ Olsen. I took the first chapter and tried to make puzzles out of it, or Clojure for Brave and True. And then I did some web programming as well, and then going on to higher order functions. And then in the last 40 puzzles or so, it was really the hardcore Lagrangian physics stuff. So it's building up, and really meant to be that anyone can who wants to learn Clojure can make the first 100 puzzles and learn Clojure, and maybe omit the last 40 ones. And for the physicists, they can go on and make the last. So the next steps wouldn't be technical advancements in the whole stack or something, or Clojure related. It would be really making more content, and refining the puzzles, and looking at the didactical side of things. But technically, at the moment, I don't have any. We had the discussions that maybe you can add guardrails, and I thought about, you have this kind of gamification things where you get points when you do things right, and so on. And some of my colleagues say, yeah, to make it more popular, just do some gamification, which I think is more called schoolification. Should be it's not my notion. It's from it's a schoolification is in my point of view, and I don't want to do schoolification really, because I think people should be free to do whatever they like with the package or the project. And so technically I can't come up with something which makes sense from a didactical point of view. But whoever has some idea. Well, there are, as I said, there are lots of ideas, but they need to be crisp and bring things really forward, and not just looking what's going on in the games industry and copying that, because there are lots of issues there as well. So yeah. No, and so there should be just more puzzles and go more content, and maybe something easier. I'm taking too much time, but maybe something easier for the grammar school thing. I'm talking to a friend of his, a teacher of physics, and maybe we can do something there. So in that space, I would progress.
And there was Edward did mention in the in Discord Q&A chat that he would be a willing volunteer as a student to kind of give you some feedback on that as well. So
oh man, that's good. That's so nice. That's really nice. Yes,
so that's good. Yeah,
much appreciated.
Thank you. So obviously the pig is working.
Sure it does. No doubt about that.
Excellent stuff. Well, thank you very much. And I think we're out of time for questions now. Well, it's nicely wrapped up on time. Jordan, what's going to happen next?
Oh wow, throwing the ball over to me. Okay. Thank you, Dovier. Thank you, Marcus.
I can also help. I'm sorry for those who had the raised hands, but we want to be sharp on time with the keynote. We don't want Jerry to stay late or to start late. So for those comments or questions, perhaps post them in the Discord channel chat. And we need a quick break to prepare for the keynote. So we'll go into the break. Thank you.
So Renzo, I need to share my screen. Renzo?
Yeah, Jerry, I'll be with you in 3 minutes.
Oh, good. Okay.
I think we just have a 5-minute break before we start, Jerry.
I was just checking to make sure everything works as usual.
Yeah.
Okay. I'm just always worry about exactly everything being on right. Okay. I'm a perfectionist.
Okay.
Good. Okay.
Howdy, folks. Are you back? Are you ready? Welcome back to the last speaker of today. I know we are all on the edges of our seats, but remember, we do have a third one lined up in collaboration with the Unstoppable Clojure community. Renzo, are you here with us?
Yes, I am. I'm just checking the vitals. Everything is good. Jerry, I can see you on screen.
Would you like me to share my screen?
Yes, if the first thing is the first slide, then yes, please go ahead so we get it on the screen.
Okay.
Perfect. Yeah,
okay.
That's perfect.
Wonderful.
We're just going to introduce you. 1 second.
Looks like we are ready. What a great way to close the conference. It's our honor and our pleasure to be joined by the great Gerald J. Sussman. It's difficult to sum up all of Jerry's achievements and contributions to computer science, but let me attempt with the following. Jerry is professor of electrical engineering at MIT. He has been involved in artificial intelligence, programming languages, and science education. He has also co-created Scheme with Guy Steele. Jerry is very well known for his work on structure interpretation of computer programs, or fondly known as SICP or SICP, a reference textbook that is often cited as one of the best in terms of elegance and functional purity. He recently published another amazing book titled Software Design for Flexibility. We're going to hear about a few interesting developments of some of the ideas there. I would ask the audience members to get these books ready if you have them. Take it away, Jerry.
Well, thank you. I am very pleased to be here. And I wanted to thank Tovia and Marcus for being just before me. I listened to their talks. They were very interesting. Of course, the stuff I was doing is mostly for very advanced students at MIT, graduate students and undergraduates at the advanced level in physics and in mathematics type subjects. Although SICP was originally for freshmen. But today I'd like to talk to you about is stuff that's brand new. It's sort of hot out of the gray matter, as we would say. It's not completely worked out, okay? And it's sort of what I've been thinking about recently. So I suppose we'll get onto it. Let me see if I can advance my slides. Yes, okay? What I'd like is to make systems that are easy to change. That's the most important idea, okay? That they have the property that they can be adapted easily to unforeseen needs, that they're flexible, that they're incremental, and I don't see a lot of detail. One of my biggest goals, you see, is to improve the expressiveness of programming. All my life, I've thought about programming as being something like other linguistic disciplines, like mathematics or English text, okay? It's an expressive medium that you write things down in. And can write beautiful things. You can write beautiful programs like poetry, okay, or Maxwell's equations are beautiful. You can write prose and Maxwell's equations when using it to describe the way electromagnetic radiation works. That's prose. It's describing the world. Okay, you can make art and music, and all of those things are a kind of expressive mediums, and programming is another kind of expressive medium where we make expressions that we couldn't say in other languages. So, the goal is to figure out how to say things that are otherwise hard to say. The current programming styles we have in most languages and most of programming in general is ponderous. The elaborations we want to express an idea complicate the expressions, and I'll be more clear about that. Okay, so here's an example. Now, I'm sorry that I happen to like parentheses. I did replace the colons that I would use in Lisp or Scheme with dollar signs because I found out that in your language, Clojure, colons mean something else. So I put in, these are presumably perfectly good variable names. But here's a simple program that computes the current in the junction diode. As an electrical engineer, you might know what that means. Given the voltage across the diode, it doesn't matter. You don't have to know what it means. Okay, so it's a simple program, and it's a product of the saturation current and an expression which contains various physical constants like the charge on an electron and Boltzmann's constant and the absolute temperature and things like that, and the voltage measuring. Okay, so that's what this is, and I want to be able to say things about this program. First of all, the voltages and things like that are inexact numbers with specified uncertainties. There are units. The voltage is in volts. The current is in amperes. The charge is in coulombs. The temperature is in kelvins, and Boltzmann's constant is joules per degree Kelvin, and the result is in amperes. I want provenance. I want to make sure that if something goes wrong, I know who to blame. Where did I get this data? The data might be wrong. So the company that made the diode, perhaps, International Rectifier Company, has to be able to sign the saturation current for the diode. That Boltzmann's constant and the charge on an electron are published by the National Institute of Science and Technology every few years. They the best estimates of the physical constants. Perhaps I measured the temperature in the room I'm working in. The formula that this comes from a book by Searle and Gray, okay, and the procedure happened to be written by me. And then there are reasonableness constraints. I could never have a voltage for this diode bigger than 1 volt. By that, I'd have thousands of amperes going through it, and it would go boom. Okay, so I want to put in constraints like that. Okay, but I want more. I want checking my units and reasonable constraints at runtime and compile time where possible. I want symbolic partial evaluation, so I can look at these things as symbolic expressions as well as numerical. And I suppose Tovia and Marcus were showing some of that with the kinds of code that I tend to write. I want symbolic partial evaluation. So as I said that, I want estimate of the uncertainty. That one I don't know how to do, but that's what I want. I want tracking of dependencies. So if I get a wrong answer, I want to know who to blame. Is it the person who wrote the program, like me? Is it somebody gave me a wrong value for the physical constant? I want to know who did it. Okay. I want that sort of thing. I want the automatic derivatives of my program and integrals, perhaps. I want the derivatives integrals to inherit the same annotations. Okay. And I want the annotations to be incremental and additive, requiring almost no change to my code. Now, here's the big one. I have a very beautiful program. See over there? There's a tiny little program. It's simple. Okay. It is elegant. It doesn't say any more than it needs to. However, I want to be able to add all of this information without burying that program in a mess of declarations that make it impossible to read or be understood. So I wanted to invent a new idea, which I call layering, and that's a very hard problem, whereby it is the case that I can sort of do what an architect does. Okay, that an architect in at least the old days, they would sketch a plan on a big board, right, for some structure they want to make. And then they have to after the plan is sort of explains what rooms there are and things like that, and the sort of what hallways and stuff like that. Then they put a piece of plastic down on top of it and draw in the next layer, which might be something like how the elevator connects, or how the HVAC, the heating, the ventilation and air conditioning system is built in. And then another layer where the plumbing goes, okay? And each of those things has to be sketched in on top. But those layers don't destroy the basic plan. The plan does not become too complicated. If you take off the layers, you can see the original plan, okay? So that's sort of what I care about. Now, we don't know all the answers. So, of course, my friend Chris and I, who, by the way, Chris worked for me at MIT for 26 years. Then he worked for Google for about 10 years. And now he's doing something else. But I'm not sure I want to talk about that. But in any case, we wrote a book about this. And we don't really know all the answers. We put down I would say is our current best estimate at the time, which is about a couple of years ago. And I want to consider one less developed idea, the layering idea, the one I've been trying to tell you about. Okay, so first I want to say a little bit about the fundamental ideas in this book. Okay, the very bottom of it is something called predicate dispatched extensible generics. We know what generic procedures are. For example, in all Lisps, the addition operator adds integers. It can add floating point numbers. It probably in a scheme, it can deal with complex numbers, rational fractions. Okay, and not only that, they mix correctly, and it's a generic operation, say addition. Okay. On the other hand, people don't usually make it so it's easily extensible. Python allows some of those things for very simple operations. They call them Dunder methods, which I'm not sure I care about. But the bottom line is, what if we wanted to make it so it's completely general, that all we have to do is say that a predicate determines what kind of thing something is, and we dispatch on those predicates, okay, to determine what handler is appropriate for every operation. Okay, that's actually how we implement the forward mode automatic differentiation that was nicely explained by Tovia. Okay, if you look here, this is what we have. We extend all of the primitive operations to handle the dual objects, dual numbers, which were invented, by the way, in the 1870s by the famous mathematician Clifford. Okay, the dual numbers. If you pass a dual number through a function, it should produce the function's value and the derivative of the function's value multiplied by the increment, so that the chain rule is automatically correctly implemented. Because if I take this output and pass it through G, I get the correct answer for the base value, the primal value, and I get the correct value for the derivative, which is evaluated at the correct places. Okay, that's just one kind of thing you can do when you have automatic differentiation. One thing you can do when you generically extend your arithmetic of all the possible functions to deal with, say, a new kind of object that was not thought of before. And this should be done easily. Okay, so that's an example of that, but also it can deal with symbolic expressions and everything else once you do that. Now, but layering is not the same as generic procedures. It's similar in the following way. Generic procedures extend a procedure so it can operate on data it could not have operated on before the extension. When we extend addition to append strings, okay, when applied to strings, we can do that. But with layering, the data potentially has metadata associated with it. And the procedures are extended with the metadata. So an example of metadata is, for example, the units. Okay, an example of that metadata is the provenance, is the support set, where that came from. Who signed for it, okay, for that data, and what you want to do is extend all the procedures to operate on the metadata as well as the data in parallel with the operation on the data. So, for example, when we add a units layer, okay, we extend multiplication to do multiplication of the data as well as produce the units for the product, which basically adds the exponents. Okay, if you want to think of it that way, for each of the units. Of course, the metadata is itself data, so it may have its own metadata. So it's a whole nother thing besides just generics. And although in what I showed you before here, we implemented the automatic differentiation in schema tills as a generic extension to arithmetic, it can also be implemented as a layer because the automatic differentiator must compute the value as well as the derivative to make the chain rule work, as you just saw here. It's computing the value as well as the derivative. It computes the value as well as the derivative. Okay. So let's do an example of layering, just to show you what it's like. Okay. So we go back to the example I had before, because it's small enough to fit on a screen. I mean, I like big examples, but but the small examples are appropriate for the screen. So here we have this, again, method of computing a current given a voltage based on some other data that's given to us from somewhere else. Okay, so here we have the saturation current, the electron charge, Boltzmann's constant, and the absolute temperature in degrees Kelvin of the room. And over here we have the result. The result is, what's it, 1.2 milliamperes. That's a reasonable number for that kind of diode. But now we add provenance. Let's sign each of these pieces of information. The manufacturer can sign the saturation current. So I'm changing IS to be the signed version of IS. The physical constants are periodically published by the National Institute of Science and Technology. So I sign Q and I sign K by where I get that data. I personally sign the temperature because I measured it. I have the thermometer, okay? And I signed the voltage I'm putting in because I'm doing the experiment. And what I get out now is more information. I get the base value, which is indeed 1.2 milliamperes. We'll worry about units later. And I get these are all of the sources that this value depended upon. Now, I consider this to be a very important idea because consider all of the great scientific papers that are written in, say, places like medicine, okay, or biomedicine. Many of them actually are wrong, okay, because an experiment turns out later to have not been done right, or something like that. But there's a huge pile of deductions based on those papers. And supposing if we find something really is wrong after much deduction, wouldn't it be nice to be able to mark all of the tree and say there's something wrong in this tree, and we mark it for, we see another case where something's wrong, mark all that tree, and we find, hey, the intersection is this paper that's got the wrong measurement. And might make things move much faster in that science. Say, also, but I'm going to keep going with this. Let's add more information. The formula was itself signed by the source book I got it out of, Searle and Gray, okay? And I wrote the code, so I'm going to, oh no, sorry, that's not yet. I'm just checking that still works, okay? That's just added, and the code still works, of course, with unsigned inputs. But later, I can seal the procedure. I can say the current, I signed it, the procedure that measured, that computes the current, that's ID, okay? Going back there, just to remember that that's what it is. ID is the procedure that computes the current, okay? That was being signed by me because I wrote the code. And now if I look at the result of calling that procedure on 0.6 volts, okay, that I had measured, okay, I have two layers of the result. The ultimate result is the 1.2 milliamps. That has its own provenance, how it was computed, okay, including all of the ingredients that went into it. But also there's provenance for that structure, which is that it was because I passed in a number which was signed by GJSV into the code that I wrote. So this is provenance of the code that processed it. Might be argued that we should flatten this. That's easy, but the real bottom line is that I'm collecting that information. Okay. Now, real complicated programs are much more complicated. Right? For example, there are conditionals and loops. So here's a nice little looping program. Does nothing very much. It says, given a count of n I want to compute. If n is 0, then I'm done. Okay. Otherwise, I want to count by subtracting 1 from n and go around this loop. Okay. Now remember, scheme is tail recursive, so this is not intended to push any stack. Okay. Now that's going to produce a complication, which we'll talk about. But in any case, I'm signing every level a piece of this. The 0, which I'm comparing with n, is signed by Frodo. The job being done, the done result, is signed by me, and the 1 I'm subtracting off of n is signed by Mr. Bilbo. I see somehow I got into the Lord of the Rings when I was typing this. And if I call this by asking Sam Ritchie to give me a number, okay, actually that might be Sam from Lord of the Rings, give it a 0, of course, the only thing that matters is these two parts of the clause. There's the predicate and the consequent. Okay, so Bilbo is irrelevant here. Okay, but if Sam gives me 5, then it goes through the entire loop, and therefore Bilbo is relevant also. Now, this is a complication. Anytime you deal with conditionals, it changes the way the interpretation mechanism works. One way to play this in a standard language, the first way I did this, and the way I've done it, to make it work at all, is by making if into a macro that expands if into a slightly more complicated situation. But that basically causes the compiler to produce lousy code. It works, but it produces lousy code, and also it is very inelegant. The easy way, and the layering, because of the fact that I have to combine at the end of every computation the various layers, which are the various metadata with the data, and pass it along, that would automatically kill tail recursion if it's done in a simple way, the easy way to do that, because what it does is it puts extra stuff on the stack which is the guy who's collecting that result. Okay. Now, in the last few weeks, actually, I've conquered this problem, and I will explain that. Okay. So that's why I'm saying this is hot out of the gray matter. So the way we did it in the SDF book, we didn't have tail recursion working for layering, but now I know how to do it. Okay, so I'll tell you more about that. But in any case, just to prove that the stuff I do works, okay, I did a big problem. Well, it's not a big problem. It's big enough. It's so big that I can just barely fit it on a screen, but it's small enough so it tests lots of stuff. And this is basically a Y operator like definition of factorial and Fibonacci. And they're co-recursive in the way I wrote it here. And so I can compute the factorial of 5 and the Fibonacci of 10. Okay, and I'm getting, of course, the results, which is, and also the sums. So I get 55 for Fibonacci of 10, and factorial of 5 is 120, and the sum is 175. And these are the various contributions which are based on the signatures, okay, of all the constants. This is just to make sure that everything was sort of working sensibly, that the interpreter I built wasn't broken. By the way, if anybody has questions, I'm pleased to answer, even if you want to interrupt me. But we can talk later as well. Okay. So first of all, a little bit of a summary of what this is before I go further. The way the way layering works is that it's somewhat like generic procedures, but it's not like them in other ways. In generic procedures, there's a single layered object. Whoops. Unlike generic procedures, there is a single layered object data type that associates a layer name with its data or procedure. There's a base layer, and there's annotation layers such as units, provenance, derivatives, whatever we want to add. Could be types. Okay. But it's very much like generic procedures in that a layered procedure has a handler for each layer of interest. So I have to build a handler for all of the primitive objects and the way they're combined, of which the most important way of combining is, well, that's what if is. That's one way of combining. And another way of combining is by definition, by the lambda abstraction. Okay. A layered procedure has a handler for each layer of interest. The unlayered procedures must look only at the base layer of the layered argument, okay? And most layers are self-contained. The handler will not look at arguments other than the ones for its layer, but remember, multiplication needs more information. And that's because if I pass 2 arguments in to multiply, one of them is 0, then the provenance of the result depends only on the provenance of the 0, because 0 times anything is 0. So it doesn't matter what the ancestry of the other argument is. A handler will also not generally be invoked unless arguments for the layer are provided. And there are defaults for missing layer values. So there's an empty support set for provenance. There are dimensionless quantities. There are mathematical constants. We'll worry about that. Okay. So I just want you to get the idea that it's something like generic procedures, but instead of it being one object which is being passed through a procedure, which may have many handlers for different kinds of objects. Okay, here we have an object with many layers, many parts, each of which these parts is being sort of routed into a layer processor for a layered procedure. And then the results are recombined at the end. And this has to be done without killing tail recursion. So just be a little bit further, a layered procedure, layering is compatible with generic procedures because a layered object is one for which there is a test for it. Layered object predicate can be used for generic dispatch. So in fact, generic procedures can have handlers for layered objects. A layered procedure is itself a layered object. The base procedure of a layered procedure can be a generic procedure, and the handler procedures can be layered procedures, and they can be generic procedures. So this is all mixes together in a way that sort of works nicely. So first of all, I'm going to tell you what I did. Okay. I'm not going to show you the interpreter that I wrote because it's a long story. It's boring. Okay. And the one great thing about it is it's generically extensible. Okay. But it's a continuation passing interpreter. Now, I don't know how many of you know about continuations. That's a thing that is available in Scheme. But think of it this way. If I have a compound expression like the sum of the product, the sum of 1 and the product of 2 and 3 and 4, okay? So the sum takes 3 arguments, one of which the middle one is a product. That expression is waiting for, at some point, is waiting for that product. In particular, I can't do any of the add until that product comes in. What's going on there is that another way to think about that is that the interpreter is got a procedure that takes one argument called the continuation that's waiting for that answer and will then pass that to the addition. That's called the continuation. Okay, and if you write your interpreter correctly so that everything in the interpreter and therefore in the compiler is continuation passing correctly, then you have what's called a continuation passing interpreter. And once you have that, you can also return that continuation to the user somehow, in which case you get call with current continuation. That's just a simple way of doing it. Anyway, I needed that because I wanted to be able to do something that makes all of this work nicely. And I'll probably explain that. But first, I want to just show you what the setup is once I've done that. What I really have to do is I have to give the handlers for everything. So I'm going to have for the provenance layer, I'm going to have a default value, which is the empty set. I'm using lists as sets. Okay. So I have an empty set. I have a union of those, because much of the time when I'm dealing with a provenance, the most important thing to do is say, here are all the contributions. I want to union those together. And so there's a little bit of that. And then there's some special thing for dealing with some of the primitive procedures. Okay, let me see, there's my mouse. Okay. And then there's a special setup for conditionals, which is also unioning stuff. This is very, very complicated in the insides of the interpreter. But what's happening is I'm making a handler so that the results of the predicate calculation can contribute to the results of the consequent or the alternative calculation for provenance. That is, if I determine that the predicate part of a conditional is true, okay, what that means is I have to say, by picking out the consequent to be evaluated, and the provenance of the result of that has to be the combination of the provenance of the predicate plus the provenance of the consequent. That's the provenance of the conditional as a whole, and that has to be arranged. Then primitive procedures have to be given their provenance handler, like addition, okay, subtraction. Multiplication has to be a little different for the reason I described. Okay. Division is a little more complicated the same way, because it's like multiplication. If the dividend is 0, the result is 0, independent of what the divisor is, unless the divisor is 0, in which case we get an error. Okay. There are also, there are comparators that have to be told what to do. All I care about is I care about the arguments, the provenance of the arguments to produce the provenance of the Boolean result. Okay. There are one argument functions like exponentiation, sine, cosine, etc. And there are a lot of those. And then there are Carcutter and cons and everything else. And just for every primitive, I'm giving a layer. Then I don't even want to get into this. Okay. This is the fact that I have to describe how to write a signer, okay, and how to assign procedures and so on. I'm going to ignore it. But I had a lot of trouble with that. It took me a while. The really important thing is this, okay? Tail recursion. And I want to make this clear to you what it means. For those of you who are not familiar with this, I could write factorial as a recursive procedure like this, as you all know. Factorial of n, if n is 0, the result is 1. In other words, it's n times factorial n minus 1. Because of the fact that this factorial of n minus 1 has to be computed before the product can be computed, the product has to wait for that result. Therefore, there's a stack frame produced for catching that answer. So this builds up linear stack. It's linear in n. However, I could write it differently this way, as an iterative procedure. I could have a procedure which has two numbers, a product and a counter. Okay, it's initialized to 1 and 1. If the counter is greater than n, then I've got the product, so that's okay. Otherwise, I go around the loop, multiplying the counter by the product and adding 1 to the counter. This does not have to build stack because there's nobody waiting for this answer. The only guy who's waiting for this answer is way back over here, the guy who called factorial. Okay? So there's only one continuation waiting for this answer. So this has constant stack, okay, rather than this, which has linear stack. So that's called tail recursion or tail call optimization. Okay? And the scheme, we do that, and I care about it a lot because it makes the language very simple, which means, and the reason why I like this language very simple, the bottom language, I don't care if you build, lots of useful macros and things that turn it into while loops and for loops and all that. I like to have the bottom language very simple, so the interpreters and compilers are very simple, so I can rewrite the interpreter very fast. I can do experiments with the whole language, and everything works. Okay, so now here's the trick. Okay, the essence of tail call optimization is that the mechanism of procedure call itself does not push stack. That's strange, right? It's not like other languages. The mechanism of procedure return does not pop stack. If any information like the environment or the return address will be needed after a call, the caller pushes that information. The caller is responsible for popping what is pushed. This is called a pure caller saves convention, which is not what they do in, say, C. A layered procedure has multiple components. Each component must produce a value. Those values must be combined. Is that a contradiction? For months, I was stuck on this, but it's not the case, okay? What I can do is I can augment the continuation to collect and combine the results of the layers. And that extended continuation is still one continuation, so it's only allocated once on the stack, okay? This extended continuation provides a locus for collecting the information from the predicate of conditional with the values of the consequent, for example, or alternative. But also, it works for tail calls. So what I'm doing is I've changed the interpreter by augmenting every continuation in the continuation passing interpreter with an extension that can catch stuff. Okay, but that extension doesn't grow except for the data that's put into it. It doesn't. There are not more layers added in. Layers, wrong word. More stack frames added in. Okay. So let's add a units layer just to show you. Okay. So now I'm going to have to put in. I have to put in handlers for all the primitives. I'm not going to show you what the handlers look like. They're pretty simple. Well, this one's doing is checking that all the inputs have the same units, and then make sure the output has that units. And that's true of subtraction. For multiplication, well, I'm going to multiply the units. Okay. For division, I'd have to divide the units. Okay. And what multiplying units means is basically the units are things like, kilograms cubed. Well, multiplying that by kilograms to the -1 gives me kilograms squared. So it's really just adding exponents. There's the equality. You think the comparators, the output is unitless because it's a Boolean, but the inputs all have to the same units. Okay. These are, again, exponentiation. All of the standard complicated functions are unitless input and output. Square root is special. It divides the units of its input by 2. Well, it takes the square root of the unit, which is dividing the exponents by 2. And now we can do the example and show it to you. So continuing with the same thing I had before. I'm going to add another layer. Remember, we already had a layer for provenance. Okay, so here, the saturation current is in amperes. Okay, the charge on an electron, which was told to us by NIST, is now coulombs, which is amperes times seconds, which is literally just a list here of amperes and seconds. These are the exponents. The Boltzmann's constant is actually joules per Kelvin, which I'm writing here in the traditional way. Okay, I actually could, if I put little squiggly brackets in, I could do this with tech. Okay, but let's not worry about that. So that's kilograms meters squared per second square per Kelvin. Okay. The temperature is in kelvins, and voltage is kilograms square meter. Okay, voltage is basically what is it? It's joules per meter. Okay, so that's what's happening here, I think. No, I just said that wrong. No, it's a joules per kilogram. Excuse me. Okay, so that's what this is. And so I hope I wrote that right. The answer is right, so I don't have to worry about it. Whether or not I wrote it this way right is wrong, it's a different question. Okay, and so if I put in if I just look at, for example, what that object looks like, it's a thing with a provenance, with a units layer, and a number. Okay, but the original program, we can still work with it. We don't have to change anything to deal with units. Okay, it still has the signature in by assigning the formula by Searle and Gray. But now if I put in a voltage with units that was signed by me, out comes exactly what I expect. Okay, I get the provenance for the call, I get the provenance for the result, I get the units for the result, and I get the 1.2 milliamperes output. Okay, so this is what's going on in my head right now. I'm sort of beginning to summarize. The idea of layering seems right to me. What it's doing is it's factoring the problem of programming into smaller pieces, and that's always better. It's dividing it up so that my poor program over here, this program is not covered with lots of detail the same way. If you're writing in Java, you have to, what's the right way to say it? It requires a great deal of ceremony to get anything to work. Okay, and that's because you have to make the compiler writer happy by putting in all sorts of detail that's irrelevant to your idea. Okay, that's a problem in most languages, but Java is a beautiful example of one that does it to a great extent. Makes it really hard to write code and to see what you wrote. Okay, I want to keep my code to be simple. This is my simple code, but I want to be able to dynamically add layers, okay, without changing my code. I want to dynamically extensively annotate something with metadata without actually changing the program I'm writing. And this is, so it means that there's got to be ways of writing the layers, okay, and hooking them together with the code base that you're working on. My experiment here that I'm showing you with changing an interpreter, writing my own little interpreter, is it's not hard to approximate. I need layered objects and I need small modifications, perhaps, the interpreter compiler. If you know enough about interpreters and compilers, which of course I do, it's not a big deal to do that. But it took me a great deal of effort to think out that extension of the continuation objects in the interpreter. There are lots of, unsolved problems. There's a painful problem of I/O, which is related to the challenge of editing a program factored in this way. One thing that, my favorite program at all, my favorite piece of software ever written is Emacs. Okay, because Emacs was written 40 years ago, and it keeps being extended, and it keeps working, and it works really reliably and really well. Okay, and the one nice new thing that's been put into it recently in the last 5 years is org mode, which is sort of like a layering for text. Okay, you could put in your code, you could put in, so you could have sort of what would be called literate programming style. You could get it to output in LaTeX. You could get it to output in Tech Info. You could get it to output and do all sorts of things. You could put pictures in and everything else. And it's a great thing. And it's an outline. Okay. And you could have different layers with different layers of detail. Okay. So I'm inspired by that, but I don't know how to do it yet. Okay. So what I'm saying is I need your help. Okay, you're the power. Okay, I'm just producing ideas. Yes, indeed, there are some problems. In general, conditionals need special treatment. The provenance of an if is the provenance of the provenance is a combination of the provenance of the predicate part and the provenance of the selected alternative. There's a problem with tail recursion. Okay, because I have to make a layered object at the end. But perhaps that idea is wrong. I have solved both of these problems by making a new interpreter. But is there a way of fully implementing layered systems without a new interpreter? Is there some trick I hadn't thought of? I don't know. Okay, maybe you have an idea. Okay, and what would oops, that's got a problem. That should be and, not and. What would an IDE for layered systems look like? Is there a kind of Emacs-like structure that we can invent for being able to edit these layered systems so that the various layers can be hooked together, okay, and yet we can separate them to work on them separately? Okay, so that's where I need your help. Okay, I need your help in one more way. Okay, everything I do and all my books, okay, are basically free. Okay, I want you to support and contribute to free software, where free doesn't mean free as money. It has nothing to do with free as in free beer. It's free as in free speech. Okay, so please support and contribute to free software. Thank you. Now I'm happy to take questions.
Thank you very much, Jerry. It seems
that
we're all very, yeah.
Unshare?
Yeah, you can unshare.
Okay, good.
Thank you.
Okay.
So it seems like they're all very silent and nobody's listening to you, but we are all listening very carefully. It's just this virtual environment that doesn't allow us to, clap our hands or make you feel proud.
You know what? I've been last year during the main pandemic, the first wave, I had to teach classes remotely. I hated that. I like to be in a room with people. Yeah, I want to be looking in your eyes and talking to you. Yes, and I know I can't do that here. And I'd like to use a chalkboard. So, are there any questions I can answer?
So that was
Go ahead, Jordan.
Okay, fantastic keynote, Jerry. I wanted to say that predicate-based dispatch procedures personally are some of my favorite techniques that I've learned to adapt from your work to my work, and I've benefited a lot from that, so thank you. And I look forward to extending that with what I've learned from you today. And so to everybody else, we would like to go into the next section and we'll have the opportunity to take some questions from you. But first, we'd like to do a fun little show of books. I know a lot of us have these handy. And so if we can get these handy and turn your cameras on, we're going to see how many we can get.
Yeah, come on.
Going to give you Well, yeah, we'll wait for like a minute. Everybody grab it. And then I will be taking a screenshot.
Oh, Jerry's got many.
Okay. I don't have 4 hands.
Okay. 5, 4, 3, 2, 1. All right, keep them up. Screen shotting. Woo!
Thank you, Jordan. Okay, so let's start like the Q&A. I just wanted to repeat a little bit the mechanism of the Q&A. Please raise your hands if you want to ask a question. We'll go with the raised hands first of all for interaction, or post your question on the QA channel, QA dedicated channel. So we have already a few. We can take James first, who I see here at the top. Should I allow? Yes, sorry, go ahead, James.
Hey there, Dr. Sussman. Thanks so much. A while ago, I was very inspired by the concept of generics. This is, of course, before layer procedures came out. And I wrote what I thought at the time was an extremely readable program, at least at the top level, the top level elegant main function. And I came back to it about 2 years later, and I had to modify it and to basically take the complex data type that was returned by it and then add another operation onto it and do some further things. And what I found is I had difficulty knowing what it was actually doing at that point, because I could read it like an English sentence at that point. It was very beautiful, but I had difficulty with the code navigation because I was using a dynamically typed language, and I wasn't able to sort of navigate without doing some complex debugging down there. Now, the methodology that you've outlined here, and I think the interpreter might be part of the answer for this, but I was kind of curious if you had any thoughts on good ways to organize the code, at least in terms of code organization, so that when for instance, let's say that the locality of the declaration of your data type is not visually near where you end up using. Let's say I just have some variable Q right there or something like that. It's not necessarily immediately obvious to me what the effect the plus operator is going to have on it. And then I've defined various behaviors for the plus operator all over the place. And it's difficult for me to tell from like the argument signature what type that is or what sort of operations it's supposed to support. So it's kind of curious if you've dealt with anything like that and what your techniques you use for working with navigating those generics.
Fine, that's a great question, and it's very interesting. The way in which I think about it is 2 ways, actually. There is a traditional thing that you would learn from perhaps early programming, where you have a big string of a conditional with a big string of condiq mumble quote foo, okay, for a whole bunch of types, okay, and that would be the way you would just make a dispatch on the arguments to a function. The functional sort of all possibilities. Then there's the thing you learn from the object-oriented world, which is you organize it by the data type, and you put the handlers in the data type for all the same operators. Okay, and of course, the real truth is that it's really a table, which is a sparse table, which is the operations and the types. Okay, which you're filling in some and some of the others. And so you could organize it by the operator, or you could organize it by the type. And not only, but the organizing by the type, which is sort of the object-oriented view, is not very good for multi-argument functions. Okay, that's so because it becomes a rather high-dimensional table. So I like to think of things in terms of the table itself, just to be very clear. Okay, I tend to not want to decide a priori that I have something that looks like an object or something that's being dispatched by conditionals. Now that does produce a bit of a way of confusing yourself, which is what you're alluding to. What I tend to do is I tend to organize the material based on the meaning. That is, for example, I might say that there's a whole bunch of things that have to do with making a symbolic extension to my arithmetic. Okay? The symbolic extension does not interfere with any of the numerical stuff, the old numerical stuff. Okay, so I never have to think about it if I'm changing the numerical stuff. Okay, it doesn't hurt. Okay, or if I change the symbolic stuff, that doesn't hurt the numerical stuff. And then I might add the automatic differentiation structure. Okay, that by adding, for example, dual numbers. Okay, it doesn't cause any trouble. Okay, because all the old stuff still works. So if I think of it only as all I'm ever doing is modifying a system by adding new capabilities, it's additive. The real problem has to do with whether or not I want to change the bottom layer. Okay, that's I think what you're worried about. So, for example, a possible bug that could come up is supposing I'm doing arithmetic and I have some complicated algebraic expression and I extend it to matrices. Okay, whoops! But remember, matrices are not commutative. Therefore, multiplication of matrices. Therefore, if I did multiplication in my original program, I've just introduced some bugs, right? And the problem is knowing that you have to go back and fix that. Is that helping? Is that helping you?
That's a really good example of it, and I love the idea of organizing it in a table. And I think that really plays in well with your idea that we could use some better IDE tooling to support these sorts of ideas
Yes.
as well, like being able to not just mentally, but to visually see that table. Because sometimes if I come back to something 2 years later, even if it was crystal clear to me at the time, I have no idea what that mental table is anymore. So
exactly,
yeah, great thoughts though.
But so that helps you? That's what I was hoping. I mean, yeah, I don't know exactly whether my answer got to your point. Okay.
Mm-hmm. Yep. Thank you.
Wonderful. Well, we have another hand up here, Edward Hughes.
Hey, Professor Sussman. Thanks for the talk. I had a question more about pedagogy, and one of the themes running through structure and interpretations of classical mechanics is that sort of intuitionistic and unclear mathematics and notation can get in the way of reasoning about problems and solving them. Now, in undergraduate calculus, some of us might recall we were told that we cannot treat dy over dx as a fraction, even though a lot of the symbolic manipulation that we do in math and physics requires exactly that. And now with dual numbers, you sort of extend your number system a bit, so you can actually do that. And given that it's such a powerful programming tool, I was wondering if you had any thoughts to whether its introduction to freshman math classes could have a similar effect that SICP does on people trying to learn freshman level computer science.
I see. Okay, that's very interesting. The motivation, a lot of the motivation came from for SICM came from reading these physics texts and realizing that they were hard to read. Okay, and part of the reason was, of course, that the math was, as I say, impressionistic, which means it left out a lot of detail. Okay, it was sort of just sketches of what's going on, and programs are not like that. But the other thing that's special is that Leibniz notation, the dy by dx notation, is very misleading when you go to high dimensions or higher dimensions. I was inspired when I was an undergraduate at MIT, probably before most of you were born. There was a book I got, I suppose it was referred to me by Marvin Minsky, okay, which was Calculus on Manifolds by Spivak. Okay, it's about 100 pages. It's a delicious book. Okay, and the whole purpose of this book is to start with basic principles and get to Stokes' theorem, which is the n-dimensional what's the right word? Generalization of the fundamental theorem of calculus, which is that derivatives and integrals are inverses of each other. And this book had the property that it alerted me to the problem that Leibniz notation was confusing. Okay, you could get into all kinds of paradoxical situations by doing the division, as you say, of d by dx, and thinking that that's what's happening. In fact, he starts out by he's the guy who pretty much alerted me to the fact that what I really want is derivatives of functions, not derivatives of expressions. Okay, which is the big D operator is derivative of functions. Okay, so going down that path, of course, you can eventually transform this into when I did the functional differential geometry. There is an interpretation of the dB dx and dx. Okay, and those are basis vectors and covectors in the manifold. Okay, in the tangent space for manifold, and that's very and the cotangent space, and that simplifies matters. So then it looks like you're doing the arithmetic on the d by dx and dx type objects as if they were sort of divisions, even though you don't have to think that way, but it just justifies that. Okay, but you have to build that through the understanding of the capital D. I think that we would be that introductory calculus would be vastly improved if we got rid of Leibniz notation and used the big D and talked about functions the same way that Spivak did in his little book. Is that helpful?
Yeah, that answered my question. That was more or less what I was thinking.
Look on page 40, I think it's 44 in Spivak's book. I'm just pulling it on my memory, where he has a diatribe against Leibniz notation.
I'll have to look that up. Thank you.
Yes.
Another raised hand, Ag Davies, take it away.
Hi, thanks so much for the talk. That's a really fascinating idea that I'm going to keep thinking about. Very, very simple question. What are some other layers that you can imagine being useful besides units and provenance?
Oh,
or even
one that's really nice is types. Okay, and type inference. Type inference is really easy to do, it turns out. And in fact, in our new book, we could give a very simple several page building of type inference. Okay, it takes only a few pages, to just show how to do it. Okay, but the point is that's something I like type inference. What I'd like, I dislike languages where there's enforcement, sort of a libertarian programmer. Okay, but I do like to get the information that the types gives me. Okay, and so I think that's an example of a nice layer. There are many other layers I can think of that are very helpful. As I said, things like tracking some of the uncertainty in a number. Now, remember that's hard. That for example, backwards inference of exactness is insanely difficult work. Floating point is the scariest business in all of computer science, as far as I'm concerned. If I were to be perfectly clear about it, and the only reason I'm willing to fly in an airplane is because it's a test pilot. I don't trust floating point numbers, but that's an example. What other things could I think of that are really useful in there? I want to be able to talk about. I want to be able to put on things like wrappers that are paranoid programming wrappers. So, for example, I'll give you a simple case where it's trivial. I want to say the output of this procedure, I know what it ought to be approximately. A reason, okay, given the inputs. I want to have an approximate answer that's computed that I'm comparing every time with the output. Okay, because the same way I do it when I'm doing real problems. I don't know if my computation is right until I said, is it reasonable? if it turns out that an orbital planet I'm computing happens to have planet X crashing into Jupiter, it's obviously wrong. Okay, so I want to have that kind of idea. So there's reasonableness wrappers that I want to put on things. I want to imagine that of course, I'm doing symbolic evaluation as well. That's very useful. If I'm debugging a complex numerical problem, then one of the ways to do it is look at the symbolic representation of the result and see what I actually am computing. But way back when I was developing the digital orrery, which was a piece of machinery for doing orbital mechanics calculations, this was in the 80s. I did it when I was on sabbatical at Caltech. And I have a bunch of friends helping. I made a special machine for doing orbital mechanics calculations. And one of the things we did is we did the computer-aided design of the hardware with code that I had written to do the computer-aided design. But one of the things I did is I made it so it could symbolically evaluate what went through the chips. Okay. So that in the simulation, so that I could put in, I could say, here's a floating point number and these two pieces of it, and they get recombined over here, and so on. And I could put in the algebraic expression that was the thing I was trying to compute, and then compare it with with what it actually did. Okay, at every stage. So that's the sort of thing I want to be able to do in everything. I want to have lots and lots of ways of making sure my code is good. Which is not the same thing as trying to prove it correct.
Totally.
Okay.
Yeah, thanks.
Is that helpful?
Awesome ideas. Yeah.
Okay, we have another hand raised from Philippa Silva.
Hi. Sorry to parrot everyone else, but thank you so much for your talk. I have a very concrete question. Like at some point you were listening. Okay, like we have to define how the arguments for all of these operations, how we're actually going to process this information, this extra information, this metadata. And it's like on addition, you combine it, etc. And then you got to multiplication, and you mentioned that multiplication by zero. If I remember correctly, you kind of discard all of this extra information.
Which kind of some of the information. Yes, it discards yes.
So my question there is, why does it actually, because like, okay, you return the zero, but one of the arguments certainly was zero. Why is the information for that zero not being used? So like the question is actually, which zero is actually being returned and which information associated? Because presumably like if this is just like, the nil element, there's a nil element somewhere that says, the provenance of this nil element is, this proof, etc.
Okay, very good. You caught it. Very interesting. A very interesting question. The answer, of course, is that you're absolutely right. Okay, the result being zero depends upon any zero in the inputs, right? But supposing there are two zeros in the inputs to a multiply, okay, then it's the disjunction of those two rather than so it's either this set or that set. But we don't know which, right? So that's really actually a place where backtracking can be useful. What that really is a place where we're saying that the actual provenance is an amb. If you know what amb is, amb is the procedure invented by John McCarthy to describe what's it called? Basically non-deterministic automata, which is amb of any number of arguments is one of the arguments, but I don't know which. Okay, and so the way to say this is that the provenance of something with several zeros in its inputs is the amb of the provenances of the pieces that were the zeros. And I didn't do that here because, of course, writing that code is big and complicated, and of course I have to do that if I'm doing a serious thing. Okay, and I couldn't put that on the slides. How's that?
That answers my question. Thank you very much.
And thank you for the question. That shows you were really sharp and caught it.
James, do you want to ask the next question?
Yeah, I'd love to. Okay, this is a bit of a softball question for you, Dr. Sussman, but I haven't seen the answer online or explained anywhere else. So I'm just really curious. What is the story with the hat?
The hat.
Your Shriner hat that's on every picture of
Oh,
you.
okay. Yes. Way back when I was running the introductory class 6001 at MIT, which was the thing that Abelson and I actually ran it together, and we wrote the book SICP. Okay. I would give a lecture every term, which is the eval apply interpreter lecture. Okay. And that lecture was always done as a fanfare, a lot of effects. I would blow things up. I use magician type tricks with stuff that would explode and things like that, because it's sort of magical. Okay. In other words, the very fact that you can make an eval apply interpreter, and it looks like what does that mean? What does it mean for the system to sort of raise itself by its own bootstraps? Okay, and it's beautiful, and of course it does. And to explain that it required some sort of fanfare. And it was always a fun sort of performance, which I would do. And I wear this hat as a magician hat. Okay, Hal wore a different one. He wore a pointed one when he did the lecture. Sort of the traditional wizard hat. So that's all it came from. How's that?
That's great. Thank you.
Love that hat. Favorite hat. So we have Sebastian Crane that has their hand up.
Okay.
Hello, thank you. I have two questions, and the first is about your talk, and which was very interesting. And the second is a more practical question about using the scheme programming language. So my first question was that when you mentioned the signing of values and functions, is that cryptographically signing or some other mechanism?
No, I used the word sign. I probably shouldn't have used the word sign. What I mean is that's just an attribution of who is responsible for this value or where that value comes from. Indeed, if I were worried about making this secure, of course we'd use cryptography. But as an old locksmith, I will tell you that cryptography doesn't answer a lot of questions anyway about security. Another way to say that is when a burglar goes after your house, it doesn't matter how good the lock is, he breaks down the door. Right?
Perfect way of describing it, yeah. So my second question was directly related to what I did earlier today, in fact, which was writing a scheme program to use the libnotify library, which is a C library. And I was wondering if you had any suggestions on how to write code that called C code in an elegant way, because just copying C expressions doesn't sound terribly nice. So I'm wondering if you had better suggestions for that.
Actually not, but I'm going to tell you the real story that I think. I think probably the main reason why Lisp didn't make it as a major language in the world is because it refused to make an easy foreign function interface to C. And the reason why it generally does refuse to do that is because Lisp is its own operating system, right? You don't want to, what you basically try to do is you don't want to, C programs are bad enough so that they can clear memory. Okay, they can basically destroy evidence of why they fail. Okay, and the nice thing about Lisp programs is that Lisp programs, when they fail, you're still there in the live interpreter, and you can look around and see what happened. Okay, and you could fix it, and you can understand it and inspect all the pieces. And this has been the big fight, of course, that most of the time you really don't want to incorporate C code into your memory image. What you want to do is to have what the operating system does, which is have a separation of processes, memory spaces. C code is so dangerous that may as well just connect to it by some good foreign function interface that goes through sockets or something, and that's not bad. And these days, machines are fast enough, so unless you're doing that at very high rates, it's not an expensive proposition. Okay.
Yeah, that's very interesting. So it might be.
Yeah. So I would make as a little server in C for problems that you want to call up, okay? And you make a foreign function interface in your Scheme or Lisp, and I have one right now that was made by one of my former students that allows me to call other pieces of code.
Thank you for the suggestion there. So writing the core interoperability parts in C and then using a socket, for instance, that's a really nice idea. Thank you.
Okay.
Thank you. Dustin, do you want to get the next one?
By the way, I just want to say, I have to leave at 4 because I have another meeting, believe it or not.
Oh, yeah. Fine.
Okay. Strangely enough, I have a meeting. Yeah, go ahead.
We'll try to make it quick. Yeah.
Yeah.
Jerry, can you explain again what you mean by layered Emacs and what you're looking for?
What I'm looking for is a convenient mechanism that I have where I can edit my base code, okay, or any layer, and make sure they still are connected correctly, okay, such that if I've layered procedures and if I edit them, or manipulate them, I can walk around and see only the part that I'm interested in, just the same way that the architect could look at the partee, the diagram, the base diagram of a structure he's trying to design, and pick off the plastic sheets and put them down and say, I only want this sheet, but not that sheet. You see, that sort of thing. So supposing I wanted to take my program and I only want to see the type information. Those are all numbers. Okay. Or I might want to say, take it, except for there's a Boolean somewhere. Or I want to say, take that off and I want to see the provenance information. Or I take that off and I want to see, and I want to work on that on each piece.
So you want to see the live runtime state of the running process per various layers.
Yes, and you want to be able to edit that. You want to be able to your whole program, because indeed I want live. I believe that the right way to think about things is the code lives for a long time. Right. This is not I don't like having to reboot things or recompile and reload every 5 minutes. That's a different kind of programming than the interactive way I like to live.
Yes, and Jerry, should we email you directly when we find the answer to this? Is there a GitHub repo?
If anybody wants to start talking to me, I have an email address that's at MIT. Right? I'm gjs@mit.edu. And if you want to talk about this stuff, great. And we should figure out how to solve, Sam Ritchie is a good intermediary because he talks to me all the time. Okay. So he can be a person you can contact who knows how to catch me at the right times.
Yeah. So Sam is.
I do not have a cell phone, by the way. I do not carry one.
Sam is in the Keynote. The Keynote Discord channel. So if you want to maybe to chat with Sam, so you can be a little bit of an intermediary between like the emails and so on, then that's a good study group that can happen there.
Right. Good. And yeah, it would be good to do that, to have a nice such arrangement of people who are really interested in trying to figure out layered programming as a thing that you can play conveniently rather than what I'm doing. I'm just developing the infrastructure. I'm a plumber.
The designer, perhaps.
Plumber. I'm figuring out how you hook it together, but I don't know how to make the nice user interfaces. I've never done that well.
Okay,
I have a question.
Oh, sorry, Jordan, go ahead.
Well, I want to follow up on, how do you not have a cell phone? How do you do 2FA without a cell phone?
People didn't have cell phones 50 years ago.
Well, two-factor authentication with everything, it texts you the code and then you have to,
I have a dongle. I have a little dongle that I plug into my computer and when I have to two-factor authenticate. Okay.
Oh, okay.
Look, I'll tell you, I had a student who I told monitor all the radio communications on his cell phone for a month. He threw it away afterwards. Because it's a privacy violation. Machine is a thing that's sitting there telling everything about you to people you don't want to know about you, like where you are, what you're doing, who you're with. Do you want that information being transmitted all the time to people who basically sell that information to each other? Okay. So I just don't have one.
I think you suggested a really great solution with doing all your 2FA on a dongle, because that's the problem that I know people are trying to get around is those codes.
And if people worry about emergencies, we didn't have these problems 40 years ago or so. We could, the old-fashioned landline telephones worked very well.
Wonderful. Well, we have a hand raised from Mike Nardell here.
Hello, and thank you very much, Professor Sussman. This might be a pretty obvious question or maybe a comment I'm raising, but it seems like one of the aspects of what you're proposing is with layered approach is it would subtly maybe push programmers towards really refining that base layer so that it really captures the essence of the meaning, and that subsequent layers could actually build upon that in meaningful ways, so that maybe, again, sometimes you write a function and it's really beautiful and captures really the meaning of what you want. And then sometimes it's just gunk. And it seems to me one of the interesting aspects of this is it really leads people like me, perhaps, more towards that beautiful expression of the idea and away from the gunk. I don't know if that's a overly simplistic interpretation.
Well, that's certainly what I intend. What I intend is to encourage you to make your code so you can read it next year. Okay. The most terrible thing about a piece of code is you elaborate it to put in all the special things you want to make happy about it, like all the things that are enforcing the types and making sure that all the details are exactly right, and then you can't read it because it's full of detail. You want those details to be pushed to places where that detail is separable. So I agree with you completely. That's my goal.
Okay, we are gonna take a question from Discord now, maybe a couple, and then you probably need to leave.
I have no idea what Discord is.
Oh, sorry, from the chat.
Got it.
We just want to make sure we can take another picture with you because a few people were not able to turn on their camera, so we can have like a larger grid, and we want to try that before you go. But before, let's grab a question from Discord. So, did you know about the kernel programming language from John Schutt? It is a scheme like Lisp with orthogonal first-class continuations and first-class environments, allowing non-massif expression by using its very elegant vowel calculus.
Actually, I don't know about it. Please send me email and I'll read about it. Cool. Is that new or old?
I'm not sure. There's an elaboration of that, but I'll have to go back and read.
Well, I don't. The answer is I don't know.
Okay, we'll get that question through you via Sam. So even if I squeeze hard, I can see spec being a layer. And I wonder if spec could be used in a way that interacts with object metadata. This could be Clojure specs. So I'm not sure we can ask you that because I'm not sure you know Clojure specs.
I don't know Clojure specs, but if it's a method, for example, writing contracts about code, is that what it is?
It's similar to declarative typing. So
yeah,
you declare
okay.
types.
Sure, I would love to have that as a layer. Absolutely.
Okay. So another one, Mr. Sussman, can you expand on the details of what makes tail recursion so challenging with layered approach?
Oh, I can say it again. The problem is that when I have a layered procedure, it has many components. Each component is computing some result. Those components have to be combined after they all complete, after they get their answer. Okay, that means that there's something that's waiting for that answer, for those answers. If that happens in the usual ordinary way, then you end up with a stack frame waiting for that, but it waits for that answer. Okay, that's what would hurt tail recursion. What I have to do is figure out some way to get rid of that extra stack frame, and the way I do it is by expanding the tail recursion, the stack frame, or call it the continuation is the right word, the continuation that's waiting for the answer anyway. Okay, without the, but it doesn't have to expand linearly in the number of guys contributing. It just has to be expand a constant amount, which is the amount needed to capture all that stuff. Okay, is that helpful?
I think so.
I should show you the details. The details are unfortunately there are a lot of many pages of details.
Yeah, they are telling me yes, it is helpful. Thank you.
Okay.
Okay, we have one last question from Discord, and then we'll get together for our pictures. So we'll do a redo. Everyone get your books again. From EB, we have the question, did you imagine or give any thought about how a security capability layer could work?
No. Immediately. And the reason why is security is not easy. Security is definitely, like floating point numbers, one of the hardest things in all of computing. I would say security has to be thought of from the beginning. That's one thing but the other terrible thing is that security is mostly not about your computer programs. Security is about a system as a whole. And the difficulty is that there are components in the system called people who can easily be caught by things like spear phishing. Okay. So it's not at all clear what you do. Tightening up, basically tightening up one place, like the software being exactly right, okay, doesn't necessarily help solve the real problem. I think the most important thing, the way I say it from the locksmith point of view, is the lock on your door does not protect you from the burglar. The lock on the door is a signal to say there is a taboo, a social taboo to breaking this door down. And we're going to enforce this taboo by legal means. We haven't figured out how to do that in the computer industry or in the, especially in the network. And I think we have to figure out how to make taboos that are enforceable if we really want real security. Is that helpful?
We think so.
Okay.
Everybody gather your books again.
Yeah, everybody gather the book again.
Okay, I'll get a
in
couple
the
of
meanwhile. And we are gonna thank one more time Dr. Sussman for everything he's done for us. Okay, yeah, we have a good 16 grid. Can we make it bigger? Let's see, can we make it bigger? We're going for 20.
5, 4, 3, 2, and 1.
Good. I also took one.
Okay.
Cool. All right. Thank you very much, everyone. It was nice. Nice cover. We're gonna post it straight away. Okay. So thank you. Huge thanks for Jerry for staying with us, inspiring us to learn better ways to program, think about problems, and design better applications. I think that was like the general message. And thank you very much, Jerry.
Thank you. Have a nice day. And I'm going to go away and get into my other meeting about the other meetings about grading this class that we just finished this term. So it's,
okay.
Teachers. Have a good day.
Good day. Bye. Bye. Thank you very much.
Thank you.
Bye-bye.
Thank you.
Thanks.
Okay. So we are about to wrap it up. Jordan, any other words we want to say?
So I think it would be really nice to highlight some of the contributions of some special attendees. Jacob, Edward Hughes, Egg Davis. The organizers just want to thank you for interacting so much and staying live with us. It's really a great help, and we really appreciate it. So I wanted to give you a little shout out there. And anybody else who interacted.
I'll add some credits for our generative art that we enjoyed during these 2 days. The special thanks go to Generate Me, Karsten Smith, Tyler Hobbs, Adrian Chirstay, Dominic Friesen, Jack Rusher, and if you enjoy them, please let them know. That's important. What's next? Jordan?
Oh,
I'm going.
okay. Yeah, I see. So we have a data science day tomorrow, which will be very special. Renzo, I'll let you take it from here.
Yeah, well, what I know is that it's got a lot of interesting talks, workshops, working groups already. And it's going to be like the full day because there are so many things to say. And it's going to be like partially revisiting what we saw in the past 2 days in a like a more pragmatic and practical way, plus other things. For example, Pavel is going to reiterate and represent what Stephen Wolfram presented during his keynote. So the bridge between Clojure and Mathematica, the Wolfram language, and plus other things that were not at the conference at all. So there's a rich program. I invite you to go on our website at the top. There is a like third day special, just close to the to the top of the page. If you click on that, you'll see the meetup link, and from there you can be there tomorrow and enjoy the day.
Okay, great. And I'd also remind everybody to check out London Clojurians on meetup.com for upcoming talks. Follow them on Twitter, all of the places. Follow them so we can be at more fun events together.
Yeah, and if you want to know our speakers even better, I don't know if you noticed, but we published a series of interviews with all the speakers that you saw so far. There are 3 of them that are still unpublished, so we'll do a surprise. We didn't have the material, like the physical time to put them out. But there are like 25 or so of them, and they're all very interesting. We're asking more or less the same questions, but they got answered in like very different and personal ways. So check that out. And I think that with that is the end of the conference, which is sounding really sad now, all of a sudden. Okay, well, a big thanks.
Someone
I should mention
has a hand raised. Maybe it's a question to you, Renzo. Sebastian.
Oh, there's a hand raised. Okay,
It
Sebastian,
is.
go ahead.
Thank you very much for this conference. It was wonderful, and I was wondering if you yeah, and it was Daniel Slutsky was very helpful and emailed me the Zoom link because I can't use Meetup. I was wondering if London Clojurians also had a like Zulip channel or something, so that I could be involved without having Meetup.
Not really, but there's a Slack channel. Now the name's escapes me, but it's London Clojurians. Maybe let me check. But that is the place. If you go on Slack Clojurians, I think there is.
Thank you.
I'm just double checking. London. I think there was. Yes, there is a London Clojurians. So that is the channel that we would use in that case.
So we have a question from Egg real quick.
And I see you have a mailing list.
Okay. So did we find the info for the third day? Is Daniel Slutsky the right person to contact for that? For the third day special?
Yes, indeed.
Cool.
That was the question. And yeah, many thanks to the organizers. Jordan for helping with all the presenting was fantastic. Pavel was in the dark room, managing a lot of the details that made this conference so smooth. Like all the transitions, fantastic, perfect timing every time. And thanks to
pleasure.
David. I don't know if he wants to join the call, but he's not in the call. Yeah, he is.
Yeah, he
okay,
is.
Sorry. That's the duck. David, you want to say any goodbye or thanks to anyone? Any comments?
He doesn't want to say anything.
Okay.
Hey,
No
Renzo,
thanks.
when's the hard copy of your book coming out?
It's been out for years.
I know. Well, but there's a reason. One is I'm slow. It took time. But the other is that at some point, like a couple of years ago, with Manning, we decided to make it mostly online only book. So they were reluctant to decide how to print the 1,000 plus pages somehow. But then they came back because there is request for the printed book. So it's really literally missing the preface. I just didn't have time this weekend, but the next will be the good one, and then it's off the
Perfect.
press. Yeah, it's really content complete.
So for Christmas,
and I hope,
right? That's what I'm
yeah,
hearing. Christmas
before
present?
Christmas. Yeah, I hope. I really
Beautiful.
hope. And I'd like a printed version of that too. So let's see if we can make
That
it
would
happen.
be really cool. Hope to see you all tomorrow.
Yeah, exactly. Hope to see you tomorrow. So conference finished, but tomorrow's on.
Yeah. Thank you.
Thank you. Bye.
Bye.